Okay, I'll be back in a minute.
Oh, no, I haven't let anybody in.
Ming-Chuan, how are things in Singapore? Are you back at work or?
Yeah, I'm in my office right now. Yeah, we're allowed to come back on alternate days.
Yes. Oh, on alternate days, I see.
Yeah, right. So my teaching is largely still online.
Mm-hmm.
Yeah, so unless your classes are really small, then we can have online, face-to-face classes. But most of us just doing it online. Yeah.
I see.
Yeah. But in terms of like COVID-19 numbers in Singapore, we're doing pretty well, actually. We opened up already, but the daily numbers are still in the single digits, so that's fine.
Wow.
Yeah,
wow, that's great.
I'm surprised. I'm also surprised. Yeah, I'm surprised. Maybe it's because we are a very compliant country. You know, people.
Well, there's that, right? Yeah.
Everyone wears a mask. Yeah, keep to social distancing and all that.
Yeah.
We're very compliant. Yeah.
Well, that's what you get. You're compliant. The numbers stay in the single digits.
Yeah, that's right.
Okay, let's see. So I just have to make a couple of announcements beforehand. We're just going to have a slightly changed schedule. So instead of having a breakaway today, we're going to do just an extended Q&A where people can just keep asking questions. Because after Edward Witten's talk, we've got an hour, and then the public talk starts. So I'll just announce that. Otherwise, it's quick.
You'll make those announcements beforehand?
I'll make the announcements in about 2 minutes or so.
Okay.
And then I'll just introduce you, and you can take it from there. Can you see my screen?
Yep.
Okay. So welcome everybody to day 4 of String Math 2020. And we have a very exciting lineup of talks today and a slight change in the advertised schedule that I just want to announce today. So very quickly, this is the Thursday slot. You will notice that we're not going to have a breakaway session today because we're going to extend the question and answer session from after the talk by Edward Witten, and we'll keep it going for a little bit, and then we're going to switch to the public lecture. I'll make another more detailed announcement later, but essentially I'm just going to keep the room open after Edward Witten's talk, and I'll close it at about 22:07 local time to allow us to go into the public talk session. As per usual, let me just remind you of the public talk again. The unreasonable effectiveness of string theory in mathematics. The talk will be given by a director of the Institute for Advanced Study, Robert Daycroft. You can register for the Zoom public talk. It's going to be in a different Zoom room to this one. And you can register at stringmath2020.com/public talk. You can also catch the live stream on the same live stream channel that we have going for this conference on YouTube. And then finally, the usual announcements for the day. Please read and abide by our code of conduct. Keep questions to the end of the talk. To ask a question, use the raise hand feature and wait to be called upon by the session chair. And otherwise, please remain on mute. The chat room can be used to ask physics questions to everybody or organizational questions to one of the organizers privately. And you can join our Slack channels to continue discussions for any of the talks as well. Today, we will be having a conference photo where I will ask everybody to, if you're comfortable with it, turn on your video feed and then take a screenshot of everybody in the room. So thank you very much. Our first session chair is Vishnu Jajala from the University of Witwatersrand. Vishnu, over to you.
Thanks. Well, good, whatever time of day it is. Thanks to Jeff, the organizers, for arranging this wonderful online String Math conference. So far, the talks have been enlightening and honestly fascinating. I look forward to more of the same today. The first speaker of the session is Meng-Chuan Tan from the National University of Singapore. He'll tell us about 4D Chern-Simons theory as a 3D Toda theory and a 3D 2D correspondence. Over to you.
Right. Hi, everyone. It's nice to see everyone here again, despite the COVID-19 situation. First and foremost, I'd like to thank the organizers for this invitation. It's a great honor for me to speak here today. And as Vishnu has just mentioned, I will be talking about 4D Chern-Simons theory as a 3D Toda theory and a 3D 2D correspondence. So the scope of my presentation. The scope of my presentation will be such. So I'll first start with an introduction and some motivation of why we want to study this. And I'll give you a summary of the results. So you could regard this section as sort of like a gong show of the talk. So just in case you get lost in some of the details in the middle of the talk, you would know what to look out for and what are the objectives of this presentation and what are the results that we expect to see. And then I'll go on to the talk proper. I'll start talking about this topological holomorphic GL twist of 5D maximally supersymmetric Yang-Mills, n equals 2 Yang-Mills in 5 dimensions. And by topological holomorphic, I mean, in 3 directions of the theory, operators are independent of, coordinates in those 3 directions. And by holomorphic, I mean operators depend on a z coordinate on a Riemann surface in the other 2 directions. And by a GL twist, I mean that if you reduce this 5D twisted topological holomorphic twisted theory, you get the 4D GL twist that's completely topological in all 4 directions. This idea whereby you have a mixed twist of a higher dimensional quantum field theory that reduces to a quantum field theory that is topological in more directions is something which you can, aside from a hard computation of the quantum field theory itself, You could see this from string theory as, low volume theories of branes in a background where you have this cotangent bundle that's in the orthogonal directions to the brane, and a normal bundle that is a subspace of this cotangent bundle, and then having the scalar fields in the world volume taking values in this normal bundle and therefore cotangent bundle, and the number of directions in which it gets twisted from a scalar field to one form. So from this sort of understanding from string theory, you could see that you could start off with theories in high dimensions that have a mixed twist. And as you go down in dimensions, the twist starts to get more topological in more directions. So in this particular case of an example in 5 dimensions, we have 3 dimensions which are topological, 2 dimensions which are holomorphic. And essentially when it means it's holomorphic in those 2 directions, you can see that the observables that we are interested in and computations we're interested in do not depend on the Kähler structure of those 2 directions. And so we could rescale them. And if you go down in 1 dimension, it becomes purely topological in 4 directions. So I've said a bit about this, but we'll see a bit more when we get to the main body of the presentation. And then I will talk about this 3D Toda theory. So this is like a 3-dimensional analog of 2-dimensional Toda theory that we know so well. The usual 2-dimensional Toda theory, which gives us a W-algebra symmetry and representations of W-algebra symmetry. But in this case, we have a 3-dimensional Toda theory. Okay. And where this Toda theory comes from is that it's the boundary theory of Fordich-Simons in which we embed into this 5-dimensional topological holomorphic maximally supersymmetric Yang-Mills. And then we will talk about this open topological sigma model on Bogomolny moduli space that we get by reducing equivalently in 3 directions of the 5D Yang-Mills theory. And then from comparing the Q cohomologies of the master theory, we end up getting this 3D, 2D correspondence between the 3D Toda theory and the 2-dimensional sigma model on Bogomolny moduli space. And then we will conclude our talk with the results that we have obtained and some interesting future work that we intend to embark on. So just as an introduction and sort of, in some sense, a motivation of why we want to study this. So if you look at the AGT correspondence, okay, this is a very well-known correspondence. It's been around, for 11 years now, I think, 2009 till now, it's 11 years. And essentially, it relates 4-dimensional n equals 2 gauge theory in its initial incarnation, of course, the Nekrasov partition function of n equals 2 gauge theory, and then conformal blocks of Toda theory, right? And so generically, it relates 4-dimensional n equals 2 gauge theory and 2-dimensional Toda theory on the Riemann surface, say sigma tilde. So among other approaches to understanding this correspondence, it is also known that the AGT correspondence can be understood in terms of this relationship between Hitchin's moduli space, okay, which is the phase space of the Coulomb branch of n equals 2 gauge theory in 4 dimensions, and W-algebra representations, which are representations coming out from Toda theory. So this was done by Nekrasov and Witten in 2010 in this paper called Omega Deformation, Branes, Integrability, and Liouville Theory. So, I mean, this is one approach. There are several approaches that tell you, the sort of the equivalence, why AGT correspondence is true. Mathematically, it sort of relates equivalent cohomology of the modular space of instantons with, modules of W-algebra. So there are many ways of sort of understanding the AGT correspondence, and this is one way in which you can see there's a correspondence between 4D n equals 2 gauge theories and 2D Toda theories. Okay, so this was done by Nekrasov and Witten. So in this work, we present an analogous relationship, okay, but it's between the moduli space of solutions to the Bogomolny equations and representations of a novel W-algebra arising from a 3-dimensional analog of Toda theory. So what we would have in the end, we would derive a Lagrangian that looks like the Toda theory Lagrangian, but it's valid in 3 dimensions. Okay. And as mentioned, this 3D Toda theory is a boundary dual of Fordich-Simons. So the Fordich-Simons theory that Costello, Yamazaki, and Witten has been studying for in the past 2 years. So we would define them on a form manifold with boundary, and you can see that we can show that if we start from a master theory in 5 dimensions, we would be able to get this 3D Toda theory at the boundary of Fordich-Simons. So yeah, so that's possible because we can embed the Fordich-Simons in a partially twisted 5-dimensional n equals to 2 super Yang-Mills, as I mentioned, and partially twisted in the sense of holomorphic topological twist. And we define it on a manifold with corners. Okay. And because it has corners, then we are able to do a different reduction in a different direction. And then we can also show that this 3D Toda theory is dual to an open topological sigma model on the Bogomolny moduli space. Now, this sigma model is an A-twist sigma model, so we would have Lagrangian branes, and that gives us some interesting mathematics. So essentially what we will be doing in this paper, so it's a very straightforward procedure. So the main body of the paper will just, detail out the computations and some of the details of the computations. So we start with 5D maximally supersymmetric Young-Mills on a 5-manifold that looks like this. Okay, so we have an interval, an R and an R plus. This gives us the corner and cross a Riemann surface. So the theory is topological in these 3 directions, holomorphic in this direction. Okay, so we could recast this twisted theory, the Lagrangian of this twisted theory, as a Q-exact term, and then a topological term that localizes onto the boundary. Okay, and when it does localize onto the boundary, if you're looking at Q cohomology, the spectrum of Q cohomology, operators and states of the 5D theory, we would see that it localizes onto 4D Chern-Simons, at the boundary of R plus, where it's the origin of R plus. Okay, so that's our boundary, the first boundary for 5D Young-Mills, and then we get 4D Chern-Simons on this guy here. Okay, and then because the theory is topological in these directions, we can also shrink I down, and there are boundary conditions at the 2 ends of I. Essentially, non-pole boundary conditions are admissible. They preserve the correct amount of supersymmetry. And then when we shrink away I, we would get a 3D Toda theory that lives on R cross sigma. Right, this is where we get the 3D Toda theory from one side. So this is one way in which we come down to 3 dimensions. So then on the other hand, so as I mentioned, it's holomorphic along these directions, which means it doesn't depend on the Taylor structure of sigma, and therefore we could scale sigma up and down. And it's also topological on R, which means together R cross sigma itself, we could rescale this factor in 3 directions down. And in the end, when we do that, we actually get a 2D A model whose worldsheet is a strip like this, a semi-infinite strip like this, and the target space being a Bergomoni moduli space on R cross sigma. Okay, so this reduction here is something which has been used in many places. It was first done by, I think, Harvey and Moore, Vafa, Sadov, Johansson, Witten, and Kapustin used it, for using 4D supersymmetric Young-Mills and equals to 4 Young-Mills, and then reducing it on a Riemann surface, getting a 2D sigma model on another Riemann surface, and then getting geometric Langlands duality from S duality. So it's the same kind of procedure. So essentially, we're just scaling down, different parts, scaling up, scaling down different parts of the metric, keeping terms that survive the scaling, and then integrating out fields which become auxiliary as a result of this rescaling. Okay, so we have this correspondence, as we mentioned here, between 3D Toda theory on this and 2D A model on this. And so the equivalence of the Q cohomology of physical states that descends from the master theory itself in 5 dimensions will then imply that modules of 3D W-algebra, which is the states coming up from the 3D Toda theory, the Q cohomology of states coming up from the 3D Toda theory, okay, defined on R cross sigma, are also modules for the quantized algebra of certain holomorphic functions on the modular space. Okay, so this part here is not so clear from just looking at the A model. Okay, essentially, if you look at the Q homology of states of the A model, there are certain strings which can be shown to be modules of certain types of strings with different Lagrangian branes, essentially canonical co-isotropic branes. They're space-filling strings that are between these 2 types of branes will act on strings that are suspended between different kinds of branes, and you can see this module structure coming out from it. And if you quantize the strings with the same space-filling branes on both ends, they actually correspond to they correspond to an algebra of holomorphic functions acting on that survive, that live on the Bergomoni moduli space. And this is where we get the segment of the modules of the states of the A string being modules for the quantized algebra of holomorphic functions on MB, and that correspondence with the modules of 3D W-algebras coming from the 3D Toda theory on the other side. Okay, so this is sort of the punchline, the mathematical sort of consequence of this physical study of partially twisted gauge theories in higher dimensions and then their different reductions. This is the mathematical punchline, and of course the physics is a 3D Toda theory being equivalent to 2D A sigma model. Okay, so this talk is based on a piece of work with my postdoc and student, and it's we're hoping to get it out on the archive next week. Yeah, so it's of the same title as the talk. So 4D Chern-Simons theory as a 3D Toda theory and a 3D 2D correspondence. Okay, so let's get to the talk proper. I mean, so the main body of the talk. And let's discuss this topological holomorphic GL twist of 5D maximally supersymmetric Yang-Mills theory. So if you look at 5-dimensional maximally supersymmetric Yang-Mills theory, involves fields which transform as rep SO5. So we are working Euclidean signature. So that's why we are replacing the Lorentz group with an SO5 group. And then with the R-symmetry group, which is SO5 too, R-symmetry group. And so you have the gauge fields, the 5 gauge fields that transform in the 5 of the Lorentz or the space-time group. And then you have these scalar fields here, which transform in the 5 of the R-symmetry group. And of course, you have 16 supercharges for n equals to 2 in 5 dimensions. And we have spinors which transform in the 4 and 4 of SO5 cross SO5R. So of course, we can understand this from string theory. I mean, this is just the world volume theory of a D4 brane. And there are, of course, a D4 brane is half BPS, and then we will get 16 supercharges in the world volume coming, which is preserved from the background of 32 supercharges in type 2A string theory. And we have these 5 scalar fields that determine the 5 spatial directions orthogonal to the D4 brane in 10-dimensional space-time type 2A string theory. Okay, so it's a very nice action. We have studied this many times, and it looks very nice and neat like this. So for simplicity and for general, to say very concrete results, let's just choose G equals SUN as our gauge group in whatever follows in our discussion. Okay, I'm sure most of you are familiar with the Lagrangian already for 5D Yang-Mills. Okay. Now, so we want to do a partial twist. So what does this mean? So let's take the 5D world volume to be M equals V cross sigma. V is a 3-manifold, right? And sigma is a Riemann surface. So we want to twist the theory in such a way where it's topological on V. Okay, so we want to have a topological twist of this D4 brane world volume along V. So what is the usual prescription of twisting, as elucidated a long time ago by Edward Witten? So this amounts to redefining the space-time group in 3 directions to be a diagonal subgroup between the space-time group and the R-symmetry group. Okay, so schematically it's written like this. So the procedure itself just involves looking out for indices on fields which have R-symmetry indices in the 3 directions, 1, 2, and 3, and replacing them with space-time indices. Okay, so if you look here, the R-symmetry indices are all hatted. They're hatted. Space-time indices are not hatted. So what you're going to do is that if, for example, you look at the 5 scalar fields that we have, which transform in the 5 of the SO5R. Okay, so we're looking at just SO3, so just the 3 of them. So if you unhat them, if you unhat these 3 indices here, so they all become phi1, var phi1, var phi2, var phi3, and you notice that they form a 1 form on V with 3 components. Okay, so that's where you can understand that the theory has been twisted along V in a topological sense. So this twist, and by supersymmetry, I mean, I've skipped some details because of time constraints, but in the past 2 papers, we have shown this very clearly in some of two papers that we wrote on related topics regarding this partial twist in 5 dimensions. So supersymmetry also sort of forces us, when we partially twist in certain directions, to have holomorphic dependence in those other directions. Okay, so that's a constraint, a very nice constraint that comes about from supersymmetry. And also, if you look at the few variations, they don't contain the metric in those 2 directions. So it doesn't depend on the Kähler structure in those 2 directions that are holomorphic. And that's very nice. It allows us to rescale things in those 2 directions also. So what's nice about this, sort of partial twist is that you topologically twist in some directions, it's automatically holomorphic in those other directions. So in this case, 3 directions topological, 2 directions holomorphic. So this twist results in 4 supercharges that are scalar along V. Okay, so we have a choice to look at the different BPS sector of this twisted theory, meaning to look at states which are annihilated by a certain subset of these 4 scalar supercharges that are scalar along V. So they're scalar along V, so the supersymmetries are preserved when you deform V topologically. So we wish to pick a supercharge Q that's a scalar along V. Okay, so which we would like to localize the theory with respect to. Okay, so what this means is, put put the Lagrangian in a Q-exact form, and then looking at the the contributions to supersymmetric or BPS configurations that are given by variations of the fields or supersymmetry variations of the Fermi fields to be 0. Okay, so that's exactly what we're doing. So now we shall choose a certain linear combination of two supercharges to be our Q. Okay, so there are many choices that you can make, but for our purposes of what we want to show, we will be making a certain choice of Q. So let's just say we make the choice of Q using the two supercharges of 4 here, okay, and writing it as a parameter for T here, where T is a parameter that is defined on a sphere valued of parameters, okay, on CB1. In other words, they can be complex, you know. So, but for our purposes later on, we would choose T to be -1. Okay, that will give us the desired models in the lower dimension with which we could get the results that we desire. So generally, so if you consider such a supercharge, then these are the twisted supersymmetry transformations. So essentially, just it's just from the original supersymmetry transformations, and then linear combination of them, and then with the fields that you see here having different spins because of the twist. So some spinor fields become scalars or spin 0, some become spin 1, and then some of the fermionic fields, the scalar fields become spin 1 and all that. So the usual sort of story for twisted theories, but now in 5 dimensions. Okay, so this is just some details here. This twist was first considered. We first studied this twist in detail in this preceding paper of ours here, which we are still thinking about how this all relates to what we're doing right here. But as for now, we just keep it as a discussion to talk about later on. But this is where we first considered this twist in this paper here. So, but such a twist has also been discussed conceptually by Elliott and Pestun in their paper here on Hitchins systems and supersymmetric gauge theory. So the transformations take a form that's very similar to those of the GL twist in n = 4 super Young-Mills, as studied very well by Kapustin and Witten. So in fact, if you take the Riemann surface that we have, in the holomorphic directions to R cross S1 or T2, whereby the X5 direction is S1, and if you dimensionally reduce, on S1 to reduce the 5D maximally supersymmetric Young-Mills theory to n = 4 theory in 4 dimensions, you can see that it will reduce, the transformations will reduce to that of Kapustin and Witten, with the A5 becoming the R5 4 in Kapustin and Witten. So these are fields in Kapustin and Witten. Okay, so most of it is the same terminology, perhaps except for maybe this one over here, I guess. But the point is that it will reduce the Kapustin and Witten's twist and the field variations. Okay, so this is what we mean by a GL twist in 5 dimensions. It reduces to a 4-dimensional GL twist. That twist is topological in all 4 directions. Okay, so in what follows, we shall be interested in our 3-manifold being of this form. V would be an interval cross R plus, so it's a manifold with corners. Okay, and the Riemann surface here, because we want to embed, 4D Chen-Simons theory into our setup, we want it to be either a rational curve, CP1, a cylinder like this, or a torus like this. Okay, which, in the language of 4D Chen-Simons with a lattice would give you integrable systems associated with the Yangian for this one, the quantum affine and the elliptic affine algebra, which has the symmetries of the XXX spin chain, XXY, Z spin chain, XYZ spin chain. Okay. So so of course we could replace sigma with something more general, but that would involve some modifications to how we could define 4D Chen-Simons, the Lagrangian, and so we, just to keep things simple, we'll just consider the case of these 3 possibilities. Okay, and so if you construct this 5D GL twisted theory, that is supersymmetric, and obeys, that's consistent with everything, then you could write it in this form. Okay, so this is the Q that we're using, and just some bunch of fields here which are fermionic. So it's a Q-exact form, and then with this term here, okay, this term here, and when you localize the theory to the Q invariant states, the contributions will be picked up by this term here, and that's how you see that actually this term here actually localizes to a boundary, which actually gives us 4D Chen-Simons. Okay, so that's, I'm just jumping ahead, but just so that you see from the action, you could sort of observe this already. So here our psi tilde is a real parameter. So psi, in the calculations, it's in some expression in terms of t. We have selected t equals to -1 for our purpose of finding the sigma model that we desire. If you choose t to be a different value, you get a different kind of sigma model on the other side of the reduction, as we'll talk about later on. So we have selected t equals to 1. So what this essentially means if we select t equals to -1 is that in this whole family of twisted theories, we're just looking at a specific one particular twisted theory in this family, this continuous family of twisted theories. Okay? So it's extremely rich. Okay, just like the GL twist in 4 dimensions, it's extremely rich. Many more things beyond geometric Langlands can be said in 4D n equals to 4 than just the usual geometric Langlands that we know. So likewise in 5 dimensions, many more things can be said, and we're just looking at t equals to -1 so that we can have a concrete result of something that's very precise. So F here is the curvature of the complex connection involving A alpha. A alpha runs from 1, 2, and 3 in the V direction. Okay, and then which is I cross, it's I, R, and R plus. And then AZ bar, these are directions on sigma. So sigma itself has a Z and Z bar coordinate. Okay, and Z is x4 plus I x5. Okay, and this is the same sign because it's a contravariant vector. So it's the indices are at the bottom. Okay, so and Z and Z bar are local complex coordinates on sigma. Okay, so of course we have boundaries. So we need to specify boundary conditions which are supersymmetric. So we have a few choices. So for our purposes, at the origin of R plus, the first boundary here, if you look, it's a strip here, first boundary here. So we pick an NS5 type boundary condition. Okay, so why we say NS5? So in our previous work, we sort of, we had a configuration of D4 branes ending on NS5. And in this case, we have not talked about it, but we could realize this is what we're studying here in terms of string theory also. So we have a D4 brane that ends on NS5 and we have a D6 brane that's intersecting the NS5. So that, if you do a T duality down, then you would end up getting something like a D3 brane intersecting NS5 and a D5, which is a corner configuration studied by some people, which allowed them to get sort of some W-algebras that are in 2 dimensions. Okay, so that's roughly the inspiration or sort of the guidance that we got to pick NS5 type boundary conditions to maintain supersymmetry. So this translates to the fact that we would have these 2 conditions on the gauge fields. So this alpha tilde runs from 1 to 2, and then Q must annihilate it, so it's invariant under Q, and likewise for Z bar. And of course, being NS5 type boundary condition, the A's obey Neumann boundary conditions. Okay, so it's pretty straightforward. And of course, that's the origin of R plus, but we have to say something about what happens at infinity along the R plus. So the boundary conditions are taken to be at the infinity of R plus, X3 independent. So X3 independent meaning that's the R plus direction. X3 independent Q invariant configurations that involve a alpha tilde and a Z bar. Okay, so the Q invariant configurations, now that's understood. You want to preserve supersymmetries of the boundary. You want the action to be Q invariant. So that's, if you look at the terms that if you potentially give you non-zero Q invariant Q variations, then you want to set them to 0. But about this X3 independence. So the endpoint, or not the endpoint, but we are hoping to embed 4D Chern-Simons into this 5D maximally supersymmetric Young-Mills. And so 4D Chern-Simons, for it to be well defined, as shown by in the previous paper that we worked on geometric Langlands, which is in some sense, a higher dimensional version of what Witten did in trying to find the integration cycle over 3D Chern-Simons so that it converges analytically continued Chern-Simons. So we would need to recast our 5-dimensional theory in terms of a 1D sigma model into the space of fields, and then use the same technology that gave us a left chest symbol, an integration cycle of the path integral of the 4D Chern-Simons. And from that point of view, we needed the world line of the 1D sigma model was along R plus, and there was a requirement of the boundary condition of this sigma model at infinity to be X3 independent. Okay, so this is the origin of the X3 independence. Yeah. Okay, so this is what we have here. So we have talked about the boundaries of R plus. So let's talk about now the boundaries of I, the other 2 corners here. So the boundaries of I, we can have non-pole type boundary conditions. Okay, we could choose other types of boundary conditions which are supersymmetric, but we choose a non-pole because eventually we want a Toda theory. So it is sort of well known by now in lower dimensional examples that if you want to get a Toda kind of theory, we ought to consider a non-pole type kind of boundary condition, and this is what we're going to do. So we'll consider a non-pole type boundary condition on the both ends of I, which are defined in terms of curly A, which is a complex gauge field. So these are valued in the real Lie algebra, but taken together as a complex gauge field, they can represent a gauge connection on a complex gauge bundle. Okay. So, and of course, the gauge fields that we're talking about ought to be Q invariant again, so as to preserve supersymmetry and to preserve the Q invariance of the action. Okay, so we'll talk a bit more about this non-pole boundary condition here. So let's do some relabeling of our coordinates. So x2, x2 is r. Okay, so the second factor in our 5 manifold. So we'll write it as tau. And let's just redefine this convenient coordinates here. So we have this x plus and minus coordinates. And so it's a mix of this r direction and a direction in the sigma. Okay. And so then we can also define with this respect to this convenient redefinition, we can also have this definition of gauge fields. Okay. And then along I itself, the interval, okay, which is given by x1, the first factor in the 5 manifold. Okay, so we call it x1. So we can label it as sigma. And sigma, we can take it to go from 0 to pi. So non-pole type boundary condition, is defined as follows. As you come, to one end of the interval, you have a gauge field that looks like this. Okay, so essentially all components of this gauge field vanish except for the sigma component, the x1 component, and the x plus component. Okay, so the x plus component is here. Okay, so these are the two non-vanishing components if you define a non-pole type boundary condition as you go to the one end of the interval. So this H here is just the Cartan matrix of the Lie group. And then the T plus here is the following matrix here. So it's defined as follows. There's a homomorphism of SU2 into SUN, and it's chosen such that image under this homomorphism of SU2 matrix to SUN matrix, which we call T plus of the raising operator of SU2. So it takes this form. The point is there are these constants inside here, which we label as mu1, mu2, mu_n. Okay, so this is the T plus. This is how it's defined. So analogously, at the other end of the interval where sigma is pi, we also have non-pole boundary conditions. But note that they are slightly different. Okay, so here we have plus components that exist and one component that exists. Here we have the one component that exists and then the minus components, minus component that exists. And the T minus, T subscript minus matrix looks like this, and its values are V. Okay. Now, as I mentioned earlier on, the 5D Yang-Mills twisted action, which has a Q-exact part, and the topological or the FHF part, which is not Q-exact, but nonetheless Q invariant. Okay, after we put in the boundary conditions. Okay, it's Q invariant, right? And then this whole path integral will localize to that term, the non-Q exact term, and which then has a boundary contribution, and that will give us 4D cycles. Okay, so the path integral of this theory localizes the solutions of Q invariant configurations. So we're looking at Q closed but non-Q exact, so Q homology configurations, and then it reduces to the path integral of 4D Simons that looks like this. Okay, so we are looking at, so this is the integration cycle that we're talking about, which makes this 4D Simons well defined. And it's defined by Q invariant localization equations, which we have worked out in detail in our previous paper that I mentioned and cited just now on lattice models, geometric Langlands, and string theory. And so, and if you remember, there was a psi Toda earlier on where we saw in our 5D theory. So it's just being labeled as I over H bar here. So if you look at this, we actually just have one term here. So if someone is careful enough, you would sort of realize that actually we have 3 boundaries, right? We have one at the origin of our plus, okay, 4 in fact, okay. One at the origin of our plus, okay, and then one at the one end of the corner of I, then another one at the corner of the other I, of the other end of I, and then you have another boundary at infinity of our plus. Okay, so what's going on here is that of these 4 contributions, there's only one that survives. The one at infinity just gives us a constant factor in the path integral, so you can take it out as a phase, a constant phase, if you will, and then it doesn't change the dynamics of the theory. So the two contributions coming from the two ends of I, the boundary conditions that we have chosen, set them identity to 0. Okay, so very nicely, we just have one factor here, a single contribution to Fordician Simons from the boundary, from the various boundaries. Only the one at R class, the origin of R class, contributes to the path integral. Okay, so that's what we get here, a very nice result. So this integration cycle is Lefschetz-Tinvaux that ensures the convergence of the path integral. So it essentially, you're integrating over the space of fields that are defined by the Q-invariant localization equations. That's not the entire space, it's just a space which ensures that the exponent behaves in such a way whereby you can integrate it over, it gives you a sensible result and it converges. Okay. So what have we done so far? We have started with 5D maximally supersymmetric Young-Mills on this manifold here. We have done a topological holomorphic twist in the sense that these three directions are topological, these two directions are holomorphic, okay, and recast this Lagrangian here in terms of a scalar supercharge, whereby we want to know the Q, the supersymmetric configurations with respect to this scalar supercharge. In fact, more precisely, we want to look at states or operators which are Q closed but not Q exact, okay, of this theory here. And then we are able to localize, to these, these Q invariant configurations to the to have the contribution coming from the non-Q invariant part that we saw, the FHF part, and then that itself localizes onto the boundary, okay, to give us Fordician Simons, as I've explained in the slide before. And so now we're up to here. Now we want to explain what happens, how we get this guy here. Okay. So three-dimensional Toda theory. So a 3D analog of WZW theory that's dual to Fordician Simons theory can be obtained when the two topological directions of Fordician Simons has a boundary. Okay, so this has been done by Ashwin Kumar, who is also a co-author of this paper. So it's in this paper called Integrable Lattice Models and Holography. So a 3D analog of WZW is dual to Fordician Simons in the bulk. If the topological directions of Fordician Simons has a boundary. Okay, so this is shown quite rigorously here. So something similar can be done in our current setup, where there are now not just one boundary component, but there are two boundaries on the ends of I. Okay, so we have two boundaries on the ends of I, because our Fordician Simons is now defined on this. Okay, and the topological direction we're talking about in Fordician Simons is I cross R. The sigma here in the terminology of Costello, Yamazaki, and Witten is the spectral curve. So we are topological in these two directions where you're supposed to put a lattice. Okay, so we are not considering lattices in I cross R now. Future work, we could consider lattices that would introduce some singularities into the modular space, Bogomolny moduli space. So, but we are just considering the very simple case of no lattice here. And so we have, so a boundary on I cross R, which is the topological direction of Fordician Simons. And so we can have something similar as what was done by Ashwin Kumar in this case here with WZW. So let us focus on the boundary at sigma going to 0, so one end of I. Similar arguments can be applied to the other interval where sigma goes to pi. Okay, so via the boundary condition of A minus equals to 0. So if you look at the numpole boundary condition, as I mentioned earlier on, at sigma tending to 0, the rest of the components of the gauge field vanish except for the x1 component and then the plus component. So naturally, this means that the A minus component is 0. Okay, and if you substitute this boundary condition to the Fordician Simons at the ends of the interval, one end, then you realize that you can compute Fordician Simons to be 3D WZW. Okay, it's a 3D WZW because if you look at this form here, it looks exactly like two-dimensional WZW, just that the measure is three-dimensional. Okay, so the measure is three-dimensional. Again, you have this z coordinate here that's along sigma here, and then you have a mixed coordinate between r and sigma here. Okay, and then you have this topological term in WZW that's one dimension higher. So it's basically a four form, right? Here, it's topological. Yes. Okay. Sorry, am I out of time? Yeah. Right.
You have 5 more minutes.
Oh, 5 minutes. Okay, fine. So okay, so we can compute the currents of this WZW model. Okay, likewise, if you look at what happens, at the end, the other end, you also can compute the currents. These are the conserved currents. Okay, you can rewrite. So for convenience, we rewrite the conserved currents into a Cartan decomposition of conserved currents. Okay, mind you that this G now we are talking about is a complex gauge group already because it descends from this curly A, which can be interpreted as complex gauge field. Okay, so because it's complex, we can do a Cartan decomposition of the J's, all right, into the the upper triangular nilpotent subgroup, the lower triangular nilpotent subgroup, the Cartan subgroup. Okay, and then if you add in the rest of the non-pole boundary conditions, we get these conditions on the fields here. And so you can see that U, mu's, and the V's come in because the Ti's, the T plus and T minuses contain the mu's, and the T minuses contain, the T minus matrix contains the V. So you get these things here. And next we can use a Gauss decomposition of the G field in this manner, which then if you substitute this G into the expressions for J here, which contains the G's here, and then you would get this constraint. Now, this is exactly what is happening, sort of is completely analogous to what happens in 2 dimensions using a Gauss decomposition, non-pole boundary conditions on WZW, and then you get this constraint here. Now, if you look at this constraint, this implies that the action of a theory which gives us this constraint is essentially this one. All right, so the corresponding action that gives us these constraints as an equation of motion takes the form of a 3D analog of 2D analytically continued Toda theory. So it looks like this. If you do a variation equations of motion for this action here, we will get this constraint, right? So this implies that if you have non-pole boundary conditions on the 2 ends, we end up getting a 3D Toda theory. Okay, so what I didn't mention here, which was a subtlety, is we have 2 copies, on 2 ends, okay, which gives us a pair of constraints. And these pair of constraints must conspire, to give us this final result, which we can deduce to be 3D Toda theory when we shrink down the interval. Okay, so that's the important part. We need 2 ends to give us, a pair of constraints that will then eventually lead us to this when we shrink the interval down. Okay. So, and from this 3D Toda theory, we would be able to get, 3D W-algebras in the following sense. Okay, so we could rewrite the Cartan matrix here, the inverse of it as gamma I. And then you can see that this 3D Toda Lagrangian, this 3D Toda theory is invariant under coordinate transformations and transformations of II. So as with Liouville theory and Toda theory in 2 dimensions, you have this extra term here because of the exponent in the Lagrangian. And then you can compute the noether current, of this 3-dimensional Toda theory. It takes this form, it's conserved, and it doesn't depend on the x minus directions. Okay, so so what we're going to show now is that you have a W-algebra, a 3-dimensional W-algebra coming up from this 3-dimensional Toda theory. So let's just go to the simplest case of G equals SL2C, where the Cartan matrix is just a 1-by-1 matrix, and the value is 2. Okay, and then we choose x minus to be a temporal direction, and write x plus to be zeta. And then, we could use an equivalent gauge 3D WZW model. This equivalent model is actually a 3-dimensional version of the Greenfeld-Sokolov reduction in 2 dimensions. Where you gauge a WZW model, you can get, a stress tensor for the Toda theory. So it's the same thing here. So we can rewrite theta as T minus del J. This part comes about because you're gauging it. And if you look at this T, it looks like a regular stress tensor of WZW model, which comes from a Sugawara construction of stress tensors or higher spin stress tensors that come from just contracting the currents. Okay, so and then we can derive the symplectic form on the phase space of this model and compute the Poisson brackets of the commutators between the stress tensor. Yeah,
Please.
Okay, right. Okay, and you quantize it. Okay, using Moya quantization as shown here, and then you can see you can get this structure here. And so this is a 3D analog of the quantum Virasoro algebra. So we can do this for higher spins by adding more J's into it using the Sugawara construction. And in this way, we will be able to get 3D W-algebras from 3D Toda theory. Okay, and so you can see that it has a holomorphic dependence on sigma here, the Z. And then at the same time, there is this factor here that appears. It's very interesting. You have a singularity along the spectral curve plane. And the origins of such a factor can be attributed to the fact that you are coming from a boundary theory of a 4D Chern-Simons theory as holomorphic along sigma. Okay. If we choose x plus to be the temporal direction, you get another copy. So it means that this choice of the temporal direction, is you're free to choose x minus or x plus, you still get the same thing. So that's nice. So we have found this part here. So in the few seconds that I have left, I guess, I'll explain how we get this. Okay, so how we get a sigma model. So okay, so we are, as I mentioned, we are topological in these 3 directions in the 5D theory and holomorphic in this. So what we could do is to essentially scale down this direction here, okay, by scale invariance, and then while blowing up I cross R plus. Okay, so when we do that, we end up getting a 2D sigma model, on I cross R plus, and as I mentioned earlier on in the talk, in the beginning of the talk, that if you look at the terms that you, if you want action to remain finite, there's some conditions on the fields, and these are the conditions. These conditions are actually nothing but the Bogomolny equations on R cross sigma. Okay, and then from the resulting action itself in 2 dimensions now, because you're scaling down metrics in 3 directions, you will see that, you know, accompanying the del phi term that comes from FR star F term of the 5-dimensional theory is this the target space metric, okay, of the sigma model. Okay, it looks like this. Okay, and this is the metric on the modular space of Bogomolny equations. And then you also have a syntactic structure that accompanies the A model as a pullback of the worldsheet of I cross R plus. And then we know from the fact that we have used t equals to -1 and also the expression for W here, omega here, that we have an A model in complex structure K. Okay, because the Bogomolny moduli space is hyperkähler, it has I, J, K complex structures, then you can have A models in different kinds of complex structure. And in this case, we have A model in K. And so what happens is that, you know, we have boundary conditions. We have 2 types, if you remember. So we have the NS5 type boundary condition at the origin of R plus, we have non-pole type boundary condition at the 2 ends of I, and this results in co-isotropic, space-filling co-isotropic A branes on the origin of R plus, and then Lagrangian branes, which are analogs of branes of opus in Hitchin moduli space. They are analogs of branes of opus in Hitchin space on the 2 ends of I. Okay, so we end up having a sigma model that looks like this. Okay, and what we're going to do, since the sigma model is topological, is to pinch the corners here like this, such that we have, you know, a configuration that looks like 3 strings coming in the vertex. Okay, so for us to compute the physical states of our sigma model would be to compute the physical states of these 3 different strings. Okay, so if you compute just the physical states of the string here, the B over prime string, then you realize that, you know, the Lagrangian branes of B over prime only intersect at a point, so they just give you 1 state and the physical states, the Q cohomology states, actually ground states, and they just give 1 state. Okay, but to find more states, you have to consider the states of. Okay, so right. Okay, I'm sorry. Maybe just half a minute. Is that okay? Just so I can finish up. Yeah. All right. Thanks. Okay. So yeah. So you want to compute more states from the other strings here, and the other strings give us states that look like this. Okay, they are holomorphic sections of the canonical line bundle on the this Bogomolny moduli space. Okay, so on the branes on the Bogomolny moduli space. Okay, so. And so we want to understand, okay, so these states, we want to understand what these states are. So these states are states of strings that are BO per BC strings, right? And if you add them with BC strings, okay, you can see they are module for BC strings. But the algebra of BC strings are just the quantized algebra of holomorphic functions on the Bogomolny space. Therefore, the space of states that we are looking at, you know, from the A model, they are modules for the quantized algebra of holomorphic functions on MB. Okay, so in effect, by, you know, 2, you know, equivalent reductions, you know, that do not change the Q cohomology of the master theory, we have a 3D Toda theory on R cross sigma on one side and a 2D A model on the other side. And then, so if we are comparing the states of what we are getting on one side and the other side, you get modules of 3D algebra defined on this being, you know, equivalent to, you know, these holomorphic sections that are the states of these open strings between B over branes and BC branes. And then, so, and we know, as we have shown, that these states here are modules for the quantized algebra of J-holomorphic functions, which then means that modules of 3D W-algebra are also modules for the quantized algebra of J-holomorphic functions on MB. Okay, so to conclude, we have shown that 3D Toda theory and 2D A model on Bogomolny moduli space are dual to each other. We have found that modules of 3D W-algebra are modules for quantized algebras of holomorphic functions on the Bogomolny moduli space. Now, the crucial ingredient is the fact that we have a 5D n equals to 2 supersymmetric Yang-Mills theory, which admits a partial twist that is topological holomorphic and analogous to the GL twist of 4D n equals to 4 super Yang-Mills. Now, so in future work, what we want to do is to talk about a GL twist for a high dimensional supersymmetric Yang-Mills theory, like 6D maybe, n equals to 1, 160, and then we do a partial twist. In this case, in 6 dimensions, the number of directions that you can have to be topological becomes even less now. So instead of just 3 directions being topological, we can only have 2 directions which are topological. Then you have 4 directions or 2 planes which are holomorphic in this case. And we are expecting to get something like a 4D kind of 4D analog of Toda theory, which gives us 4D W-algebras. And instead of Bogomolny equations, just like from Hitchens we get the Bogomolny equations, we are expecting to get quantized algebra of holomorphic functions on the moduli space of instantons. So there's something which we want to investigate in future. Okay, thank you for your attention. I'm sorry I exceeded the time. Thanks for your patience.
Thank you very much. Maybe we can all unmute and start with the speaker.
Do I still share my screen?
So we'll start with Edward Witten. Please unmute.
Yeah, I have more comment than a question. So there's a puzzle to me about Costello's 4D Chern-Simons theory. If you look at it non-perturbatively, the R matrix has poles, which aren't quite where you'd expect them to be classically. They're shifted from there by an amount of order h bar. And in perturbation theory, you don't really see this. You can see higher order poles, order by order perturbation theory. The position of the poles isn't shifted, but their order is increased. But non-perturbatively, definitely, the position of the poles is shifted. And this is an effect that one should try to understand in a non-perturbative theory, although you can't really understand it in a perturbative theory. I'm kind of puzzled about how it is, so I can't say more than that.
Please unmute. You're on mute, next one.
Right, sorry. Okay. Sorry, guys, meant. Yeah, so, okay. So, so that would, for us to sort of think about this a little bit deeper, we would need to generalize what we have here to include Wilson lines in the, and the lattice in 4D Chern-Simons. And in this case here, we are just studying for 4D Chern-Simons without a lattice. Yeah, so we are not putting operators inside. Yeah.
You can treat the Wilson lines just as observables.
Oh, yeah.
So
Okay.
you literally can just put them in the boundary and do exactly the same thing. So your setup is adequate to ask the question.
Okay.
I don't know what the answer is.
Okay. Okay, we'll think about it.
Kumran Vafa?
Yes, thank you. Nice talk. I have a question about the, as you mentioned in the AGT correspondence, you get a map from a Riemann surface to the Toda theory on it when you want to compute the partition functions in the 4D theory. So it's natural to ask whether in your case, if you do the same thing on a 3 dimensions, whether your 3D Toda has anything to do with the partition function of the corresponding 3D theory, is it?
The corresponding partition function of a 3D. Okay, so the point is this: the sort of the generalization of AGT in our case. So we were sort of inspired to find, in some sense, a generalization of the AGT result by Nekrasov and Witten, which relates Hitchens moduli space with the W-algebras in 2 dimensions. So ours is, in some sense, a higher dimensional version of that. But it's not clear to us right now at this point how we could sort of view this result as a higher dimensional generalization of the AGT. So in terms of the partition function, if you are asking, the things that we can say concretely are just partition function of, let's say, the 2D model, the 5D model itself, and the 3D Toda theory itself. So that's all we can say. But I think you're asking about something different.
Well, I'm saying that if I'm just pushing your analogy. If your analogy was the AGT gives you to the Toda theory, and if you repeat the same thing with one higher dimension, and the right answer you get 3D Toda, what are you answering? You're answering a 3D Toda.
So
twist of
right.
That.
So there's no omega deformation in this case of the 5D theory. So I mean, if you look at AGT, it's 4D n equals to 2 with omega deformation. So we are 5 dimensions. One dimension higher, we have more supersymmetries. We're not looking at 5D n equals to 1. So if you look at AGT, the 4D theory that you're studying starts with 5D n equals to 1, and then you sort of do the omega deformation you compactify it on a circle, and then you talk about planes that go around the circle and picking up a rotation. and that starts with 5D n equals to 1. So it's not exactly the same. So I can't really say something concrete of how it would be for a 5-dimensional n equals to 1 AGT partition function, if you will. I think maybe that was your question.
No, I'm not asking 5D partition. No, I'm not asking that. I'm starting from 6D and going to 3D.
Oh, 6D going to 3D. So your 6D is what 6D theory you're talking about? 2, 0 or the 1, 1?
2, 0. AD 2, 0 theory on a three-dimensional manifold, just like the AGT was 2, 0 AD
So
theory on surface.
So
And
if you
that's
start,
the AD Toda.
okay, so if you start with 2, 0 and you compactify in 3 directions, you could get 3-dimensional Chern-Simons, or you could get 3D n equals to 2 superconformal field theory, depending on how you compactify it.
Yes. And the question is, what's the partition function of that in terms of it? Is this related to some Toda theory on the intermediate manifold?
Okay, let me think about it. So we would have to add a circle to 5D n equals to 2 from where we started. And if you compactify it in 3 directions, it's the same as like going down to our 3D Toda theory. Yeah, perhaps, possibly. Yes, yep, that's right. It's possible. So you could compute. Yeah, you're right. So we could compute, if we add a circle to our 5D n equals to 2 partially twisted theory, that gives us some connection to 2, 0. And then if we compactify 3 directions from there, which is the same as compactifying 2 directions like what we're doing now to the 3D Toda theory from 5D, yeah, you could. There could be some relationship to that. That's right. Yeah.
Okay, thank you.
Yeah.
I don't see any more hands, but there is a question in the chat. Nathan Steinberg asks, is it important that the theory is not renormalizable? It cannot even be embedded in UV in a 5D SCFT. Do you have any comments on that?
This theory is not reliable. Yeah, it can be embedded into 2, 0, basically. Yeah, so we can look at it as 2, 0 on a circle, and then you get 5D n equals to 2. Yeah, so from that point of view, it's okay.
All right, if there are no further questions, let's thank the speaker again.
Thank you.
And we'll resume at 3 o'clock local time, so 6 minutes for the next speaker.
How are things over there in Princeton, Edward? Everything's okay? Good. I can't hear you. You're on mute. They muted you again.
Yeah, we're okay, and I hope everything's well where you are.
Right. How's the COVID situation in Princeton? I mean, is it getting better?
It's gotten better in New Jersey. We're a little tired of being stuck at home like everybody else. I want to take a short break before the next lecture, though. So thank you for your time.
All right. I'll see you around. Bye.
Hi, Kevin. You're now co-host.
Okay, can I share my screen?
You should be able to, yes.
Okay.
Correct.
So I think there might be a bug with the version of Zoom I'm using, that you can't actually see me. Is that right?
That's correct.
Okay, so I am going to bring up a little video of myself. There.
Okay.
Is that visible?
Now you are, yes.
Okay, and the text readable and everything?
It is. Your video is overlapping with some of the text at the bottom of the screen, but otherwise.
Yeah, I don't know how to avoid that. What if I?
Now you're just sideways in the same picture. Wait, that's better. Something's happening. Yeah, that seems to be better. And if you scroll, good. So I think if you leave it at the bottom corner and just scroll through, should be fine.
Okay. So now I can't actually see myself because the orientation of the camera. No, that's not going to work. I think this might be the best I can do.
That's probably fine. If you can scroll through it, then it's fine. I think it's.
Yeah, I can scroll through it. Yeah, I just didn't want to.
Yeah, no, I think
didn't
that's
want
fine.
to Small. I can't quite tell how this appears in everybody else's screen. You see.
So Kevin, I'm the session chair. I'll give you a 5-minute warning and 1-minute warning. Is that okay?
Okay.
Okay, so it's 3 o'clock local time. Let's get started. The second speaker of the session is Kevin Costello from the Perimeter Institute. He'll tell us about 3D n equals 2 chiral algebras and dualities. Kevin, please.
Okay, thank you very much. So I'm going to talk about some work I've been doing the past couple of years with. I suppose it started with work paper we wrote with Mina, Jake McNamara, and Cameron, and more recently we have a recent paper with Tudor and Davide, and I have some other earlier work with Davide and Thomas Kreutzig. And it's about the chiral algebras related to 3D n equals 2 theories, and also a little bit about 3D n equals 4 theories as well. So we've seen a few talks about 3D n equals 2 and n equals 4 theories in this conference, and we know that they play a very important role in both math and physics. So one way they do so is you take a 3D n equals 2 theory and you put it on a circle. Of course, you get the two-dimensional 2,2 model. So you would expect that the 3D n equals 2 theory knows about quantum K theory. So if I have a gauge group G and matter V, I should 3D n equals 2 theory should know about quantum K theory of the quotient stack. This was studied by, amongst others, Jockers and Meyer. There are many rich dualities for 3D n equals 2 theories. Well, if I take an n equals 4 theory and view it as n equals 2, the 3D mirror symmetry of 3D n equals 4 theories, when I view it as just with the n equals 2 supersymmetry algebra, this is related to how a Kunkov is studying 3D mirror symmetry, Kunkov and his collaborators. Because in a Kunkov's approach, 3D mirror symmetry is a duality which interchanges quantum K theory on both sides. And of course, we've seen that 3D n equals 2 theories can be engineered from M5 branes. So there's a very rich, complicated, and beautiful story, which I don't know very well, and I won't say anything about. So what I found like slightly unsatisfying about the literature on 3D n equals 2 theories is that most computations or most dualities people study, they check them by looking at the index, which is the character of the space of supersymmetric local operators. So there's, of course, there's been lots of beautiful and difficult work studying the index, which I obviously can't summarize here. But what I would like to be able to do is to lift this to something a little more like homological mirror symmetry, where instead of studying the index, we're going to study the underlying algebraic structure. So this will be the bulk operators, which are supersymmetric. This will be some algebra whose character will give you the index, and similarly a boundary algebra. And I'd like to be able to define and compute these algebras and verify that the dualities you're interested in hold at the level of these algebras. So this was studied in our recent paper with Toda and Davide. And we made some progress, but I think there's a lot of interesting open problems in this vein because, well, as you'll see, we were not actually able to prove that many dualities. We ran into very difficult problems of computing cohomology groups when we tried to prove the more interesting dualities. So what I like to describe is the algebras, as I said, of supersymmetric local operators, mostly in the boundary, but with some information about the bulk. And then to formulate in this language some 3D n equals 2 dualities and to explain in simple cases how we can actually prove them at the level of the algebra. So the starting point is, of course, we're going to be studying the supersymmetric localization. So what I mean by this is we take the physical theory and we add to the BRST operator a nilpotent supercharged Q. Once we do this, this procedure will give us what I will call, for the purposes of this talk, the twisted theory. So I'm emphasizing adding this nilpotent supercharge rather than changing the spins of the fields. And this twisted theory was studied by so we study this. Sorry about that. So we studied this in this paper with Mina, Jake McNamara, and Cameron Vaffa. We wrote down a Lagrangian describing the twisted theory. So one important point is that there is not a topological twist. In the twisted theory, the stress energy tensor is not zero. It has a z component, as a single component. So another way to say that is if I take an operator in the twisted theory, it will be independent of time and be holomorphic in space, but it will not be killed by d by dz. Similarly, if we're going to study the boundary, the operators will be holomorphic functions of z bar. So on the boundary, it looks a little bit like a chiral algebra already. Okay, so we can ask what? So we have this collection of operators, which are, if they're independent of time and are holomorphic functions of z, what algebraic structure will they have? So if I was thinking about describing this in the physical language, more physics point of view, so on the bulk, I would say it's a Poisson vertex algebra, or the Poisson bracket is of degree -1. This was studied in a recent paper of Owen Yagi. Let me, this other thing up here, which is supposed to explain this. So the way this arises is by descent. If I have two operators, O and O prime, I take the descendant of O prime, which is here. The descendant of O prime, it's a one form with dz bar and dt components. And well, if you're familiar with descent, you know that Q of OZ bar is the z bar derivative of O. So this is the kind of this off shell. And the shifted Poisson bracket is defined by this formula. I integrate an operator at 0 against its descendant along the T-sphere. Because I'm descending, that's why I get this shift by 1. If I was thinking of this in more mathematical terms, I would say it's an E1 chiral algebra. It's like a vertex algebra with a compatible associative bracket, associative product, in which case the Poisson vertex algebra would arise by thinking about an Ekman-Hilton argument, the compatibility. Now, on the boundary, well, we simply have a vertex algebra. But it's very important that this vertex algebra does not have a stress tensor. The reason is there's a stress tensor in the bulk, but if I differentiate an operator in the boundary, that's not realized by a contour integral around that operator. It's realized by an integral around a hemisphere of the bulk stress tensor, or rather the descendant of the bulk stress tensor. So these vertex algebras are not, they're very, very, very different from the ones we're most familiar with, like rational conformal field theory. Okay, so it's kind of clear what the algebraic structure will be. So let's see what the main difficulty is. So the main problem is three-dimensional theories have monopole operators. So this is a local operator which sources a gauge field which has charge on the T-sphere surrounding that point. So it's going to be very difficult to figure out how to define the algebra of monopole operators. For n=4 theories, when we introduced the topological twist, this problem was solved in this great work of Braverman, Finkelberg, and Nakajima. So what they did was they introduced an infinite dimensional algebraic variety, and they said that the space of the algebra of monopole operators is the homology of the space. They called it the space of triples. And that the product on the algebra of monopoles, not just the algebra of operators in the twisted 3D n=4 theory, the product is just given by some convolution of this infinite dimensional algebraic variety. Let me bring up an interlight again. So there's, they didn't write it in this way, but their construction is a very physical interpretation. So if I study the space of solutions to the equations of motion on a cylinder like this with a point removed, it looks like their space of triples. Modulo group, the group of gauge transformations on one of the disks. What's the point on the space of triples is like it's a G bundle with a section here, a G bundle with a section there, and as I move along, I get an isomorphism which has a pole at the origin. So just by studying geometric quantization around a sphere surrounding my place I want to put the operator, you're led immediately to their construction. So we can try to do the same thing for n=2. But, well, the reason we found homology in their construction is when I reduce along that sphere, I found some quantum mechanical system with an infinite dimensional space of fields. And there was enough supersymmetry so that the twist gave me homology, as is familiar from twisted quantum mechanics. But for n=2, that is not what we find. We find just the Dolbeau homology, a coherent homology, not the Durand homology. So this is much more complicated. It's a much more infinite dimensional space. So I don't want, you shouldn't be confused by the word coherent homology. It's just the linear dual of cohomology. And we should think about this space as some space of distributions on an infinite dimensional variety. So this is in contrast to the work of Bravo and Finkelberg and Nakajima, where the space was some space of cycles on an infinite dimensional variety. So the difficulty is, well, maybe we can define the space of distributions, but I find it extremely difficult to figure out how to define the product of it. This could just be a personal failing. There is this school of people, for instance, Gates Gary and Sam Raskin, who are great expertise in infinite dimensional algebraic geometry, and maybe they have the techniques to do it, but it seems very difficult to me. But if we could do this, the answer, what we would find would be very interesting. Suppose I take an n equals 4 theory, and I view it as n equals 2. That is, I take this n equals 2 twist. And suppose I was able to define the bulk operators, and I take its spectrum. The kind of thing you might find is one part of it should look like the infinite jets on the shifted tangent bundle of the Higgs branch, and another part of it should look like the infinite jets on the shifted tangent bundle of the Coulomb. So it's something that you should know, about the Higgs and Coulomb branches of the n equals 4. But there might also be mixed branches. So as we go on, I'm going to see another way to approach defining this algebra, which works sometimes. Now, in the n equals 4 case, once I pass to the n equals 2 twist, I have two more supersymmetries, which will localize me to either the Higgs or Coulomb branch. So in the n equals 4 case, well, whatever we should find here is some very rich algebra, which knows about the Bravo and Finkelberg Nakajima construction. Okay, so far, I've been kind of explaining things I don't really know how to do. But it turns out if we study the algebra of operators in the boundary, we can do a lot better. And in some cases, understanding the boundary algebra is enough to reconstruct the bulk algebra. Let me say what the data of the n equals 2 theory is. We have a group, a representation of the group, and a G-invariant superpotential, Manager and Simon's law. There might be more complicated things. For instance, in some situations, the superpotential will depend on monopole operators. But let's not include those for now. So to this data and a choice of boundary condition, we're going to produce a vertex algebra. So let's start by assuming we just have matter, that we just have the simplest thing is one free chiral. So then there's two choices of boundary condition. With Neumann boundary condition, I have a bosonic field on the boundary, but it has trivial OBE with itself. The reason is this bosonic operator can be extended into the bulk, which prevents the possibility of finding any singularities in the OBE. And similarly, with Dirichlet boundary conditions, I have a single fermionic field, but again, trivial OBE. And it's important to note that with the natural spin, this fermionic field here is spin 1. So that more generally, suppose I have some number k of chiral fields with some superpotential, and I give some of them Neumann and some of them Dirichlet. And let us assume that the superpotential vanishes on the boundary. That is, if I set to 0 those fields which have Dirichlet boundary condition, their superpotential becomes 0. So then I have on the boundary, I have some bosonic fields coming from those fields which have Neumann, and some fermionic fields coming from those fields which have Dirichlet. And we have the following formula for the boundary BRST operator and for the boundary OBEs. U of psi is the derivative of the superpotential, and the OBE of 2 psi's is the second derivative of the superpotential. Now, in principle, if somebody could pin down what an A infinity vertex algebra was, you could imagine this pattern continuing and giving you the higher products in terms of the higher derivatives. I don't really have a good understanding of that, though. Another case you might consider is if all of your boundary conditions are Neumann, well, then the superpotential will not vanish on the boundary, that's 0. And we have an anomaly. So to cancel this anomaly, just like in the 2D B model with this potential, we need to choose a matrix factorization. But here it's a chiral matrix factorization. So in the literature with 3D n equals 2 theories, normally people describe this in terms of coupling, E and J terms coupling to boundary Fermi multiply. But in this context, it's really quite general. I can take any chiral algebra and any fermionic element of my chiral algebra to join these commuting bosonic fields. And I want the singular term of the OPE of this fermionic element with itself to be the superpotential. Then I can add this the integral beta to Q, and then that will cancel, Let's look at a simple example. Suppose I take a single chiral with superpotential W equals x squared. And if I take Dirichlet boundary conditions, the boundary algebra is simply one free fermion. Because if I look back a little bit, the OPE was psi times psi is the second derivative. The second derivative of this guy will give you the usual OPE of one free fermion. And in this case, because of the presence of the superpotential, it's natural to change the spin of the bulk field so that the split fermion ends up having spin a half. Here's another example which will be important for us. We take the XYZ model. So I have 3 chirals, the superpotential is XYZ, and I want to give them Neumann Dirichlet boundary conditions. Now there were 2, the superpotential contributed to the BRST operator and also the OBE. Well, the first derivative of the superpotential vanishes in the boundary, so that doesn't contribute to the. So we get no change of the BRST operator. We do get this kind of funny OBE, where my 2 fermionic operators, which come from the Dirichlet boundary condition, the OPE is my bosonic operator. So this will be important later, because I want to check in a little bit the dual of this boundary condition gives you the same chiral algebra. So the dual of the XYZ model is FQED. That is, it's a U1 gauge theory with no Chern-Simons level and a single chiral. What is a single chiral problem? Sorry, 2 chirals. So to do that, we need to understand something about gauge theories. Now, for gauge theories, if I was to choose Dirichlet boundary conditions, the problem we ran into earlier arises that there are boundary monopoles. It turns out that for technical reasons, we kind of understand boundary monopoles a little bit better than bulk monopoles. But in any case, let's work in a setting where there are no boundary monopoles by assuming we have Neumann boundary conditions for the gauge field. And then we'll choose boundary conditions for the matter so that there's no anomaly. We might be forced to add on some boundary fermions or something like that, depending on the Chern-Simons level. Then whatever we get for the matter, I'm going to call C. So this includes the contribution of the bulk matter, together with any boundary fields we need to add on, either for a matrix factorization or to cancel a Chern-Simons anomaly. So for the full system, for the gauge theory with matter, the answer is very simple. All we do is we take C and we adjoin the C ghost. So I'll clarify this a little more carefully with this in a second. But it is very important that this is not BRST reduction, that we do not have a B ghost. There is also no current. There's no particular reason the action of the gauge group on C arises from a current, from a boundary current. It arises from a bulk current. In any case, it doesn't make sense to adjoin the C ghost and write down the familiar formula for the BRST operator. Normally, we would write Q of an operator in terms of the integral of the current. So here, I don't want to do that. I'm just here writing Q of the operator is given by how it transforms under the action of this Lie algebra of arcs in G, which is the boundary gauge symmetry on a small disk. Now, from a math point of view, this construction is extremely simple. All we're doing is we're taking whatever boundary algebra I had and taking the derived invariance with respect to what's called G of O, which is another name for another name for G of Z. So let's see how this works for SQED. Oh, actually, one more point. So in what follows, it's extremely important that, well, I was thinking slightly misleading when we say join the C ghost. So what we have to do is something that I think is well known in some circles. We have to, so the purpose of adjoining ghosts is to impose gauge invariance cohomologically. So for the constant gauge transformations, because that's a reductive group, we should just impose gauge invariance directly for those guys. So that means we shouldn't include the C ghost itself, only its derivatives. That is, we take the algebra containing my C, whatever I get from the matter, I join the derivatives of the C ghost with this BRST operator, and then I take the invariant subalgebra with respect to the global G symmetry. That's all that is encoded in the derived invariance, the G of O, because G of O is a pronilpidant extension of a reductive group. So that's the right thing to do in that context. Let's do an example. Let's do SQED. We take two chirals, and U1 gauge theory with two chirals of charges plus or minus. And we're going to study the boundary conditions, which are Neumann, Neumann, Neumann. So what does that mean? Well, we already saw for the gauge fields, the Neumann boundary condition, we should introduce the C ghost. And for the two chirals, we'll get boundary bosonic fields with trivial B. But to cancel the anomaly, we'll also like to adjoin a complex fermion. So the plus or minus indicates the charges of this fermion under the U1 gauge symmetry. Charge 1, minus 1, and they have the standard OB. So what's the boundary algebra? As we said, we take the matter part, this guy, generated by gamma plus or minus and phi plus or minus. Then I adjoin the derivative of the ghost, and then I take the U1 invariance. Now, one of the basic dualities in three-dimensional n equals 2 theories is between the XYZ model and the SQED model. Now, the boundary version of this was studied in this paper, Dimofte, Gallardo, and Piquet, which I should say was kind of inspires, a lot of what we're trying to do here is to kind of categorify what's in that paper. So they argued that, and they checked at the level of the index, that the XYZ model with the Neumann Dirichlet should be dual to SQED with Neumann, Neumann, Neumann plus these fermions in the band. Okay, so as a first check, so the whole program would be to see if we can find isomorphisms between bulk and boundary algebras under these dualities. So let's check this one. We would expect an isomorphism between the boundary algebra here and the boundary algebra here, and we've described them both. So the theorem is boundary vertex algebras for XYZ and SQED are isomorphic. So let's see how this works. So if you remember, for the XYZ model, because it was a Neumann Dirichlet, the Neumann guy, we had this boundary scalar field, and the two Dirichlet ones give these boundary fermionic fields. And this superpotential gave rise to this OPE, where the two fermionic fields combined to give the bosonic field phi. So as a first check, we'd like to find some operators in the boundary of SQED which satisfy this OPE. Now the operators have to be U1 invariant, and if you think about how what spins things have and how they're so on other symmetries, well, the only reasonable possibilities is psi y and psi z must be sent to these combinations of the boundary fermions. Because remember on SQED, on the boundary I have complex fermion, so fermionic fields of charges 1 minus 1, and I also have these scalar fields, these bosonic fields of charges 1 and minus 1, and I combine them to get fields of charge 0. And the only other field of charge 0 is this one, phi plus phi minus. So in this way, we get a homomorphism, and it is a homomorphism because if I take the OPE between these operators here, the gamma plus and gamma minus will annihilate, give me 1 over z, and that times this operator. So this is indeed a homomorphism. It's very easy to check. Well, we would really like an isomorphism, but that's really not obvious at all, because on the SQED side, we presented the algebra in this BRST way, and there could be all kinds of hierarchical homology. In particular, what we don't see where the derivative of the ghost is. So it could be that on the SQED side, we have an operator del C, which does not appear in the image of the homomorphism for the XYZ algebra. But fortunately, if you carefully calculate the BRST operator, you find Q of the normally ordered product of gamma plus gamma minus is the derivative of the ghost. So it requires some work, but you can convince yourself that all the other cohomology groups vanish, and that this map is in fact maximum. So it's at this point where things become difficult in more general cases. Because you would like to be able to prove the same kind of thing for other dualities, like Roni duality, which this is a special case. And so one example would be, I take SQCD with the NC equals NF. On the other side, the duality, I find a theory without gauge symmetry. So I have an n squared matrix of chirals and 2 other chirals, and then this superpotential. And then Dimofte, Gaiotto, and Piquet argued that there was an equivalence of boundary conditions like this. So what we can show is that there's a homomorphism. Unfortunately, it seems really, really hard to check that it's an isomorphism, because computing the cohomology groups on this side, on the SQCD side, the cohomology seems to be really hard to compute. With one exception, when n is 1, which is the case we already did, or else when n is very, very large. When n is very, very large, it kind of gets boring. But I was able to compute the cohomology when when I take boundary operators, which are written as words which are small compared to n, in which case it works. Okay, so this is Neumann for gauge fields. So to get further, we'd also want to describe all kinds of other boundary conditions. Well, in principle, any other boundary condition should be obtained by coupling appropriate matter to the Neumann boundary condition for gauge fields. We do have a direct description of Dirichlet. So Dirichlet, there are of course boundary monopoles. So what we were able to do is describe the vacuum module on the boundary in terms of the Affan-Grassmannian. So what we found is the boundary vacuum module is the homology, the Affan-Grassmannian, with coefficients in a very big vector bundle, algebraic vector bundle, built from the matter fields and the tautological line model on the Affan-Grassmannian, sorry, the determinant line model on the Affan-Grassmannian tensor to the Chern-Simons slope. Now, for instance, in the case there's no matter, this is a description of the vacuum module for the WCW model, which I think was proved by Sherwin Kumar in the 80s. But in the case there is matter, it's something more general. It seems hard to understand or to compute, but we were able to prove it has the correct index by using localization on the Affan-Grassmannian. Another difficulty we had, we found it a bit hard to show that this vacuum module, to construct the OBE in this vacuum module. So Sam Raskin told us he had some techniques using the Bales and Grinfeld approach to vertex algebras, which would allow him to do that. So I think that can be done. Okay, so I have 5 minutes left. So let me move on a little bit to discussing how one might understand them both, because everything I've said so far was about the boundary of vertex algebra. So in a 2D TFT, people might be familiar with the fact that if you know everything about the boundary, for a nice enough boundary condition, you can recover the bulk algebra as a Hochschild cohomology of the boundary. So this is expected to hold when say the boundary condition you choose is a generator of the category of boundary conditions. So somehow when the boundary condition is big enough. An example, if I took a sigma model, the B-twisted sigma model with targets from Calabi-Yau, my boundary condition was Dirichlet at some point. That the skyscraper sheet for that point doesn't know about the whole Calabi-Yau, so then it wouldn't work. On the other hand, if it was Neumann with coefficients in some vector bundle, then if the vector bundle was sufficiently ample, it would work. So with Davide and Thomas Kreutzig, we were studying whether something similar will hold in this 3D case. So the conjecture, which, as I just pointed out, can't really hold for every boundary condition that's big enough, is that if I take the boundary vertex algebra, then the bulk algebra is the self-X in the category of C modules of the vacuum. So if you think about it a little bit, this is the analog of Hochschild cohomology in the world of vertex algebra. So we propose this for n=4 series. I should point out it's very closely related to something in Shooter's talk, because this category is very closely related to the D modules on the loop group, on the loop space that appeared in Shooter's talk. So one aspect of this I find kind of fascinating is that, well, we did check this in some cases, and we do have a general formal argument for why this could be true, although we don't have a proof in that many cases. But if this is really true, then the vertex algebra knows both the Higgs and Coulomb branch of the n=4 theory, because, as we saw in Tom Yuki's talk, the Higgs branch is the associated variety, and the Coulomb branch is the derived center. Okay, so we would like to extend this to equals 2 from n equals 4. So purely formal reasoning tells us that there must be a homomorphism from the bulk, whatever the bulk algebra is, this self x. Because if I take a bulk operator and I bring it to the boundary like there, that commutes with the OBE of any boundary operator. But it commutes up to coherent homotopy. So that means it's an endomorphism of the vacuum module in the category of C modules up to homotopy. And that's what this space is, it's the derived endomorphisms. So my student Katie Zhang checked that this really holds for n equals 2 theories, which are pure matter. So the point is, in the case of pure matter, there's no bulk monopoles, so we don't run into this issue, and you can just, we know what the bulk algebra is just directly, you know what the boundary algebra is, and we can just compute both sides, and he checked the theology isomorphic. So we'd like to suggest that this is a reasonable definition for gauge theories, where I take Neumann boundary conditions for the gauge field, and then define the boundary algebra as we did above, and then compute the self x of the vacuum module, and this will give us a candidate for the bulk algebra. Well, why is this reasonable? I mean, if we take any gauge theory where the boundary, right, take any gauge theory which is dual to a theory of some chiral with some superpotential, it has to be true. By this argument of Katie Zhang, because it's true for any theory of chirals with any superpotential. So let's look at the XYZ model again, and we'll check, does this really work? They're XYZ and the SQED model. So can you prove that the self x in the XYZ case is indeed the correct bulk operators? You know, there's three bosonic operators, 3 fermionic operators, and some BRST operator, and so on. But now we know that on the boundary, the XYZ boundary algebra is isomorphic to the SQED boundary algebra. So therefore, these things are just the same. If I take the self x of the SQED and the self x of the XYZ, we get the same thing. So that tells us that the self x of the SQED vacuum module is the correct bulk algebra. Now we see something kind of remarkable. Even though on the boundary of the SQED model, it was really perturbative. We didn't insert any non-perturbative operators at all. We found the correct bulk algebra, including the monopole operator. The point is that the monopole operator is one of the 3 fields x, y, and z. I mean, our conventions is x. And if you track through where it comes from x1.
So 1 minute, please.
Okay. So here suggests a general strategy that we can use Neumann boundary conditions to compute the boundary algebra. It's purely perturbative, and then attempt to compute the bulk algebra by using the self x of the vacuum. Okay, so some of these computations get pretty hard, but I think this is a doable thing for abelian gauge theories, and I really want to see how far we can push. Let's see, want to see anything else? Yeah, so one fun generalization is, can you do this in 5 dimensions too for 5d(n = 1? So I did a little computation for 5d(n = 1, where on the boundary algebra with Neumann boundary conditions for the gauge field is a very similar description. And if you compute the self x in a similar way, of course, it's not a vertex algebra anymore because I have 2 holomorphic directions. You do see something which recovers the known index, including incident operators. but only for operators of positive instant top charge. Okay, so let me stop there and I will stop sharing.
So let's take a speaker. So Sergey Guhov, please.
Hi, Kevin. Thank you for wonderful talk. This was very nice. I have a very lowbrow question. In two-dimensional theories with 0-2 supersymmetry, we know that non-perturbative effects can sometimes change perturbative chiral rings, like ecohomology. And this 2D, 3D coupled system is very similar in many ways. So obvious question is, what do we know about non-perturbative effects? And more importantly, under what conditions can we trust the perturbative chiral ring, perturbative boundary?
I see. The only non-perturbative effects I could think of would be like the boundary monopole operators, which I can assume aren't there if I use Norman boundary conditions. Was there another concern you have? I suppose you could have boundary vortex operators if your chirals were periodic. Is that the kind of thing you're thinking about?
Well, in two dimensions with 0-2 supersymmetry, not all of them are well understood, but even in sigma models, there could be such effects. So question is very general, lowbrow question.
Yeah. Okay. I mean, I think I feel fairly confident as long as we just have chirals on flat space with a superpotential, maybe with some homogeneity. I think as long as your chirals are doing something curved, it could get much more complicated. I agree.
Ethan Seiberg.
Yeah, so first of all, a comment. So before that, wonderful talk, thank you. A comment to Sergey. There are many examples of 3D n=2 theories where the chiral ring is modified from the classical answer. In fact, this is a rather common thing, just as it's common in 4 dimensions and in 2 dimensions. But I also have a question for Kevin. There is some insight into these dualities in 3D n=2 is arising from compactification of n=1 in d=4, which is not unlike compactification of 2-0 theory, giving us insight about what happens in lower dimensions after compactification. So my question is, can you get anything by compactifying a 4-dimensional theory on a circle, or maybe more sophisticated compactification, to learn about these 3-dimensional theories?
I find myself really confused by this, and so I did try to think about this, but I got kind of stuck because if we were to apply supersymmetric localization in 4 dimensions with n=1 supersymmetry, there's only enough supersymmetry to make it holomorphic. But then I have no idea. And then if you reduce in a circle, I just have no idea where the monopole operators could come from. Because you can't really have things wrapped in that circle so easily in a holomorphic theory. So yeah.
The general rule is that when you reduce the theory from 4 dimensions to 3 dimensions, you need to add the monopole operator by hand to the 3-dimensional theory in order to get a good duality.
Okay.
Well, the comment you just made really hits the nail on the head because, yeah, for precisely this reason. So the nice dualities in 3 dimensions arise by adding this monopole operator by hand. And in fact, you alluded to that in your talk when you mentioned Aharon's dualities, because they also have the monopole operator in the Lagrangian.
Mm-hmm. Yeah. I feel like I would really like to understand Aharon's argument better, but where those came from. So I think until I do that, I don't think I can really say anything to your question.
Thank you.
Whitmore?
Yeah, when you derive the bulk algebra as a derived center of a vertex operator algebra on the boundary, you're using some category. So first of all, it's the vertex operator algebra does or does not have a stress energy tensor?
Does not.
So I'm not quite sure what category of modules you're using.
Okay, so what you do is you take the mode algebra of the vertex algebra, and that's some giant topological associative algebra, and you just look at modules for that. But probably you want to bound below the space.
Well, yeah, I was wondering if they were bounded below, and well, since there's not a stress energy tensor, I'm not even sure what that means. But
well, it has an action of the conformal symmetry group. It's just not an inner action.
Okay. So is there an L naught?
Everything is charged under L naught, but there's no current giving you that charge on the boundary.
Are your modules bounded below by L naught?
Yes. Yeah, I think the paper with Thomas and Davide, I think we had some discussion about this because there was a disagreement between me and Thomas about the best way to treat this point, which led to different answers in the computations. Like he wanted, I mean, his initial approach was a kind of traditional thing you might do for RCFTs, and then you find you don't get the same answer. You don't get the right bulk answer, I think. I mean, traditionally you might look at like semi-simple modules, and then you don't, and then there's no interesting extension.
This category is a semi-simple category or not?
Absolutely not. No.
Not.
No. Absolutely. The simplest example is just take one free chiral with normal boundary conditions, and then the category is just I take the loop space of C, and it's some kind of category of coherent sheaves on that. And that clearly is not semi-simple because even sheaves on C has x1. So.
I see. Thanks.
Jinbawu?
Okay, in three-dimensional super-tensorial case, I mean three-dimensional equal to supersymmetric tensorial symmetry, there are many non-local operators like bosonic BPS where loops constructed by Gato and Yin, and also formalic one constructed by Ouyang, Zhang, and myself. So where is BPS where loops play some role in your discussion here? Thanks.
The audio wasn't great there, but I think the non-local operators you see would be, well, there's the initial ones you might study would be line defects, which could be vortex lines, Wilson lines.
Yes.
So one thing I kind of skipped over, I was running out of time, is that if you have a nice boundary condition, you might expect, kind of similarly to Tudor's talk, that the category of line defects is the category of modules of the vertex.
Okay, thanks.
I don't see any more questions, so let's thank the speaker again, and we'll pick up at 1600 local time, so in 9 minutes. Hi, Timo. You're muted.
Very good. Hi.
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 So I'll give you a 5-minute warning and a 1-minute warning.
Perfect. Thank you. I've got one question. So I don't anticipate it to happen, but it could happen that my computer erratically switches off. For that case, I have also an iPad with everything uploaded. So I'm logged in twice. Could you maybe also make this one co-host, because then I can switch?
I've already done that. Both your logins are co-host.
That's great. Thank you. So
okay.
If it happens, then I'll just switch to the other machine, and
okay.
I hope it won't happen. Thank you. Good.
Are you at Mainz or are you at Heidelberg?
I'm in Mainz.
It says Heidelberg on the.
Yes, that was a long time ago. That was before, yeah. So I changed to Mainz.
Timo, I recently discovered that Inspire still has you listed at Heidelberg.
Oh, hi, Dave. That's you. Hi,
yeah.
Hi, Dave. Okay.
I was trying to double check because I was pretty sure you had moved to Mainz when I saw this Heidelberg here, and so I went to Inspire and they said Heidelberg.
I see. Thanks.
I don't know how one fixes that, but
probably one can change one's. I don't know.
Something. Yeah.
There's something. Or, okay. Thank you for pointing this out.
Sure.
I'll look into it right after. Good to see you or hear you.
Yeah, it's 6 a.m. here, so I'm not visible.
Oh, good morning.
I'm sorry, 7 a.m., whatever.
Thanks for joining.
Okay, the final speaker of the session is Timo Weigand from the Mainz Institute for Theoretical Physics. He'll tell us about modularity, VPS invariance on elliptic fourfolds and the weak gravity conjecture. Please go ahead.
Yeah, thank you very much. First of all, I'd also like to thank the organizers for making this meeting possible. Of course, like all the other speakers and participants, I'm very sad that we didn't get to enjoy beautiful South Africa this year. But of course, it's great the meeting is taking place in this way. And I'd also like to thank my collaborators for collaboration on the work I'm going to present here, Songju Lee, Wolfgang Lerche, and Guglielmo Lockhart. So the aim of this talk is to understand the modular behavior of elliptic genera of strings as they appear in four-dimensional n=1 theories. And these will be strings whose worldsheet theory has 0,2 supersymmetry. Such strings could be, for example, critical heterotic 0,2 strings of 4 dimensions, but also 4-dimensional non-critical strings. And I hope I'll convince you that this topic is a typical example of the beautiful interplay between mathematics and physics as mediated by string theory, and which is, of course, the topic of this meeting. So on the mathematics side, first of all, we will make contact with the theory of quasi-Jacobi forms. I'll define this later on in the talk, which are also of interest in arithmetics. Then from the physics perspective, we will be using string dualities, including mirror symmetry, to actually compute those elliptic genera. And we will compute them by, in turn, relating them to Gromov-Witten invariance on fourfolds. So unlike the topic of Gromov-Witten invariance on threefolds, which would be relevant for strings in 6 dimensions, this topic has been studied much less, at least in the physics literature. But finally, there will also be a lot of physical conclusions that we can draw. One aspect would be the quantum gravity conjecture, the weak gravity conjecture more precisely, and I will very briefly at the end mention this. So let me give you the main results of the talk in a nutshell. The first point is that we can use mirror symmetry and string dualities to actually compute, to explicitly compute the elliptic genera for strings in 4-dimensional n=1 theories, so with minimal supersymmetry. And this includes, in particular, strings which are non-perturbative, for example, heterotic strings in non-perturbative NS5 brane backgrounds, or non-critical strings. Second, from this computation, we will observe that these 4-dimensional elliptic genera behave very differently from the counterparts of elliptic genera of strings in 6 dimensions. In particular, the elliptic genus is not just a modular form or Jacobi form, as you might expect. It has such a component, but in addition, it includes the derivative of a Jacobi form, in this case of weight -2. And this derivative is something that was surprising to us. It makes contact with known results in the mathematics literature. And it also has important physical implications. I will briefly mention applications of this in the context of anomalies for 4-dimensional n=1 theories, and as said already, for the weak gravity conjecture as one example. So these will be the 3 main points which I would hope you to take away. So the strings that I'm going to discuss are constructed originally on one part of the duality chain, on one side of the duality chain as solitonic strings in 4-dimensional F theory. So 4-dimensional F theory is for us now the laboratory in order to define those strings to begin with. F theory, therefore, as you allow me to quickly review, is a compactification, as you all know, of type 2B string theory with non-perturbative 7 branes. It's compactification where the compactification space, Bn, is non-Calabi-Yau because of the 7 brane back reaction. It's the base of an elliptic fibration, which in turn is Calabi-Yau. And the 7 branes wrap devices on this base, which can be mathematically identified with the discriminant locus of the elliptic fibration. However, in this talk, I'm not going to focus on the 7 brane sector, but on another important sector, the 3 brane sector. More precisely, we are going to consider the 3 branes wrapping a curve on the base of the elliptic fibration. this gives rise to a string in the extended directions. And these are precisely the, in general, solitonic strings that we would like to compute the elliptic genus for. For instance, if we consider compactification to 6 dimensions, so on an F-theory elliptic fibration, which is a threefold with base B2, then those strings have been studied in great detail in the literature, and you're all very well aware of their importance. These are the BPS strings of 6-dimensional n equal 1, 0 supergravity. For example, if the curve wrapped by the D3 branes has negative self-intersection, then these give rise to the non-critical strings, which are an important feature of 6-dimensional SCFTs, which have been discussed already and will be discussed more also tomorrow. And if the self-intersection of the curve is 0 or positive, then we get strings which are not strings of SCFTs, but which are also interesting from the supergravity perspective. For example, if we compactify on an S1, they will correspond to black holes in 5 dimensions. So these strings are very familiar and they have been studied a lot. And we will, of course, build heavily on the insights found in 6 dimensions. So we, by contrast, are going to be concerned with strings in compactifications to 4 dimensions, 4-dimensional n equal 1, so 4 supercharged compactifications of F-theory. Now, this is defined in terms of an elliptic Calabi-Yau fourfold, and the base is a threefold. But still, the strings arise by wrapping a D3 brane on a curve on the base. And the curve on the base will be denoted by C0. Now one can get general information about at least the field content of those strings by reducing the theory on the D3 brane. This is, if we start with a single D3 brane, say this would be U1 n equal 4 super Young Mills, which then has to be reduced. One has to invoke a topological and in fact a duality twisted, topologically and duality twisted reduction because of the variation of the gauge coupling. And in the end, one finds that these strings in their worldsheet theory are a theory of n equals 0,2 supersymmetry. The modes on the string first arise from the sector of dimensional reduction of the Young-Mills fields. But in addition, there's an important extra sector. This arises at the intersection of the curve wrapped by the string and the divisor wrapped by the 7 branes. At this intersection, there are new degrees of freedom, 3, 7 modes. These are charged under the 7-brane gauge group. And this, in fact, shows that the 7-brane gauge symmetry becomes the global symmetry or flavor symmetry of the string because of these charged modes which arise at the intersection. Just as an example, for instance, suppose that the base of the elliptic fibration emits by itself a rational vibration, so a P1 vibration. This would be just an example. So here I'm drawing now not the elliptic vibration, I'm just drawing the base B3 of the elliptic fourfold for a particular type of geometries. Then the rational P1 fiber, the generic fiber, once wrapped by D3 brane gives rise to a string with trivial normal bundle. And it turns out that this string is, of course, precisely a heterotic string. It's the critical 4-dimensional heterotic string of the dual heterotic theory. And one can explicitly see that there's an E8 times E8 or SO32 current algebra on the string because of the extra 3-7 sector. On the other hand, if this C0, if this P1 can split into, say, 2 curves in this fashion here, wrapping a D3 brane on one of these 2 curves gives rise to what one would call a 4-dimensional non-critical E string. So E strings arise in this way in 6 dimensions, as is very well known. And you could view this as the 4-dimensional generalization of the concept of E strings, which have just an E8 current algebra. But these are just 2 examples. In principle, you could imagine wrapping any curve on the base, and you will get a string with 0,2 supersymmetry on its worldsheet. Now, we said that the flavor or the global symmetry group on the string is the gauge group on the 7 branes. And therefore, we do need to spend at least one slide or only one slide on the gauge group on the 7 branes. And for simplicity in this talk, I will focus on models or on situations where the gauge group is as simple as possible, just a U1 factor, just to make things simple. But everything can be generalized to more complicated non-abelian gauge algebras. Therefore, I have to quickly remind you of the geometry that arises here, some aspects we will need. So in order to get a gauge group U1 in F-theory, the elliptic fibration has the following structure, or the genus 1 fibration has the following structure. First of all, it's an elliptic fibration, already said it. So we have a section, a zero section, and we have an additional rational section, another map from the base into the full Calabi-Yau. And the important point is that one considers essentially the difference of the rational section and the zero section. That's called the Toda map. In fact, there should be a minus sign. Take it with a minus sign, everything here. There's a typo, sorry. And this difference of sections, this gives rise to a divisor in the fourfold, and therefore to a U1 gauge symmetry. Why? This is most easily seen if we invoke duality with M theory. If we compactify M theory on the fourfold, then we get the U1 symmetries by expanding the M theory threefold along the divisors. And the particular divisor given here by the Toda map, or the difference of the two sections, this turns out to be the one that gives then rise to a U1 gauge potential also in the F theory. So we have, by an extra section, we have an extra divisor class. Therefore, we also need to have an extra dual curve class. And the extra dual curve class is drawn in this cartoon here. We have an extra class in the fiber. This class in the fiber of the elliptic fibration is intersected by this divisor sigma once. And since the divisor sigma is associated with the U1 charge, we interpret this as counting the divisor sigma is associated with the U1. We interpret this as counting the U1 charge of an M2 brane wrapping this curve. So this is all you need to take out from this. We have gauge group U1 on the 7 branes. This is flavor symmetry group U1 on our strings. And this implies in particular that there's a certain class in the fiber C5 from now on, which is associated with matter charged under the U1. Okay, so this concludes our little crash course on the geometry that we will actually need. And we can now turn to the main point of this talk, namely the definition and then computation of the elliptic genus. So recall we are interested in the elliptic genus of strings obtained by wrapping a D3 brane on a curve on the base, solitonic strings in 4D n equal 1. The elliptic genus, of course, is an object that is well known to all of you. It's essentially a part of the full partition function, or it's the partition function over the subsector with Ramond-Ramond boundary conditions if we wrap the string along a torus. And most importantly, with a -1 to the f, the fermion number inserted. So this is really an index-like partition function. It counts with signs. When we take this trace, of course, as always, we weigh the states with the left and right moving energy along the string. And we also weigh it with all the excitations with the U1 charges. U1, because this is now the flavor symmetry that we're looking at. If we have a more complicated flavor group, then we would have to include all of those if we want an interesting result. So we include a fugacity parameter, Z, and Xi is e to the 2 pi I Z and appears inside the trace. Just like Q is e to the 2 pi I tau, with tau, the complex structure on the worldsheet T2, as always. And let me stress that this refinement is really crucial because, as it turns out, for 4-dimensional elliptic genera in 4D n equal 1 theory, the elliptic genus is 0 if you do not include the refinement. This is just a consequence of the modular properties that we will see. So this elliptic genus, of course, just to finish off the definitions, then is a generating function for the degeneracies of the string excitations, with the understanding that we're in the Ramond sector and have inserted a -1 to the f. So it's an index, essentially. And I'd also like to point out that the object that we will get will in general be meromorphic in Q. Why? Because we have to face a vacuum energy along the string. The vacuum energy can be negative. This is how it is computed, C0.k bar in the worldsheet theory. So we expect something meromorphic for the elliptic genus. Now let us compute it. As I said, there has been already a tremendous literature on elliptic genera of 6-dimensional strings. So let me devote 2 slides to briefly reviewing how we can use, or how these authors here have used dualities in order to compute the elliptic genus of 6-dimensional strings in string M and F theory. So the general idea is that we start with F theory compactified now, as we said, to 6 dimensions, but on an extra S1. And this, of course, is dual to M theory compactified on the Calabi-Yau threefold to 5 dimensions. And in this, an aspect of this duality is that if we consider a BPS string in 6 dimensions, but now wrapped on the S1, this gives rise to a BPS particle in 5 dimensions, of course. To define or to describe the wrapping, we need to specify the wrapping number and the KK momentum along the string. And the corresponding modes map under the duality to particle-like modes, which we identify with M2 branes wrapping this combination of curves, namely wrapping number times the curve C0 on the base, plus KK momentum number N times the full fiber E tau. This blue object here should be the full fiber. And of course, we can invoke a relation between momentum and KK on the one hand and the excitations of the string. And in the sequel, we will set the wrapping number W equal to 1. So we will be talking essentially only about a single string, and then we can essentially identify the excitation level with the KK momentum by this relation. So this is the elliptic genus as we'd like to compute it. And more precisely, the duality states that conjecturally and confirmed in many, many examples, the index-like degeneracies in the elliptic genus should now map to the BPS invariance of the M2 branes, which correspond to the wrapped string states. More precisely, to the 5-dimensional genus 0 BPS invariance associate counting M2 branes wrapping the curve C0 once, because wrapping number is 1, and then N times the full fiber, and R times this extra fibril curve. This is why I had to introduce this extra fibril curve 3 slides ago, because this is the one that keeps information about the charge. So if we look at the degeneracies in charge sector R, this corresponds to BPS invariance counting M2 branes wrapping, in particular, R times the fibril curve C fiber. And furthermore, the last step is that for primitive base curve C0, so if this C0 is not itself the multiple of another curve C0 primed, then these BPS invariants in 5 dimensions, or Cooper-Kummer buffer invariants, they coincide with the Gromov-Witten invariance, and the latter can be computed by a mirror symmetry for threefolds. So the elliptic genus is therefore related to the partition function of the topological string on the threefold. So this is a very beautiful story in 6 dimensions that allows us to actually compute using this chain of dualities, the elliptic genus, and also study, of course, its modular behavior, among other things. Now, what we'd like to do in this talk is apply similar reasoning to elliptic genera of strings in 4 dimensions, in 4-dimensional compactifications of F theory. And of course, the natural assumption or the natural conjecture is that also the 4-dimensional elliptic genus and its degeneracies here can be computed via quote-unquote 3D BPS invariance associated or suitably counting in a suitable manner M2 branes wrapping this curve CNR, which was the same type of curve that also appeared in 6 dimensions. After all, we're just going down further 2 dimensions. So more precisely, the conjecture is that if we consider a string, a solitonic string, wrapping a class in the base, now on the fourfold, so on the base threefold, which is primitive in the sense that it's not the multiple of any other curve class, then these degeneracies that appear in the elliptic genus, they should be the genus 0 Gromov-Witten invariance for type 2a, essentially for the curve C and R given in this fashion. But we have to specify now, and this is now where lots of the meat will be buried. When we talk about genus 0 Gromov-Witten invariance on fourfolds, we have to say that these are computed with respect to a certain choice of flux, certain background flux G. So the degeneracies are related to genus 0, conjecturally related to genus 0 Gromov-Fit invariance on a fourfold in the background of a certain flux. And there are two ways to understand why the flux should play a role. First of all, from the physics side, because if we look at convectification on a fourfold, then it's known that to really define that convectification, we have to choose background flux, both in F theory and in M theory, and then also in type 2A if we go via mirror symmetry. The appearance of the background flux can also be understood just at the mathematical level from looking at how the Gromov-Fit invariants are actually defined. So let me briefly recall this well-known material for you. As you all know, the genus G Gromov-Fit invariants on a general Calabi-Yau K-fold, these count stable holomorphic maps from a Riemann surface of genus G into the target space manifold YK. So the genus G Riemann surface is mapped to some curve class C, say. But in addition to saying that this is a stable holomorphic map, we also have to fix a certain number of points on the Riemann surface. And these maps will be counted subject to a certain incidence relation. In other words, we say that we look at those stable maps such that these n fixed points on the Riemann surface lie within certain cycles in the target space manifold. These are cycles AI. So when we talk about Gromov-Fit invariance, then, as you know, we always have to also specify the number of fixed points and the incidence relations. This is part of the defining data for the Gromov-Fit invariance. Now, the expected or virtual dimensions of those maps, of the moduli space of such maps, is given by this blue formula here. For Calabi-Yau, it's given by dimension of Calabi-Yau minus 3 times 1 minus g, g being the genus of the Riemann surface, plus n, n being the number of fixed points. So, of course, for k equals 3, if we were looking at invariance on a threefold, this would mean that the virtual dimension is 0 plus n, so we don't even have to specify, if we specify 0 points, n equals 0, then the virtual dimension of the moduli space is 0, so this corresponds to isolated points, and this is why we would be counting actually curves, so to speak. But on a fourfold, and this is the difference, now k is 4, so the virtual dimension is 1 plus n, the number of points. So even for n equals 0, we would not get a zero-dimensional object, so we can't associate with this a number of curves naively. Rather, what is natural to consider instead is for g equals 0, to fix 1 point, n equal 1. Then we have a moduli space which has 2 complex dimensions. And in order to get a number out of this, so to speak, we have to integrate a 4 form over this 2 complex dimensional moduli space in very rough terms. So in other words, we have to fix 1 point on the Riemann surface subject to an incidence relation that this point sit on a real 4 cycle on our manifold. And the actual genus 0 invariant is then obtained by essentially pulling back the flux, the 4 form class dual to this 4 cycle, pulling it back onto the moduli space and integrating it over the fundamental class associated with these maps. So therefore, this was just a review of well-known mathematical facts that indeed specifying a 4 form is intrinsic to specifying the genus 0 invariance on Calabi-Yau fourfolds, different from Calabi-Yau threefolds. And the physical interpretation of this 4 form is, as we said already, as the background flux, which appears both in F theory and in M theory. So the proposal would be that we can compute these degeneracies of the 4-dimensional elliptic genus by computing, quote unquote, the 3D BPS invariance. I don't really want to define what this is actually supposed to mean, but in the case of a primitive base curve, I should really be saying here a genus 0 Gromov-Fit invariance. And these in turn can be computed by mirror symmetry. So the elliptic genus therefore can be explicitly computing by using the technology of mirror symmetry on fourfolds. And in this way, one can obtain very concrete results, as I said, even for strings which would be non-perturbatively defined. For example, heterotic string with NS5 branes, as long as it is mapped to good F theory. by a duality. So in order to set up, so that's our next task now. So I hope you're still on this journey. So F theory in fourfold strings. We say elliptic genus of the strings has degeneracies. Degeneracies are computed by genus zero chromophyton invariance on the fourfold in a certain background flux. And these in turn are computed by mirror symmetry for fourfolds. So mirror symmetry for fourfolds is much more complicated than for threefolds. And the reason is, among other things, the appearance of the background flux. The flux in the supersymmetric situation takes values in 2,2, in H2,2 of the fourfold. And this space decomposes into a direct sum of mutually orthogonal spaces, the primary horizontal subspace, the primary vertical subspace, and sometimes a remainder. The horizontal subspace is the one that can be obtained from the unique 4,0 form by variation of hot structure. And this has a non-zero pairing with omega 4,0. So from here, if we have a background flux of this type in type 2a, then we would get, so to speak, a superpotential for the complex structure moduli. The vertical subspace, primary vertical subspace, is given by tensoring or by wedging essentially to 1,1 forms. This one has non-zero overlap with 2 copies of the Kähler form, but no overlap with 4,0. And as I said, sometimes there is a remainder, but I'm not going to discuss this. So mirror symmetry for fourfolds then works by exchanging a pair of mirror manifolds, X and Y. On X, one can specify a flux, a background flux in H22 horizontal, and this is mapped under mirror symmetry to a flux in H22 vertical. And the Guckow-Fafavid superpotential or prepotential that is induced by the horizontal flux on X is mapped by mirror symmetry to a prepotential, so to speak, in the A model, if you like. So this has a classical piece, which I'm not writing down, J wedge, the F, plus then higher order corrections. This is where all the instanton corrections appear, and in particular the BPS invariance and then chromophyton invariance. So by setting up this mirror computation, one can do, as always as is the case also on threefolds, do exact computations on the world sheet in the B model, and then map it, so to speak, to the A model, if you like, and read off the BPS invariance and then chromophyton invariance by an expansion. Oops. Okay, so this was what this flux is from the perspective of type 2a. But recall, we are not really doing type 2a on fourfolds. We are just using this as a tool in order to extract these BPS invariants and then chromophyton invariants. We are really looking at the physical problem that we are really looking at is F theory on the Calabi-Yau fourfold. And as it turns out, when we look at F theory on the fourfold, not all those fluxes in H22 vert can actually be considered as backgrounds. More precisely, if we want the fluxes to uplift between M and F theory to something that preserves 4-dimensional Poincare invariance, then only a certain class of such background fluxes can be looked at. This is unfortunately a technicality that I have to point out because we will need it. So the point is that we need to make sure that the flux does not have a leg along the 4th direction if we go from M theory in 3 dimensions to F theory in 4 dimensions. And to prevent this, we need to make sure that the flux satisfies so-called transversality conditions. The details of this may be not so interesting for you, but in any event, note that this vertical subspace, which is where we are computing in the A model, in turn, again, enjoys a decomposition into 3 spaces. And the first and the third space are perfectly fine fluxes in type 2a and in M theory, but they do not uplift to something Poincare invariant in 4-dimensional F theory. So I will not switch these on as a background in F theory. And the flux here in the middle, that's the flux that can also be considered as a background flux for F theory. More precisely, in the context that we are, this flux is precisely the U1 flux, the gauge flux associated with the U1 gauge symmetry on the 7 branes. So this flux takes the form Shioda map. This was this difference of the 2 sections, if you recall. Wedge the pullback of any divisor from the base. So on the base, we can choose a divisor. We pull it back to the fourfold. This gives another divisor class. We wedge this with the difference of the two sections. This gives a 2,2 form, and this is the U1 gauge flux in this description of MF. And this is the flux that we're going to consider from now on. So the task is consider a string in F theory by wrapping a D3 brane on a curve on the base in the background of U1 flux of this type. So we have a U1 gauge group on the 7 branes. We have switched on a gauge background for this theory. And as we will now see, the elliptic genus computed in this way has properties which can be summarized in one sentence by saying that the elliptic genera are quasi-Jacobi forms. So the naive and, as it turns out, wrong expectation would first of all be that the elliptic genus shares very good modular properties just from the fact that, of course, the elliptic genus is defined on a torus, so it should transform well under modular transformations. And this is true, but not quite as naively in 4 dimensions as one would have thought. So the naive expectation would be that everything should work like, for example, in 6 dimensions. For instance, if you consider a perturbative string in 6 dimensions, then it is very well known that its elliptic genus transforms as a meromorphic Jacobi form. So a Jacobi form is like a modular form, but has an extra fugacity index, in this case, the index set here. And I'm showing the transformation behavior under SL2Z. So such a form is defined by its weight, and the weight in D dimensions would be minus D minus 2 over 2, and by a U1 fugacity index M, which we will discuss in a second. So for 6-dimensional perturbative strings, this is a classic result, ancient result, that elliptic genera have objects in the ring of Jacobi forms. And this is very practical because Jacobi forms, of course, this is a freely generated ring and generated by the Eisenstein series. And then 3 further, for example, I'm choosing those basis elements defined via Jacobi theta functions. However, this simple statement is unfortunately not true. One reason we know already from 6 dimensions, and the other reason is now new to 4 dimensions compared to 6 dimensions. So already familiar from 6 dimensions is the fact that there can be a modular anomaly for the transformation behavior of the elliptic genus. And this occurs in our language whenever the curve on which the string is wrapped can split up into the sum of 2 or several holomorphic curves. Or in other words, if the string is really the bound state or can break up into individual strings. For example, a heterotic string could break up into 2 E strings. If this is the case, then, as has been discussed in a large corpus of work in 6 dimensions, then the elliptic genus is in fact only a quasi-modular Jacobi form. This means that in addition to E4, E6 and the others, we also need the Eisenstein series E2. In other words, the elliptic genus has a modular anomaly under a modular transformation. It picks up an anomalous term. This modular anomaly can be translated into holomorphic anomaly by, instead of working with E2, which is non-modular but holomorphic, we can work with E2 hat, which is, as it turns out, modular but not holomorphic. And what one finds, therefore, is in fact, as predicted by the famous BCOV holomorphic anomaly. This is true in 6 dimensions, and it will continue to be true in 4 dimensions whenever our string is really a bound state of more elementary strings. But, and now we come to the main point, the main punchline, there's a new and an extra feature for the 4-dimensional elliptic genus, which is not present in 6 dimensions. And this is the fact that the elliptic genus includes not only the quasi-modular piece, but also the derivative of a quasi-modular piece. So naively, we would have expected it just to be a quasi-modular Jacobi form, in this case of weight -1. But in addition, we must allow also for the derivative of a modular form of -2. And this is something which could, for example, in principle be an elliptic genus in 6 dimensions. And this is in fact, according to our findings, the general structure of the elliptic genus in all the cases that we have studied. So it is a sum of a quasi-modular piece and the derivative of a quasi-modular piece. Both of these are in general meromorphic. This, as I said, has to do with the fact that we need to allow for the 0 point energy to be reflected properly. And in order to specify these functions, we need in particular to specify the U1 index or the fugacity index. As for strings in 6 dimensions, these are related to the Toft anomaly on the worldsheet with respect to the U1, and they can be computed geometrically in our case as a certain intersection number where B is what's called the height pairing associated with the U1. So this is not too important for those not interested in the geometry, but everything can in fact be translated into geometric terms. Okay, so the message is again this pretentious little equation in the box, the extra derivative piece. So why would such a derivative piece occur? Let me give you a simple geometric argument. And the argument I'd like to make is, again, using the relation to Gromov-Witten invariants. So recall what Gromov-Witten invariants were. These are invariants of stable maps from an n-pointed Riemann surface into the Calabi-Yau fourfold, subject to n incidence relations. The endpoints have to lie on these n cycles AI. In our case, we are interested in the situation with 1 point fixed, where the cycle is a 4 cycle dual to the flux. And we said we take only the U1 flux, sigma dot pi star d, d a divisor on the base. Now, suppose we look at the special case where this divisor does not intersect the curve C that we are talking about. This is only a special case, but in this case, it's very clear what happens. Because now geometrically, 2 things can happen. Either the 4 cycle, G carry dual to C, to G, and the curve C are always disjoint. In that case, the Gromov-Witten invariants are 0. Or the curve C is contained inside the divisor pi star D for suitable members in the family, if there are any. If this is the case, then the incidence relation due to this divisor here simply localizes the result onto the invariance inside the threefold obtained by restricting the fourfold to this divisor. So this fourfold invariant, then in this special case, it's really just a threefold invariant. This threefold is an embedded threefold inside the Calabi-Yau fourfold with 1 extra point fixed, subject to incidence relation of this divisor. And now one can use a trick. This is just the well-known divisor equation in Gromov-Witten theory to rewrite this Gromov-Witten invariant in terms of the invariance on threefolds without any points fixed times an intersection number. So in other words, in our case, for the U1 flux, we therefore, if this extra condition is satisfied, get the product of this intersection number times a threefold invariant. But this product is just the charge R, the U1 charge of the state, because sigma with the curve in the fiber that we talked about, this curve C fib, this precisely gives the U1 charge. So the fourfold invariant is the charge times a certain threefold invariant. And therefore, it's clear that if we look at the generating function, which after all is the elliptic genus, we pick up a derivative, a psi derivative, to account for this extra charge R. So we see that we can, in elementary terms, understand first the appearance of a derivative piece, and second, see that these derivatives are associated with invariance of certain embedded threefolds inside the fourfold. This was true for this special class of fluxes. More generally, it is not true that the derivatives are necessarily associated with threefold invariance, but it is always true that we can add, that we have a sum of this form as given here, and that the derivative term has a closed form expression. It can in fact be written in terms of the invariance for a certain -2 flux. These are the fluxes which I actually didn't want to consider. They are not the background in F theory here, but it's just an auxiliary form of rewriting these invariants. And this is an agreement with a general formalism that was developed in the mathematics literature, in particular in the work by Oberdijk and Pixton. Okay, and final piece of mathematics, and then we come to 2 applications, and then we're done. These forms that we get now, so a quasi-modular plus a derivative, are in fact inside the ring of so-called quasi-Jacobi forms. A quasi-Jacobi form is something which can be made Jacobi by adding relatively harmless non-holomorphic or almost holomorphic functions in this way. For example, E2 is an example of a quasi-Jacobi form. And in fact, as it turns out, also a derivative of any Jacobi form as such can be turned into something modular by adding a non-holomorphic piece, and therefore it's by itself quasi-Jacobi. So this makes contact with this literature in the mathematics, on the mathematics side, and explains why elliptic genera are really, in general, meromorphic quasi-Jacobi forms. And in particular, again, we can replace, as I said, this derivative by a non-holomorphic covariant derivative, such that the full object is non-holomorphic but modular, and then enjoy instead a holomorphic anomaly equation, which is the analog of the holomorphic anomaly equation, which one gets when the string is the bound state of several strings in 6 dimensions. But this is something that appears in this form for 4-dimensional strings. Okay. Just 2 more remarks. We discussed this in a number of examples as well. For example, for instance, if I go back to this cartoon of how the heterotic string appears, one can find a close expression for the elliptic genus. If you give me 30 more seconds, I'm almost done. Thank you. So one finds, one can find closed expressions for the elliptic genus in concrete examples. For the heterotic string that appears in such F-theory constructions, in fact, the genus 0 invariants, which appear with the derivative, are in general, non-color Bayard threefold invariants. And their appearance can be interpreted physically. The elliptic genus, of course, knows about anomalies, in particular for the heterotic string as a special example. It knows about the Green-Schwarz counter terms. And very roughly speaking, the physics interpretation is that while the usual modular piece in the elliptic genus accounts for the Green-Schwarz terms associated with the universal 10 dB field as in 6 dimensions, the derivative pieces account for extra B fields and their contribution to the Green-Schwarz mechanism. So there's a clear physics interpretation associated with these derivative structure. And for more information, please ask me later. This can also be computed for non-critical strings, say for the E string. And finally, I'd like to conclude by pointing out the original motivation, at least for us, to study these structures. The original motivation was that we wanted to prove the weak gravity conjecture in F-theory. The weak gravity conjecture states that there should exist some, or in fact, a tower of states which are super extremal, whose charge to mass ratio is bigger than the charge to mass ratio of a corresponding extremal black hole in that theory. And if you try to prove this or check this in F-theory, then you find that indeed in every weak coupling limit, and this is where the weak gravity conjecture should hold a priori, in every weak coupling limit, one finds a asymptotically tensionless solitonic heterotic string, whose excitations then give rise precisely to this tower. So the states that we count by the elliptic genus are precisely the states which should appear in the weak gravity conjecture. And indeed, the modular properties, the derivative structure and the full modular properties of this elliptic genus allow one to quantitatively check that the super-extremality condition is satisfied for a tower of states. So from that perspective, this mathematical analysis and geometric analysis was really crucial in order to make contact with these quantum gravity conjectures. And with this, I'd like to thank you for your attention.
Thank you very much. I'll invite everyone to clap.
Timo. I have a question about the F. So if you turn off the flux, I assume that the elliptic genus vanishes. Is that the case?
That is the case, yes.
So this resonates with some work actually we did together related to the superpotentials being generated or not for F-theory and elliptic fourfolds, where if you don't have flux, you can have no flux or no brains if Euler characteristic is 0, and those are the special cases where the superpotential can vanish, where it's a hidden higher supersymmetric theory. do you see any relation between elliptic genus of strings and superpotentials? Is there, it seems, because this link is a bit in that sense, in other words, elliptic genus being non-zero being correlated with superpotential being non-zero.
So for sure in the formal sense, because the elliptic genus is computed via the by looking instead of to type at type 2A theory on the Calabi-Yau fourfold. And there, of course, if we have no flux, then we also have no superpotential in the type 2A theory. And the superpotential is precisely what allows or what incorporates the degeneracies in terms of the PPS or comorphic invariance. So from that perspective, if we go to 2 dimensions by the duality, it's obvious and indeed correct that one necessarily has this flux. Now, from the 4-dimensional n=1 perspective, I mean, not having any flux will not enhance the supersymmetry, of course, of the F theory. So I'm not sure if one can argue by enhanced or by a secret enhanced or a pseudo supersymmetry that the elliptic genus should vanish.
So but a related question is that the computations of the elliptic genus that you're doing, does it have any bearing in the computation of superpotential in 4D? That's, in other words, are the objects related in some way?
So I should also stress we look at F theory in terms of the primary vertical flux. This is the flux, not the flux that gives directly a superpotential, but which is mirror to it. So the physics of the flux background is to instead induce a D term. So from the direct 4-dimensional perspective, we should rather think about a D term as appearing. And here there is a direct physics connection. As an example, consider the situation where the curve is a heterotic curve, just as an example. Then, as we saw, the elliptic genus is related to the appearance of an anomaly. Now, an anomaly appears precisely when there's a Green-Schwarz term and precisely when there's also a D term, because the gauging and the appearance of Green-Schwarz terms in 4 dimensions are related and in fact equivalent. So the physics is really more that of the D terms directly in F theory. But by mirror symmetry, the superpotential plays a role then in 2 dimensions, as we said.
Okay, thank you.
Thank you.
Whitmore?
Yes, I was wondering what you can say about deriving these modular properties for general elliptic genera of 0-2 theories, just from the point of view of conformal field theory. So, I mean, there's very, very nice and simple arguments that for 2-2 theories, you get a Jacobi form.
Yes.
Within the context of conformal field theory. So let's see. So here you have an insertion of the fermion number.
Yes. I'm not sure if is it still visible?
Yes, it's visible.
Okay, good. Thanks. Let me.
Okay. So I was just wondering if you can derive this modular transform. Yes, there we are. And D is what here?
D is the number of dimensions. In our case, this would be 4. So we would have -1 to the F times F. In 6 dimensions would be F squared.
I see. Okay. So that insertion of F is surely part of why you're getting derivatives.
Yes.
If you exponentiated the F, I'm thinking if you exponentiated the F, you would get some kind of modular behavior, but then you're taking a derivative and equal to 0. Is there? Anyway, have you thought about, just as an abstract question about 0-2 conformal field theories, how to derive this modular transformation behavior as something you would expect?
Yes, this is a very good question.
You did the calculation and then you found from the algebraic geometry, you found that it had this structure.
That's right.
And I was wondering if you could derive that structure from 2-dimensional conformal field theories.
Yes. So unfortunately, we have not derived it from that structure. We would have loved to derive it from that structure, and I think it should be derived from that structure. So this would be a great thing to do. So we thought, for instance, in this process, we thought the simplest case would again be the special situation where that string is a heterotic string, where we would have criticality and we would know most. And there we have some hints why things work differently for general fluxes, for general flux backgrounds. But we have not been able to really pinpoint it into something. So the point is again related to the appearance of D terms. So we have some vague ideas what should be going wrong in the 0,2 field theory in those cases where we have these derivatives for the heterotic case, but it's still very vague, and I'd be happy to discuss this more and hear your opinion. But short answer, we have not been able to derive it yet, and it's definitely something that should be done.
Okay, David Morrison.
Can I ask a question?
Sure.
So just to summarize, if you were integrating divisor classes, am I right that there would be no derivative terms, but the partition function still has modular properties? Let's say genus 0 occurs with no marking.
Good. So genus 0 for Calabi-Yau fourfolds, genus 0 with no marking is not an invariant, but it's just a class. It's a grammar-fitting class because the dimension would then be complex dimension 1.
Yes, but couldn't you then be integrating some kind of codimension 1 class, like a divisor class in the fourfold?
This is complex dimension. So, well, but you have no marking. So that's the point. I mean, this you can always do. Of course, you can always add 1 point and 1 divisor, always. But here you have already complex dimension 1 without a marking. So you wouldn't know how to do this evaluation map because you haven't marked a point.
Pull back a divisor on the Calabi-Yau fourfold, you pick a divisor class of some threefold sitting in it and then pull it back. That's codimension 1. You can integrate it against your degree 1 virtual cycle. No?
So my understanding was that one needs to fix a point in order to define this evaluation map first, in order to pull back. That's at least the construction that I'm aware of. But I'd be happy to discuss this more.
Thank you. Maybe I can ask later.
Okay, thanks. I'd be happy to discuss this. Thanks.
David Morrison.
What if your flavor symmetry is SU2 or some other non-abelian thing instead of U1?
We also considered SU2 in the paper for the E string, in fact. Everything goes through with the exception that the denominator gets more complicated. Let me scroll to the formula. This formula here, we see that we have these meromorphic Jacobi forms. The eta function in the denominator for the U1 case is in order to account in particular for the non-zero vacuum energy. In the case of non-abelian gauge groups, this denominator becomes much more complicated and it needs some guesswork for how to pick it. So this is actually the difficulty in finding then explicit solutions for non-abelian groups. So in particular, these E-string example, which I didn't have time to discuss much, what we called, or what one might call four-dimensional E-string, which is just this E-string fibered over a curve. With the U1 flux only, the elliptic genus in 4 dimensions is extremely simple. It's essentially just the derivative of the elliptic genus in 6 dimensions, as is also clear geometrically. But if one looks, for instance, at the situation where the E string is inside an SU2 7 brane, then this simple structure no longer holds, and one gets extra contributions, which are also not involving any derivatives. But the general structure that you get something Quasi-Jacobi stays the same. What becomes more complicated is the denominator in the explicit examples. And of course, this has as you know, there's a very elaborate classification, of course, and computation of many examples for the 60 non-critical strings. None of this has been done in 4 dimensions. So there's really a lot to look at.
Okay, I don't see any more questions. Let's thank the speaker again. And the next session will begin at 1700 local time. We're in 6 minutes.
Can I ask a question? If
I think there's another question, Vishnu.
All right, Shayar, this question.
I was just to I just wanted to know if you've considered the following example where you consider two K3 surfaces both with an equivalent involution. So you can consider the quotient of that. That would give you a the manifold that you're looking for. It would be elliptically fibered, but the only thing is that it would admit more than one elliptic fibration. And all these invariants would depend actually on that fibration. So what kind of forms do you get out of that, the Jacobi forms?
We have not looked at the example. Well, we would have to first pick, of course, a particular curve for the string. So it will depend very much on which type of string you're picking.
Well, it probably also depends on the G form that you're choosing. The
Yes,
H class.
It depends on the curve for the string. It depends on the G form, and it depends on the type of elliptic fibration. So so this means the 7-brane gauge group, if you like. It would be interesting to look at. So we've really only studied a handful of examples, but so. Of course, to get actual results, I mean, to get concrete results, what you need are the BPS numbers, a few BPS numbers, low-lying ones, and then you just complete into a Quasi-Jacobi form. So you need to be able to do mirror symmetry following the usual algorithms for that manifold. But from what you told me, I think it would be possible to do it for that example.
So, I mean, the example obviously becomes more interesting if your K3 surfaces, if both of them have a complex multiplication. So if both of them are attractive K3 surfaces and their the associated imaginary quadratic field is the same. So one would obviously be, well, one question would be, what are the Jacobi forms that show up in this case, because they would be more interesting, and there would be more choices for H22 class as well, especially classes coming from complex multiplication. But a simpler question would be, if you look at the moduli space of such fourfolds, which are basically products of K3 surfaces more out some involution, do you know what are the attractor points in on this moduli space? I think Greg might have actually proved in his paper that the attractor points are precisely where both the K3 surfaces are attractive. But
that's how I recall also from his paper with Kalosh, right? Indeed, Greg might want to comment.
Sorry, can we? I don't mean to interrupt, but we need to set up for the next speaker. We're going to have an extended question and answer session after the next talk, so maybe we can pick it up there.
Thank you.
Thank you.
So thank you very much to the speakers, to all the speakers in the session and the session chair for the first session. Edward, could you see if your screen is sharing?
Hallo. Nou, ik ben aan het gaan luisteren. Dat is goed. Dan doen we dat. Ja.
Okay.
Okay.
Okay, looks like that works.
Great.
You see my cursor, by the way?
I do.
Okay, I'll be right back.
Okay. Okay, well, welcome to the next session for the fourth day of String Math 2020. Our next speaker is Edward Witten of the Institute for Advanced Study, who will tell us about volumes of supermodular spaces.
Well, thanks, Jeff, and thanks for the invitation to speak at this conference. And let me say that, like many of us, I haven't given up on the hope of visiting South Africa in the near future, although unfortunately it didn't happen this summer. So I'm going to be explaining how to generalize Mario Mirzakhani's work on the volume of the moduli space of Riemann surfaces of genus G to the corresponding supermoduli space of super Riemann surfaces of genus G. This was part of my paper with Douglas Stanford a year ago. I won't try to explain the context for this calculation, which involved JT gravity and random matrices as mentioned in the title of the paper. This was explained in a previous seminar, which is available online, and also an overview was written up in this article. So it's kind of impractical to both explain the context for the work and also the purely geometrical part of the work in one lecture. So in effect, I've split it into 2 lectures, and this is part 2. It's independent of part 1, though, on the purely geometrical side. So there's some related work I should mention. There's a paper by Wang, Penner, and Zeitlin on the super McShane identity, which plays a role that you'll hear about later. And then there's 2 papers by Paul Norbury. One where he introduced independently and before us the relevant spectral curve, and the second in which he proved that a generating function of the supervolumes satisfies a KdV equation. I'm going to begin by reviewing the work of Mirzakhani. So first of all, she studied Riemann surfaces as hyperbolic 2 manifolds. So in other words, every Riemann surface Y that we're going to mention comes with a metric of constant scalar curvature -2. Equivalently, every Y will be the quotient of the complex upper half plane H by a discrete subgroup of PSL2Z. Now, in Mirzakhani's work, it's important to allow Y to have boundaries, and the boundaries are always assumed to be geodesics. So a geodesic has a length, and the lengths of the geodesics are some of the moduli. And it's best to define the moduli space keeping the length fixed. So she studies a moduli space M sub GB, where G is the genus, and B is a list of lengths of the boundaries. So if it's a Riemann surface of genus G with n boundary circles, then there are n positive real numbers, B1 up to Bn, and we specify that those are the lengths. Now, this moduli space has a Weil-Petersson volume that's defined the same way as in the absence of boundaries, and Mirzakhani computes this volume. Now, a key tool is that a hyperbolic Riemann surface Y, which might have geodesic boundaries, can be built by gluing together 3-hole spheres with geodesic boundaries. Now, it's really hard to draw negative curvature. So in this picture, not everything everywhere has negative curvature, but you should imagine that each of the 3-hole spheres has constant negative curvature -2 with geodesic boundaries. The geodesic boundaries are more convincingly drawn than the negative curvature. Now, the subtlety of Riemann surface theory is that anything you might want to do, if it can be done, usually can be done in many different ways. So in this case, there are many different ways to decompose this Riemann surface by gluing together 3-hole spheres. That's basically because of the mapping class group. If you take a transformation in the mapping class group, it'll map these 4 circles to 4 different circles. They won't be geodesics, but you can adjust them in their homology class to make them geodesics again by minimizing their length. So a mapping class transformation would map this picture to another picture that would be a different way to decompose the same Riemann surface in terms of a union of 3-hole spheres. Now, if the decomposition, I'm not sure if this line on my, okay, if the decomposition in 3-hole spheres with geodesic boundary were unique, we'd get a simple recursion relation for volumes. So here I've drawn a slightly different picture. This is a Riemann surface of genus 2 with one boundary. Well, I've drawn a decomposition, but the important part of it is just the first three-hole sphere that's connected to the boundary. So I've labeled its boundaries B, B1, and B2. I'm worried about the noise from downstairs. I'm closing a window just so you don't hear some noise from outside throughout the world. Now, a three-hole sphere, its only moduli are the boundary lengths. But this part, the right part of the picture, could have a lot of moduli. The moduli of the complete picture would be B, which we've held fixed, then B1 and B2 are variable, and whatever else is over here. So if the decomposition was unique, we'd get the volume of the big surface, the whole thing, by integrating over B1 and B2 and integrating over these moduli. So the formula we'd get would be that the volume of genus 2 with B specified would be gotten by integrating over B1 and B2 times the volume of the part of the surface on the right. And the appropriate measure for integrating over B1 and B2 is just B1 dB1 and B2 dB2, where the factors of B1 and B2 come from integrating over twists that enter when you glue together the left and right of the picture. Now, this formula is wrong. And it's wrong because the decomposition wasn't unique. There was no modular invariant way to pick a particular three-hole sphere with the given boundary. So the integral on the right-hand side will actually diverge. And it diverges because you're counting the same Riemann surface many times. But it's important that the failure to include modular invariance is the only thing wrong with this formula. So here's a similar formula without integrating. So this is not meant to be a formula for volumes, but for volume forms. So while V with this font was the volume, curly V with the same subscripts is meant to be the volume form that you would integrate to get the volume. So curly V is the VP volume form, and likewise curly V with different indices is the VP volume form on the right. And then I haven't tried to integrate over B1 and B2, I've just written volume forms. So this formula is actually correct as a relation between volume forms rather than integrated volumes. But if you try to integrate it to get the volumes, it goes wrong because this you'd integrate over the moduli space, allowing for the mapping class group of the small surface. Here you'd have to allow for the mapping class group of the big surface, and the big surface has a bigger mapping class group than the small surface. So if you try to integrate this formula, you have trouble. It doesn't properly take the mapping class group into account. Well, simply integrating the formula over the moduli space of this surface would take into account the mapping class group on the right, but not the full mapping class group of the total surface. Now, to belabor this point, the moduli space of Riemann surfaces is a moduli space of flat PSL2R connections divided by the mapping class group. You have to divide by the mapping class group to get a finite volume. If instead of the non-compact group PSL2R, we considered a compact gauge group such as SU2, then you would divide the moduli space of flat connections without dividing by the mapping class group, and their volumes do obey a simple identity analogous to the naive one. So the naive identity is true for SU2, but it's wrong for PSL2R because in the PSL2R case, you have to divide by the mapping class group. The need to divide by the mapping class group means there's no simple identity like that one. This is the difficulty that Maryam Mirzakhani overcame. Now, here's the basic idea of how she did it. Consider any choice of a three-hole sphere lambda with this boundary, with this particular circle gamma of length b as one of its boundaries. So what I've actually drawn in the picture is a possible lambda, but there are infinitely many possible lambdas. Consider any possible choice of lambda and let B1 and B2 be its other lengths, boundary lengths. Suppose there were a function f of 3 positive real numbers such that the sum over all lambdas of f of the boundary lengths of lambda was 1. If there was such a function, we could fix the naive identity by simply inserting a factor of f on the right-hand side. We'd be counting all the possible lambdas, but weighting them with a factor of f, which adds to 1, would give us the right answer. So the right-hand side, assuming we integrate it over the moduli space of the smaller surface, would involve a drastic overcounting, but inserting 1 in this form would correct for that. So the insertion of f would compensate for the fact that the smaller surface has a smaller mapping class group. Well, McShane had found an identity of roughly the necessary form in a particular case, which was a hyperbolic torus with one puncture, and Mirzakhani generalized it to hyperbolic surfaces with geodesic boundaries in any number of boundaries, any genus. To explain how, the basic idea is the following. So I've drawn a surface again, and I've picked a boundary, and I've picked a point in the boundary, and then L sub p is the geodesic orthogonal to the boundary at p. So I've drawn a little bit of that geodesic, and now you imagine continuing it. If you continue it, there are a few things that might happen. Well, if it's continued, it might go on forever without either intersecting itself or returning to the boundary. It might return to the boundary it started from. It might leave the surface by a different boundary. That's not possible in the case I drew where there's only one boundary, but in a different example with another boundary over here, this geodesic might spiral around and leave by some other boundary. I'll draw a picture on the next slide. Or it might intersect itself. Now, if it doesn't go on forever without intersecting itself or leaving the surface, then it will do one of the other three, and it will do one of them first. So every p either leads to an orthogonal geodesic that goes on forever, or else that does one of these three first. Now, a theorem of Berman and series says that the probability of outcome 0 is 0. Probability means that the set of p's where outcome 0 happens has measure 0. So the boundary is a Riemannian manifold of length b, and the subset consisting of things that do outcome 0 is actually a complicated conjecture set, but it has measure 0. So with probability 1, there's an outcome of type 1, 2, or 3. And in this figure, I've illustrated the three possibilities. Here, the orthogonal geodesic leaves by a different boundary. Here, it goes around and returns by the same boundary. And here, it intersects itself before it does either one of those two. Now, the next sentence in italics is the key point of the whole proof, and it's kind of surprising. If you just give the boundary gamma, there are infinitely many choices of a three-hole sphere with that as one of its geodesic boundaries. But if you give a point P, and therefore this geodesic LP, then a distinguished three-hole sphere with geodesic boundaries is naturally determined. I think it's surprising. So the way you do it, well, I've explained it in parentheses, but to say it in words, well, let me, as an example, take this picture C. You take the boundary, and you also take this LP. Well, you take the union of those two arcs, one is a circle, one's a semicircle, and you thicken it slightly. With a little mental effort, you should be able to see that the thickened version topologically is a three-hole sphere. One boundary is a geodesic we started with. One boundary goes around up above LP and also around a semicircle here. It's a circle, it's not a geodesic. The other boundary is a circle below. You take those two other circles and minimize their lengths in their homotopy classes. And when you've minimized their lengths, they become geodesics, and you get a three-hole sphere that contains P and LP and is canonically associated with that pair. The same thing works in the other two cases, except that in A, you take the union of the two boundaries along with LP, thicken it a little. The thickened version is a three-hole sphere, and then now two of the boundaries are already geodesics, and the third one, when you minimize its length, becomes this geodesic labeled L tilde. Anyway, in each case, so gamma itself doesn't determine a three-hole sphere, but gamma and a point on it, except for a set of measure 0, does determine a three-hole sphere by this construction. So let upsilon be the set of all three-hole spheres with boundary, the original geodesic gamma, little gamma, and two internal geodesics. So in case B or C, the three-hole sphere that's shaded is an element in upsilon. And in the other case, I define a set upsilon I, which labels all possibilities for what the three-hole sphere might be, given that its second geodesic, boundary geodesic is gamma I. So upsilon I is a set of all lambdas that match the first picture, and upsilon is a set of all lambdas that match picture B or C with a particular, the set of all such lambdas that match such a picture. If lambda is in upsilon, let A lambda be the subset of gamma that leads to a picture B or C with a particular lambda. So every L sub P will lead to one of these pictures, but you can change P a little bit and get the same picture. A lambda is the subset of the boundary that leads to a particular three-hole sphere. And in case A, B lambda is the subset that leads to this picture, again with a particular three-hole sphere. And let mu of A lambda and mu of B lambda be the measures of A lambda and B lambda. Let's measure with respect to the Riemannian length of the boundary. Now gamma has length B, and except for a set of measure 0, every point in gamma is uniquely in one of the A lambdas or B lambdas. So we get a sum rule that B is the sum of the measures of the A lambdas plus the sum of the measures of the B lambdas. And that's the sum rule Mirzakhani uses, generalizing the naive sum rule. Earlier I mentioned a more simple kind of subrule that would have solved the problem, but she observed that this sum rule instead is more complicated, but also solves her problem. Now for a given lambda, the quantities mu of A lambda and mu of B lambda only involve properties of geodesics in lambda. So they only depend on the three boundary lengths B, B1, and B2 of lambda, and not on the complicated genus G surface that lambda might be embedded in. As a result, these functions are functions of the three lengths that can be computed explicitly, as Mirzakhani did. And toward the end of my talk, I'll explain how to do that. But for now, we'll just say that these are explicitly computable functions. So the sum rule has an explicit form in terms of known functions. And she inserts, she computes B times the volume, and for B she substitutes this, and each term involves a choice of a three-hole sphere with the given boundary, and that gives a way of building her surface out of a three-hole sphere glued onto a simpler surface. And then by doing that, she gets an explicit formula where B times the volume she wants is an integral over some intermediate lengths where gluing happens of these known functions, mu of A lambda and mu of B lambda, times the volume of a smaller surface. And the three terms in her recursion relation correspond to the three topologically distinct ways that a surface Y might be built by gluing a three-hole sphere onto a simpler surface Y prime. So one possibility is that Y prime has two internal geodesics that connect to the same component of Y prime, or lambda has two internal geodesics that connect to the same surface Y prime. Lambda could have two internal geodesics that connect to different components, or lambda could have another external boundary and an internal boundary that connects to some Y prime. So these three terms, if you work it out in detail, you'll see that the three pictures correspond to the three terms in her recursion relation. In each case, though, the recursion relation expresses a volume as a sum of contributions, or actually an integral of contributions, each of which involves the volume of a surface of less negative Euler characteristic. So by induction, this eventually reduces to the volume for a single three-hole sphere, and that volume is 1. So this is a recursion relation that you can explicitly evaluate to determine all the volumes. And it's actually quite useful. So first of all, for a given case you're interested in, you can literally explicitly do all the integrals and get the volumes. But she also showed that it's useful for general theory. She used her recursion relation to prove many old and new facts about volumes and intersection numbers on moduli space. And it had many later repercussions. Her recursion relation was interpreted by Eynard and Orenton in terms of topological recursion for a particular spectral curve, and this was the starting point for the work of Saad, Schenker, and Stanford on JT gravity as a matrix model. And that paper was the starting point for my work with Stanford, but as I remarked at the beginning, today I will only describe the geometrical part of that work, not the part related to random matrices and quantum gravity. Now let's go over to super-Riemann surfaces. Well, super-Riemann surfaces in string theory are most studied as holomorphic objects. And as holomorphic objects, they're very subtle. So I'm going to give the holomorphic definition, although we won't do much with it today. So from a holomorphic point of view, a super-Riemann surface y hat is a complex manifold of dimension 1/1, meaning locally you can parameterize it by an even variable z, a bosonic, if you like, complex variable, and an odd or anti-commuting complex variable theta, with some additional structure. The additional structure is a distribution of rank 0/1 that's completely unintegrable. A distribution is just a subbundle of the tangent bundle. So a distribution can be described by giving a vector field, such as this one, up to multiplying by an invertible function. So any two invertible functions times this, or any multiple of the non-zero multiple of this defines the same distribution. You can always pick local coordinates such that the distribution is generated by what I've indicated here. And then you can compute that d theta squared, which is d by dz, is everywhere linearly independent of d theta, which is what's meant by complete unintegrability of the distribution. So this definition leads to a theory surprisingly in close parallel to the classical theory of Riemann surfaces. I think a fascinating and largely understudied mathematical theory. However, it's definitely a definition that takes some getting used to. And I'm not really going to try to help you get used to that definition today, because for today, we're really interested in hyperbolic super-Riemann surfaces, which almost don't require any familiarity with that definition. I'll make slight use of it a couple of times. So today we're studying super-Riemann surfaces from a hyperbolic point of view. And from that point of view, the definition is perhaps more obvious. We simply replace a Lie group, PSL2R, by a supergroup, OSP1/2. So, well, OSP1/2, its maximal bosonic subgroup is not PSL2R, but the double cover SL2R. So we really generalize SL2R, and that's inescapable. PSL2R doesn't have a useful superextension, but SL2R does. SL2R can be defined as the automorphism group of R2 with a symplectic form du dv. Well, linear automorphism group, leaving fixed the origin. Similarly, OSP1/2 is the linear group of automorphisms of a symplectic form of R2/1. So this is R2/1 with bosonic coordinates u and v and a fermionic coordinate curly theta, and the symplectic form is du wedge dv minus d theta squared. So formally, you define OSP1/2 the same way you might define SL2R, except there's a fermionic variable. Now, the usual upper half plane is PSL2R divided by U1, or it's SL2R divided by U1. If you replace PSL2R by a double cover, SL2R, you have to replace U1 by double cover, but the double cover is just a bigger U1. And the super analog of the upper half plane is OSP1/2 divided by U1, where U1 is a subgroup of SL2R, the same subgroup we used here. And SL2R is embedded in OSP1/2. So U1 is actually a maximal torus in OSP1/2. OSP1/2 has fermionic generators, but none of them commute with this U1. So even after taking a super extension, the same U1 is still a maximal torus. So a hyperbolic Riemann surface is H mod gamma, where I defined H here, for a discrete subgroup of PSL2R. And similarly, a hyperbolic super Riemann surface is H hat mod gamma, where now gamma is a discrete subgroup of OSP1/2. So this is an old story where the original references go back to the 1980s. I might say an old story that's been somewhat more studied recently, but still hasn't been that much extensively studied. Now, in classical Riemann surface, lifting gamma from PSL2R to SL2R means endowing the two manifold Y with a spin structure. And in the super case, there was no way to avoid this lift because the bosonic subgroup of OSP1/2 is SL2R, not PSL2R. So a super Riemann surface always comes with a spin structure. Its classical limit is an ordinary Riemann surface with a spin structure. Now, a Weil-Petersen symplectic form on the moduli space of super Riemann surfaces and various generalizations for super Riemann surfaces with punctures or boundaries can be defined by imitating any of the classical definitions. So I'm not really telling you today any of the classical definitions of the Weil-Petersen form, but if you're familiar with any definition, it has a super analog. A compact symplectic supermanifold has a volume, so we can define the volume V hat G of Mg, and the goal is to find a Mirzakhani-style method to calculate it. At the end, I also will explain a formula for the supervolumes in terms of ordinary bosonic geometry. Let me describe the super upper half plane a little more concretely. So we recall that OSP1/2 was defined by the way it acts on R2/1 with these linear coordinates, preserving a symplectic form. So you could projectivize these coordinates and they become homogeneous coordinates for RP1/1, which has u, v, and theta as homogeneous coordinates. RP1/1 is just a super circle. It's convenient to introduce affine coordinates. Z is a bosonic variable, v over u. Theta is curly theta over u. And then OSP1/2 acts on z and theta by a super analog of fractional linear transformations. So far, z and theta are naturally real. Now, OSP1/2 obviously still acts on them if we complexify them. If we complexify them but take z to have positive imaginary part, we get one description of the super upper half plane H hat. So this definition makes it manifest that the super upper half plane is a complex manifold. And this complex manifold has a super Riemann surface structure that's invariant under OSP1/2, and it's inherited from the symplectic structure we started with. So roughly, what happens is that when you projectivize, a symplectic structure becomes what's called a contact structure, and the non-integrable distribution is a contact structure. So the upper half plane has a super Riemann surface structure that's invariant under OSP1/2. So every quotient by subgroup of OSP1/2 is also a super Riemann surface. What do we mean by geodesic in the super upper half plane? There are lots of ways to define it, but perhaps the quickest is the following. By setting the odd coordinate to 0, we get an embedding of the ordinary upper half plane in the super upper half plane. So you know what are geodesics in the ordinary upper half plane. I simply declare that a geodesic in the ordinary upper half plane is an example of a geodesic in the super upper half plane. Of course, it's a submanifold of dimension 1/0. Acting with OSP1/2, we can transform L to another submanifold of dimension 1/0, which we also call a geodesic. These are the geodesics in the super upper half plane. If L in the super upper half plane is geodesic and P is a point in L, there's no problem with the notion of an orthogonal geodesic to L at P. We just transform to the case that L is in the ordinary upper half plane. In that frame, you already know what's meant by an orthogonal geodesic. And since every L is equivalent to this one by an OSP1/2 transformation, that defines for you L perp in general. Now, the notion of a super Riemann surface with geodesic boundary takes a little bit of discussion. What I think is the reason it does is the following. As a real supermanifold, a super Riemann surface has dimension 2/2. So its boundary, which should be of codimension 1/0, should have dimension 1/2. But a geodesic, by the definition I gave, has dimension 1/0. I think the best explanation is that a geodesic has a canonical thickening of dimension 1/2 that's obtained by displacing it in the direction of the unintegrable distribution. This wouldn't work in bosonic geometry. If you have an unintegrable geodesic distribution on a bosonic manifold, precisely because it's unintegrable, it doesn't have leaves, and you wouldn't know how to move in the direction of in the unintegrable directions. But in the super case with a completely odd, completely fermionic unintegrable distribution, obeying a mild condition that's satisfied here that I won't state, it does make sense. And there is a canonical thickening. So the geodesic actually determines a canonical dimension 1/2 submanifold. And that's really what's the boundary of a geodesic super Riemann surface with geodesic boundary. But as a shorthand, I just talk about a super Riemann surface with geodesic boundary. Now, just as in the classical case, super Riemann surfaces with geodesic boundary can be built by gluing together three-held spheres with geodesic boundary. And once we get this far, it's not too hard to see that all previous statements have super analogs. And in fact, the original super McShane identity has been also generalized in this paper. So, okay, to state the situation for Riemann surfaces with geodesic boundary, if y hat is a super Riemann surface with geodesic boundary, and gamma is one of its geodesic boundaries, and p is a point in gamma, then the geodesic gamma perp orthogonal to gamma at p has the same options as before. It could go on forever without intersecting itself or returning to gamma. We need to explain what intersecting itself means, but I'll skip that. It could return to gamma. Well, a simple definition is to say that if you reduce mod the odd variables and intersects itself, then we say it intersects itself. It could return to gamma. It could leave by a different boundary, or it could intersect itself. The measure for option 0 is again 0. By the way, since the boundary is an ordinary manifold, a geodesic of dimension 1/0, it has an ordinary Riemannian metric with length b again. So p is just a point in an ordinary circle. Gamma is an ordinary circle. And it's again true that option 0 corresponds to a subset of the circle of measure 0. So we only have to consider options 1, 2, and 3. And the three alternatives lead to the same pictures as before, in each case picking out a three-held sphere containing gamma. So again, we get a sum rule in which gamma of total measure b is decomposed after throwing away a set of measure 0 as a disjoint union of subsets that correspond to one of the three-held spheres that can appear in the picture. And again, to determine the measure of the piece corresponding to a particular three-held sphere with given boundary lengths is a universal computation that only depends on those boundary lengths. So same picture as before, except now it's a super Riemann surface. And I've drawn a little bit of a geodesic orthogonal to a boundary. And we have to do a universal computation in that three-held sphere. I'll tell you a little bit about it later, shortly. After doing this computation, we again get a Mircea-Kani style recursion relation. It has the same general form as before, but with different universal functions that come from, well, really, they correspond to these three options. Well, the three terms correspond to these three ways to build a surface as a three-held sphere glued onto something else. I think this one corresponds to that. This probably corresponds to this, and this corresponds to this. But the universal functions are different functions that we get by studying this picture now for super Riemann surface. Now, Mirtakani's recursion relation was interpreted by Eynard and Orrington in terms of topological recursion for a spectral curve, this one, whose relation to JT gravity was the starting point for Saad et al. And Stanford and I showed that the super version of the recursion relation is related in the same way to a spectral curve that has a similar relation to JT supergravity. This spectral curve had been introduced earlier by Norbury with a different motivation. Putting these facts together, the volumes of supermoduli spaces are related to random matrix theory, just like the volumes of ordinary moduli spaces. Now, I think I still have 5 minutes, and there are two facts I'd still like to explain. One is how to compute the universal functions in the recursion relations. And two is what volumes of supermoduli spaces mean in terms of ordinary geometry. On the first point, if lambda is a hyperbolic three-held sphere with geodesic boundaries, then its universal cover is a region in the upper half plane bounded by three geodesics. To draw the pictures symmetrically, it's convenient to use the disk model for the upper half plane. And then the picture looks like this. The circle is the boundary of the disk. The disk, it represents the upper half plane. The universal cover of lambda is this region, and the semicircles are the boundary geodesics. That's the picture in the disk model. To do the computation, it's convenient to break the symmetry. See, in the computation we want to do, one of the three boundaries plays a distinguished role. It's where the orthogonal geodesic starts. It's convenient to map to the upper half plane with this particular geodesic as a vertical straight line. And then we want to know what's the probability that an orthogonal geodesic ends here on this circle. So the picture becomes this one. This is the orthogonal geodesic that we start with. And the orthogonal geodesics to it are semicircles centered at this point x0, where the orthogonal geodesic leaves the boundary of the upper half plane. And here's one of the other geodesics. And we want to know the condition for an orthogonal geodesic which needs a semicircle to meet gamma had this other semicircle. And the limiting cases that don't quite meet it are these two semicircles that end at x1 and x2. And they emanate from the points that I've labeled on the vertical axis. And B prime is the interval on the boundary consisting of orthogonal geodesics that will end on this boundary before they do anything else first. And so one of our universal functions is just the length of B prime. One of Mario Mirtakani's functions is the length of B prime in the metric on the upper half plane. So that gives one of her functions in the bosonic case. And actually, once you compute that one, it's trivial to get the others. And a super version of the same picture gives the universal functions for the super Riemann surface case. If you want more detail, it's in Appendix D of my paper with Stanford. In fact, the whole lecture basically is in Appendix D of the paper with Stanford. So the lesson here, this was a simple computation. So the set B prime that maps, that exits, well, so the lesson is that for a single three-held sphere, the decomposition according to what happens to an orthogonal geodesic is simple. The complication of the original problem is that if all you're given is the boundary, there are infinitely many choices of which three-held sphere might be relevant. So the decomposition of this boundary circle that enters Mirtakani's sum rule is very complicated. And the measure zero set that was thrown away is actually a Cantor-like set. But once you pick a particular three-held sphere to do the universal computation, it's actually all quite simple. Now, on the second point, for which I have 1 minute, I claim there's a useful general formula for the volume of a symplectic supermanifold. In general, let M hat be a smooth supermanifold with reduced space M. M is defined by setting odd variables to 0, in other words, by reducing functions on M modulo nilpotence. M is canonically embedded in M hat with the normal bundle V that's completely fermionic. As a smooth supermanifold, M hat is just the total space of this normal bundle. That description is highly non-unique and in general would not exist holomorphically. Supermoduli space is an example in which there is no such description holomorphically, as Denagi and I showed. but not in 1993, maybe in 2013. So anyway, in the smooth world, there is such a description. And then there's a projection pi from m hat to m. Now, suppose that m hat is a symplectic supermanifold with symplectic form omega hat. Restricting omega hat to m, you learn that m is an ordinary symplectic manifold whose symplectic form is the restriction of omega hat to m. Moreover, you can evaluate omega hat along m as a bilinear form on the fibers of the normal bundle, and that gives a symmetric and non-degenerate quadratic form on the normal bundle. So the structure group of the normal bundle reduces to the orthogonal group. Now, since the fibers of m hat to m are topologically trivial, being purely fermionic, well, to say it in a fancy way, you use the spectral sequence for the fibration and prove the cohomology is the same as the cohomology of the base. So the supersymplectic form of the total space is a pullback from the base plus an exact form. Now, in the bosonic world, you'd say that the volume is independent of the exact form. In the super world, you have to be more careful. The volume that you would define for omega hat is only well defined if omega hat obeys a certain non-degeneracy condition. And the correct statement is that the volume doesn't depend on psi if psi is sufficiently generic so that the volume is defined. Now, remembering that the normal bundle had an orthogonal structure, you can pick a connection A on this orthogonal vector bundle, and for any such connection, you get a convenient choice of psi. You can write this way. The one form psi is the sum of theta d theta, where theta are odd coordinates associated to a local orthonormal trivialization of the vector bundle. And capital D is the gauge covariant exterior derivative. So the thetas aren't globally defined, but the one form psi is. And so you can use it in this formula. And with this psi, you can do an easy computation of the volume and get a formula that the volume is the integral over m of the exponential of the symplectic form times the Euler class of the normal bundle. In the example studied in this talk, the supermanifold is the moduli space of super Riemann surfaces. The reduced space is the moduli space of ordinary Riemann surfaces with a spin structure. Perhaps they both have geodesic boundaries. And after shrinking the geodesic boundaries to punctures, which doesn't affect the topological invariant chi of V, V can be identified in holomorphic terms as the vector bundle whose fiber is this sheaf cohomology group, which people who do superstring perturbation theory will know as the vector bundle of odd moduli. And that's with this definition of V, this formula is the expression studied by Norbury. So anyway, the supervolumes are quantities that can be defined purely in terms of the ordinary moduli spaces. The moduli space of genus G surfaces with a spin structure and maybe with geodesic boundaries. In sum, therefore, I've reviewed Mario Mirzacani's recursion relation that determines the volumes of the moduli spaces of Riemann surfaces, and I've explained that the necessary ingredients have analogs in the super case. I've given some idea of how to compute the functions that come into the recursion relation, and I explained that what we computed in the super case has a purely bosonic interpretation. Thank you.
Thank you, Edward. We have time for questions. Shreya Sikander.
Hi. I was just wondering if there's an analog of a super mapping class group as well, because that's where you started off from, and how the mapping class group was changing the geodesic length in the original case.
Well, this is mapping class group is a topological notion.
Right.
Topology isn't changed by supervising. So this mapping class group of a super Riemann surface is the same as the mapping class group of its bosonic reduction. There simply is no topology in the odd directions.
So and there's an analog of a super Teichmuller space as well, but with the same mapping class group acting on it.
That's right.
Okay. Thanks. And another thing, not about moduli spaces, but specific super Riemann surfaces themselves. In the ordinary case, in the case of hyperbolic surfaces, to study the length spectrum, there are two things that become very important. One is conjugacy classes of hyperbolic elements of the group that you quotient out by, and the second is the eigenvalues of the Laplace operator, and the Selberg theory basically connects the two. Is there an analog of, say, Selberg zeta function or Selberg theory, basically, which for super Riemann surfaces?
I'm not aware it's been worked out, but I also could be forgetful. It might be relatively close to Docker and Fong did, things Docker and Fong did, but I really don't remember this. I feel it makes perfect sense that there should be such an analog. And I don't know the answer of whether it's known. Well, the Selberg trace formula is a formula for the determinant of the Laplacian.
Yes.
So the first question is, what's the analog?
Yeah, what's the elliptic operator on functions? Yeah.
Well, what you would do would be to take what's called a scalar superfield, a massive scalar superfield. See, in the case of a split, okay, the simple, okay, remember a super Riemann surface was defined using a discrete subgroup of OSP1/2, but a special case would be a discrete subgroup of SL2R. That's kind of the trivial case where you get what's called a split super Riemann surface. Then you would take the direct sum of the Laplacian and the Dirac operator. And a yes answer to your question is only possible if there's a good Selberg trace formula for the Dirac operator. I'm worried that there is for its square, but not for the unsquared Dirac operator. But sorry, I hope that there is. Sorry, I think.
Well,
okay.
For the Dirac operator, do you expect the eigenvalues to be related to something like the geodesics? That's
Well, sorry. Well, I actually don't know a lot about the Selberg trace formula. So for spin J, there's some kind of Selberg trace formula for an ordinary Riemann surface.
Ah, okay.
But I don't remember what it says. And I've seen it written for integer J. I assume it exists for half integer J if you're willing to pick a spin structure. I don't really know that. That has to be true in order for the question for super Riemann surfaces to have a chance. If there is such a formula for, if there is a half integral spin form Selberg trace formula in an ordinary Riemann surface, then there's a good chance it superizes. What you would do would you take the direct sum of spin 0 or spin half, possibly the direct sum of spin J and spin J plus half in general, but spin J equals 0 is going to be more straightforward for various reasons. Okay. The question, my answer shows you that I don't know the answer to your question. And there are preliminaries I don't really know also.
All right.
I think if there is such a formula, though, it's definitely worth understanding it. That's all I should really tell you for sure.
Cool, thanks. I have another question, but
yes,
maybe.
Go ahead.
Okay. Again, I mean, I feel it's a little generic just doing the stuff for classical to super, but one thing is, I mean, in the classical case, if you quotient out by discrete subgroups of PSL2Z of, so arithmetic groups, not just PSL2R,
yes,
you get modular curves and sections of a certain line bundle on it are modular forms or automorphic forms for SL2Z.
Right.
Are there arithmetic subgroups for these supergroup OSP1 too?
I don't think so, because that's a little bit like asking whether there's a super analog of a rational number. I don't think so.
Well, I don't get that analogy, but yeah, okay, because the entries have to be a super analog of the rational. Yep.
Yes.
True. Okay.
Okay, thank you. Ashwin Balasubramanian.
Oh, hi. Yeah, thanks. So I had a question. So is there a supersymmetric analog of the Fenchel-Nielsen coordinates for the super moduli spaces? If yes, like what's like the super partner to the length or the twist coordinates?
Well, there is, and it was implicit in my lecture. I just didn't explain it because I was trying to, trying to do the lecture in the available time. So I kind of hit it. I hope, let me try to find the right picture. There are Fenchel-Nielsen coordinates with one difference. So to a geodesic, okay, where in the world is my picture? I'm just looking for a picture of a Riemann surface built by gluing together three held spheres. Here, okay. So okay. In the bosonic case, when you build a Riemann surface by gluing together three held spheres with hyperbolic boundaries, locally its moduli are a length for each of these geodesics. Also a twist by which they're glued together. That means you could cut on the circle, glue one side, rotate one side by a length theta, and then glue them back together again. So there's a length and a twist for each circle. But there are no moduli for each three-held sphere.
Right.
Because in the bosonic world, a three-held sphere has no moduli except its boundary lengths.
Right.
Now, the difference in supercase is that a three-held sphere has two odd moduli. So when you take this picture, Fenchel-Nielsen coordinates mean the same as before for every circle, but two odd coordinates for every three-held sphere.
And there's no odd coordinate to the boundary itself. There's
No,
only, okay.
no, right.
Okay.
And Stanford and I wrote the Weil-Petersen form in Fenchel-Nielsen coordinates, in super Fenchel-Nielsen coordinates.
Oh, okay, great.
I'm not sure, I don't want to claim nobody else has done it. I can't remember everything that's been done. Panner and his co-authors have written the Weil-Petersen symplectic form explicitly in a different coordinate system where they used hyperbolic triangles.
Okay.
I don't know exactly how it's related to this. But anyway, we definitely wrote the Weil-Petersen form in Fenchel-Nielsen coordinates. Oh, okay. sorry. We wrote the Weil-Petersen volume form in Fenchel-Nielsen coordinates.
Okay.
My statement isn't quite true. Sorry. Yeah. Okay. Okay. My statement isn't quite true, but okay. Yeah. Okay.
Okay.
Actually, okay. I actually did compute it. Okay. You see, we used in our paper we used not the symplectic definition of the volume form, but the torsion. And the reason we did was that we were interested in unorientable two manifolds, where the moduli space isn't symplectic. So we computed the Weil-Petersen volume form in these coordinates using the torsion. Yeah, okay. I exaggerated when I said before what we've done. Any other questions?
Sasha Voronov?
Hello. When you create a pair of bands in the super case out of an orthogonal geodesic, will the new geodesic boundaries that show up be always of Neveu-Schwarz type, or do you have to mess with Ramon type boundaries?
They're of both types.
Neveu-Schwarz types?
No, they're of both types.
Oh, both types. Okay, yeah, that's what I
They
thought.
have to be of both types because to within infinitesimal corrections, the geodesics are the same as they are bosonically, and in the split case, they're literally the same. And the spin structure could be anything, so it could be of Ramon or Neveu-Schwarz type on either circle. I kind of hid such issues in the talk, but
how would this affect the computation of the volume? I would expect more terms in the recursion formula.
We showed that you can write a correct formula with all these Neveu-Schwarz contributions.
I see. Okay, thank you.
Sure.
Kumran Vafa?
It's nice talk. I have a question regarding the topological string perspective on this. So things that compute on things on moduli space are typical bread and butter of topological strings. Whereas the moduli space of, and for example, your old work, that's the kind of thing that you did with the context of Mumford classes and so forth. But in the context of Mirzakhani's models, in the context of topological A model, I have not seen any formulation of a topological A model which computes the moduli, the volume of the moduli space. If one had such a formulation, that could open up a path to a new proof of Mirzakhani's model, because we know that Mirzakhani's model is equivalent to topological B model on a Calabi threefold. So if you have a direct topological A model formulation of it, which computes the moduli space volumes, then mirror symmetry will be another derivation of Mirzakhani's model for that model. That would be advantageous perhaps in some ways, because instead of getting a recursion relation which satisfies the correct formula, you directly get the answer. So So the whole thing then boils down to understanding whether there's a topological A model, which directly computes the moduli space of the volume of moduli space, and that's the question I wanted to ask you. Are you familiar with such a model?
Well,
is there something that you have?
Not quite. Well, suppose we're interested in the Euler characteristic of moduli space. What answer would you give there?
That we know that topological A model does compute it. That's in fact the topological A model on Calabi threefold computes it for the case of the conifold, for example. Yeah.
There's a different answer I thought you might have given. If you take the minimal model with a
oh yes, I was giving the mirror answer. Yes, the topological A model would be the mirror model that you probably want to answer. Yes.
If you take the well, something you can do on ordinary Riemann surfaces is to couple to a Landau-Ginzburg minimal model, an n equals 2 minimal model with a phi to the r superpotential. I think phi to the r plus 1 maybe. And then you topologically twist it. You get a topological field theory. And the partition function of that topological field theory is given by a formula similar to what I claimed here at the end. Superficially similar. Except that the Euler class is not straightforward to define because things aren't locally free. Sorry. Where is it? Oh, this formula at the top. Okay. So if you take a twisted minimal model and couple it to topological gravity, you get a partition function which is like this, except that chi of v isn't straightforward to define. It depends on an integer r. And formally, if you continue to a crazy value of r, which is something like -1, you get this formula with the same v.
Right.
Whereas you get the Euler character of moduli space if you continue to something like r equals -2. I might be giving the wrong values, but I think you're familiar with one continuation.
Yes.
And if you continue to a different negative value, you formally get this formula.
Oh, you do. So you're saying there's a formal way to get the volumes in that way?
The super volumes.
The super volumes, or the volumes also, right?
Well, no, I don't know such a way to get the volumes.
Oh, super.
No, sorry. No. Well, what I'm saying is a little misleading. You have to couple to topological gravity. You don't study. I'm not sure if that was part of what you wanted or not.
No, I want topological gravity. I want topological A model gravity, topological strength.
Okay, all right. Well, but you need to include this class omega, which might be, even though it's related to Mumford classes. Okay, you have to describe omega in terms of Mumford classes, you have to turn on the whole hierarchy, namely the hierarchy that appears in this spectral curve. Oh, where did I write it? The coefficients in this hinge function are the coefficients. If you want to convert omega into Mumford classes, you have to use the coefficients of the hinge function as coupling constants. If you do that, and you couple to the minimal model continue to some crazy negative value, then formally you get this.
Right. Well, that I understand. That's in your work with Robert in particular. You explained that connection with
well, how to express this in terms of Mumford classes. We explained.
Yes.
And then the part I'm telling you is that this chi of v is a continuation to something like r equals -1 or something. I don't remember the value of the rth minimal model, rth n equals 2 minimal model, topologically twisted. So you take something like a 1 over phi superpotential.
But this is not in the form of topological strings, let's say on a Calabi or something like that. You wouldn't have that such a formulation.
I can't put it that way, but it wouldn't shock me if you could. That's why I'm giving you this answer.
I see. Okay.
You know how to do the Euler characteristic, you say. And the Euler characteristic involves a similar analytic continuation to an equally crazy looking value. So if you can do that one, maybe you can do this one.
Okay. Thanks.
Sure.
Are there any other questions? If not, let's thank the speaker again. So I want to take the opportunity to thank all the speakers and this session chair for the morning session right now. And given that we're having the public talk in an hour from now, roughly. We're not going to have a breakaway session, but I will leave the room open for another half an hour if people would like to ask questions of the speakers from the morning session and or of the last talk. If you would just be so kind as to, if you're asking a question to a particular speaker, state who the speaker is. And otherwise, we will close the session in half an hour so that I can open up the next Zoom room for the public talk. Thank you very much. Edward, there's a question in the chat room directed at you from Alex Feingold.
Okay, the question from Alex Feingold, is there a generalization from hyperbolic 2 space to hyperbolic 3 space? Well, hyperbolic 3 space is very different. For example, hyperbolic 3 manifolds don't have moduli, whereas hyperbolic 2 manifolds have moduli, which are the moduli of Riemann surfaces. On the other hand, if you think what you're doing is quantum gravity, hyperbolic 2 space, okay, as explained in more detail in the other lecture, the one I didn't give today, today's story is related to a version of 2-dimensional gravity. So hyperbolic 3 space would be related to trying to understand 3-dimensional gravity, which physicists are very interested in, but progress has been halting, I would say. Although there was a little bit of recent progress by Maxfield and Toriaci, which gave a little bit of hope. But we're far away from having it, well, okay, we know some interesting things about 3-dimensional gravity, like the Brown and O states and the boundary Virasoro algebra. But I would say we're far away from saying interesting things about 3-dimensional quantum gravity that would relate to facts about hyperbolic 3 manifolds. That seems pretty far away from what we know how to do.
I guess what I meant, wait, there's another question.
There is another question, which is, can you extend this story to Riemann surfaces with conical singularities? Okay. This lecture was about Riemann surfaces with geodesic boundaries. A geodesic boundary is a circle. If you shrink it, you get what's called a cusp. A cusp is a singularity that's infinitely far away. It's like the limit of a cone with a zero opening angle. So the question is about non-zero opening angles. There is a very interesting story with non-zero opening angles. So it's been shown that if the opening angle is bigger than pi, I think, sorry, no, less than pi. Yeah, it's been shown that for cones with this, it's been shown that for cones obeying an inequality for the opening angle. I'm afraid sorry, I can't remember offhand the reference. Well, both I and also Maxfield Toriaci worked on this recently as physicists, but there's a prior math paper that I'm forgetting the reference to. Anyway, Mirzakhani's story has a generalization where you allow conical singularities as well as geodesic boundaries, provided you put a certain inequality on the cone angles. And the physical interpretation of JT gravity is more simple with boundaries. And I think the derivation is also a little bit more straightforward. But as long as the conical angles obey a certain inequality, they are very similar formulas with cone angles. You can guess the formula. It's hard to guess the inequality, but you can guess the formulas because a geodesic boundary corresponds to a hyperbolic conjugacy class. The hyperbolic element has a trace. A cone angle corresponds to an elliptic conjugacy class. It also has a trace. If you just analytically continue, you can guess what the relation should be. So under a certain restriction on the cone angles, volumes with cone angles are analytic continuations of volumes with boundaries.
Thank you. Thank you.
And by the way, my paper has, it's certainly in the math literature, but my paper has an attempt to explain for physicists why there's an inequality on the cone angles that's needed to make the arguments work.
Okay.
Edward, was this in your paper, the restriction on alpha between pi and 2 pi?
Yes.
Okay.
I just wanted to clarify that point because so there's a third kind of boundary as well in at least classical hyperbolic surfaces where you quotient out by an element of trace exactly equal to 2. So parabolic elements.
Yes, that's the small, see, that's not essential. That's essentially part of my lecture, at least in the bosonic case, because you're describing a cusp, and a cusp is just the small b limit of a boundary. So in the bosonic world, volumes for Riemann surfaces with cusps can be gotten by just setting b equals 0 in the corresponding formulas for Riemann surfaces with boundaries. It's more subtle in the superworld because there are two different parabolic elements of OSP, two different parabolic conjugacy classes of OSP1/2. One of them is the small b limit of a boundary, and the other is not. In OSP1/2, there's actually a parabolic limit that's not, sorry. In OSP1/2, there's a parabolic conjugacy class that's not a limit of any hyperbolic conjugacy class. So in OSP, the question that people are asking about cusps is actually more interesting for super Riemann surfaces. It's discussed from my paper with Stanford, but it's too elaborate to explain now. But we didn't get very far. I'm sure one could do much more.
I had a question about the equation that you showed in your paper. So you said the Mirzakhani thing follows from this classical sinh basically, and your thing was just a little bit of a deformation of that, or?
No, it's a similar but different function with a cosh instead of a sinh.
I see. So Mirzakhani's recursion can also be understood as a recursion coming from a solution of a KdV equation.
Well, I won't be able to, if you're asking whether there's a super analog, I won't be able to answer the question, but I won't be surprised if it is. I wouldn't be shocked if that's already been done by Norbury, who I think has, I believe in Norbury's recent paper. Well, first of all, to get a KdV equation, you need more variables than was in my lecture, I think. Well, sorry. Anyway, Norbury related the super volumes to a different solution of KdV. So if there's a yes answer to your question, it very possibly either is in Norbury's paper or an extension, or at least his paper might be a starting point for doing it.
Actually, a quick follow-up on the limit on the cone angles. Is it similar to, say, in Liouville theory, if you have punctures and the real value of momenta, there's like a natural limit for them. People usually put it between 0 or in half and so on. Is this something similar? Because in the usual case, that can be interpreted as a local cone deficit angle in the bosonic case.
I don't know. It'd be great if that's true. What's the if you certainly it's true that the Liouville operator can be thought of as creating a cone angle. The inequality that people usually impose, do you know what limit it corresponds to in the deficit angle?
So because of this alpha to q minus alpha thing that we can do. So usually everybody puts the real part of the momenta between 0 and q/2. I was wondering if that's the analog of putting the cone angle between 0 and pi.
It might be, but do you know what cone angle you get at q/2 by any chance?
I would guess pi. I'm not
That's
sure.
correct. There's something that was, there's actually something I forgot to write in my paper, even though it's obvious in all the formulas, which is that there's a symmetry. Well, naively the cone angles go from, okay, there's a symmetry under something like alpha going to 4 pi minus alpha. It's true that to get to 4 pi, you've analytically continued. The derivation only made sense if alpha was between 0 and pi, or maybe between pi and 2 pi. It's embarrassing to be forgetful, but I am right now. The derivation worked in a certain range, but then you get an analytic function. And the analytic function actually has a symmetry under alpha going to 4 pi minus alpha. And I was wondering if that's related to the Liouville symmetry you've mentioned.
Okay.
It would be nice if it is. I completely forgot to mention it in the paper. And I certainly didn't.
I've seen this sort of similarity between the symmetries that arise in the hyperbolic metrics with cone singularity literature and the Liouville literature. I sort of assume that the pattern is strong enough that they are the same, but I haven't sort of nailed it down.
I hope that's correct, is all I can say.
Okay, okay, thanks.
Sorry, I can make, I have a question.
Let me say one more thing about that. I'm slightly worried though, because in the story with volumes, there are two special values of alpha, namely pi and 2 pi, because pi is, well, a certain derivation stops at pi. 2 pi is the value. Okay. The symmetry is alpha going to 4 pi minus alpha, even though naively alpha goes from 0 to 2 pi. Well, anyway, I don't know what to say. Okay, it should be.
So this is already for the bosonic case. This is, there are two special values already for the bosonic case?
Well, there's one special value in the answers and there's one special value in the derivation. But the value which is special in the derivation, I don't know if it's really special, because maybe it's just a technicality in the derivation. So maybe there's only one special value, but it would be 2 pi. You'd see it in my paper, for example, except that I forgot to mention that there was the symmetry. I probably should add a sentence or two and resubmit that.
Okay, I'll look. Yeah, thanks.
Anyway, there was another question.
Hi. Yes, I had maybe a quick comment about that and a question. That yeah, if you do Liouville with a fixed length boundary and you insert the Liouville operator and you do it maybe in the context of the minimal string, maybe it's better. And you take the semi-classical limit, you'll get the JT gravity answer with the conical defect. And that can be matched precisely, but I don't have all the formulas in my mind to check whether this relation between the alphas, I don't know, I will have to check it in detail, but there is a precise relation between local insertion and a conical defect.
Good point. But this large P limit, C is going to minus infinity, right?
Yes. Yeah.
Well, at least that's a semi-classical region. So
yeah. No, sorry. The minimal model is going to minus infinity, but the Liouville mode is going to plus infinity.
Oh, okay, fine. Even better, because that's physically sensible for Liouville.
Yeah, from the Liouville side, it's fine. Yeah.
Okay. Good point. Yes.
And I also had a question about your talk. So from JT gravity, we can also do n equals 2 supersymmetry. Is there any generalization of the moduli space for that?
Well, first of all, there's JT supergravity. And secondly, the same arguments as before appear to show that say for a closed Riemann surface, the partition function is related to the volume of the supermoduli space. There's a technical problem in defining this, defining that volume. I think it's just a technical problem. I've had an extreme frustration with this question. Well, first of all, Schenk, in a previous paper, Stanford and I did have some discussion of the super Schwartzian, and therefore the density of states on the disk. And I've also computed on an annulus, and everything seems to work with a spectral curve that to n equals 2 supergravity. But to check it was right, I wanted to compute for a three-hole sphere. And it's not hard to do the matrix model computation, but when I've tried to do the gravity computation, it hasn't worked. So I don't know what to say about that. It should work as far as I know. But
I see. And the matrix model is, I just thought it would be a little bit more complicated because of the extra U1 symmetry.
there's a different matrix model for each value of the U1 charge. There's a separate matrix model for each supermultiplet. And I didn't find this completely obvious at the beginning, but the result from the annulus appears to show that the matrix models for different values of the R charge for different supermultiplets are statistically independent. And for each one, there's a spectral curve, which is somewhat similar to the Sinch spectral curve.
Yes, it's like a Sinch divided by the energy by E or something like that.
Yes.
But yeah, there my confusion is that you have a sum of two terms that start at different energies, right?
What do you mean by
you have the Sinch, but the Sinch starts at different energies depending on the charge.
Yes, but for each charge, it only starts at one energy.
Yes, but
for low values of the charge, there's also a delta function at 0.
Yeah.
The spectral curve, I think, is 1 over E. Y squared is 1 over E times Sinch squared of something with a square root. But as I've said, well, so far I haven't been able to get a sensible answer in the gravity computation for the three-hole sphere.
Okay, thank you.
Sure.
So I had a small comment about, in trying to understand the pictures that you showed about if you start off with a geodesic perpendicular to the boundary geodesic, what its behavior would be.
Yeah.
First of all, I have to say you made the Mirzakhani's proof remarkably clear. It was very nice. Seriously. But so the first thing, maybe it doesn't work for manifolds with boundary, but the first thing that would come to mind is to apply the Poincare recurrence to this geodesic. And that would say that it should come back and hit the boundary that it started off. But although Poincare recurrence, it doesn't tell you when it would come back. It just says eventually it will come back and hit the boundary.
Well, in this derivation, we stop as soon as it either intersects itself or reaches any boundary.
I see. That's what. Okay. So as soon as the first intersection, the algorithm stops.
Well, we only look at the part if you look back at my pictures, you'll see that the only part of the geodesic we use is the part up to the first interesting event, where an interesting event is where it either reaches the boundary again or intersects itself.
I see.
What the geodesic does if continued after that isn't considered.
I see. Okay. And I think this must be in your talk as well, but the length of this geodesic after you end it, this should essentially determine the new pair of pants that you get.
Well, we didn't use that explicitly, but from the picture I drawn, you could compute that length. Well, that relationship wasn't what we wanted to know.
No, I know. That's why I just saved it right to the end.
I'm sure you could just, the picture is simple enough that you could compute other things with it. Probably. The only thing which we used it for was what I said in the lecture, to compute the length of that interval that I labeled B prime on this slide. You can do more, but that was that's what's needed from Mirzakhani's derivation.
Right. No, I understand. But yeah, it was just such a nice tool to work with this thing. To decompose the surface into further smaller, not even surfaces, but pair of pants using this geodesic is quite a neat idea.
Well, I actually think it's amazing it works. That's all.
Yeah, that
40 minutes isn't very much for a talk, but I thought that point was so amazing that I really wanted to explain it in detail.
that was. Thank you. Appreciate it.
Sure.
Just very quickly, I just want to take some screenshots as the conference photo. If you could turn your camera on for a few minutes, that would be great. Thank you.
Hey, Edward, if I may ask another question.
Yeah.
Thank you very much for the nice talk. It's just a technical detail and you jumped over it, like this notion of intersection of two geodesics on a
Yes.
hyperplane surface. Is it correct? I would think about this if I have a vector field which is conformally invariant, conformally invariant, and this builds a foliation of dimension 0/2. Then the notion of intersection would be if this two geodesics intersect one of these leaves.
Yeah, I regard that as the most natural definition.
Okay, I see. Yeah, okay. Okay,
Now,
great.
I consider that the most natural definition,
Mm.
but you could more crudely view it as a topological notion. Just reduce mod the odd variables and ask whether the geodesics intersect in the reduced space.
Mm. Okay, I see. Yeah.
But still, what you've said, I think, is the natural super definition.
Great, thank you.
Is there a map between supermoduli space and classical moduli space?
Well, there's not a natural map. So in the smooth world, there's such a map for any smooth supermanifold, from any supermanifold to its reduced space. And I actually use that in deducing the formula in bosonic terms for the volume of supermoduli space. That formula with the Euler class was
Right.
deduced using the
Going
fact
back
that smooth
well.
world there is such a map. However, holomorphically, there is no such map in general. So if we replace the boundaries with punctures so that our supermoduli space is a complex manifold, you could ask if there's a holomorphic map to the ordinary moduli space. And Tanagi and I showed that there's not, except in some low genus cases.
I see. That
makes, in my opinion, that result is actually what shows that one should study supermoduli space. If there was a holomorphic map, it would mean that supermoduli space could be reconstructed in an elementary way from ordinary moduli space.
That was my hope.
You would not have to study it as you would not have to study it as a thing in itself. This
Right.
result shows that it's an essentially new holomorphic animal that doesn't trivially reduce to ordinary moduli space. That wasn't important in today's lecture because today's lecture was basically in the symplectic world rather than the holomorphic world.
Mm-hmm.
And symplectically, one doesn't see this difference.
Mm-hmm. Okay. There is just no holomorphic map. It's not that there is a holomorphic map which is not flat or is not.
I don't know what flat would.
I mean, fibers are all the same dimension. So
I think fibers will have to be of the same. Well, sorry. There's of course a map to a point. What you want is a holomorphic map. Supermoduli space has there's a natural embedding of ordinary moduli space in supermoduli space. What you usually ask for is a projection, a sort of left inverse of that embedding.
Mm-hmm.
And that's what doesn't exist.
Mm.
It would automatically be flat. There's no further condition you would ask for.
Yeah, no, if the embedding thing is true, then it would be flat. If it existed, it would have been flat. That's true. But
if you ask, suppose you decide you're interested in the question of whether such a homomorphic map exists. If it exists, you have to find it, and then you need a clever construction of some kind. If it doesn't exist, probably, if you just find any obstruction, potential obstruction to its existing, you'll find the obstruction is non-zero. So after wondering for years whether such a holomorphic map existed, I became convinced it probably didn't. So Donaghy and I just calculated basically the first obstruction in a special case. I could explain what's meant by a special case. And since the map doesn't exist, the obstruction we computed was non-zero. I'd become convinced such a map wouldn't exist because I felt the experience was that supermoduli space has no simplifying properties beyond what's needed for superstring perturbation theory to make sense. And the existence of such a map is not needed for superstring perturbation theory.
Thanks, I missed after your comment that I can explain the special situation because of internet. I'm sorry.
Sorry, which was the special? I don't remember which question you're asking about.
No, I missed your comments because of unstable internet connection after your comment that you can explain what the special situation is. So I apologize.
I don't remember I don't remember when I used the word special situation. So I can't, yeah, I need more of a clue to tell you what you missed.
So you said that with the Ron Donaghy, you just simply checked if there was an obstruction or not in some special situation.
Well, okay, right. So, okay. If, for example, you look at Manin's book on it's called Gauge Fields in Complex Geometry. Okay, there's a sequence of cohomological obstructions to the existence of such a holomorphic map. If a finite sequence of obstructions all vanishes, it will exist. In particular, but the first one is more straightforward to define. The higher obstructions are less straightforward to define. So suppose you think that the first one is an H1 with values in some sheaf. Suppose you think it's non-zero. Well, then it's probably non-zero if evaluated on a generic curve in the ordinary moduli space. This is a little tricky because you need a compact curve in the ordinary moduli space, and constructing one is a little tricky. So, but anyway, people have done that. There's a literature on compact curves in ordinary moduli space. So
I know a lot of
the simplest. Yes.
In moduli space, do you mean the Deligne-Mumford compactification or?
Well, we wanted to prove that this map doesn't exist even if you don't try to extend it over the compactification. So we simply considered the moduli space uncompactified. Obviously, it's a stronger proof. It's a stronger result to show that there's no map, even without asking if it extends over the compactification.
Yes, I agree. The comment was that there's a lot of where this theory of Teichmuller curves does produce curves which holomorphically embed in the classical moduli space, but they are always non-compact.
I know, but people have constructed compact curves, and luckily I attended a lecture by Krishever, I think. I had attended a lecture on compact curves in moduli space, and one of the ones he had described was convenient for this problem.
No,
so
I think, yeah, so I, sorry.
Let me just finish. So we evaluated the first obstruction on a conveniently chosen compact curve in the ordinary moduli space. And it wasn't zero, as you would expect if the map doesn't exist. If it doesn't exist, a generic obstruction will probably show it doesn't.
I see. Yeah, okay. As far as, okay, just a comment.
I'm afraid I can't hear. Your connection must be having trouble.
Hello?
Yes, hi. Well, we missed some of what you said, I'm afraid.
Oh, I said that in genus 2, there are, I know of examples of compact curves in M2, and these are basically Shimura curves. So they're
Genus 2, you have to compactify before you have compact curves. Because in genus 2, the uncompactified moduli space is an affine variety.
yeah, it's just a configuration space of 6 points on C.
And therefore, okay, it would the okay. Our proof was really starting in genus 5.
I see.
But in genus 2, trivially, the map exists over the uncompactified moduli space, and there's even a relatively nice one found by Doker and Funk. I would guess, however, that it does not that there's no map that extends over the compactification, and that would be interesting to prove. So you could use the curve you just mentioned, try to evaluate the obstruction on them, and my guess is it would prove to be non-zero.
Okay, now I'm okay.
That would be an interesting result.
So in genus 2, this over the genus 2 moduli space, this obstruction can be explicitly written down simply because the moduli space has explicit coordinates. I mean, you said it's an affine variety. It's actually just a configuration space of 6 points in C.
I know, but here compactification is important, and it's well. I don't know what would happen if you try to really do this. I can't say.
Okay. I mean, there's also so there's also different kinds of compactifications as well. So one would also have to make a choice there. I mean, for example, configuration spaces is the Fulton-McPherson.
Well, let me just say that in string perturbation theory, the important one is the Deligne-Mumford compactification.
Okay.
I know that the splitting, what we're talking about now are called splittings. The splitting found by Doker and Funk for the genus 2 moduli space with even spin structure does not extend over the compactification. I'd guess that there's none that does, but that isn't known.
Mm-hmm. And the way the classical moduli space sits inside the supermoduli space, or any ordinary manifold sits inside in the supermanifold, you said there's a, is it an immersion or
It's
an embed?
Well, you see, the way mathematicians say it is as follows. You have a supermanifold. It has a ring of functions. You reduce that ring mod nilpotence. So you get a ring homomorphism from the superring to the reduced ring. And geometrically, that corresponds to a map in the opposite direction from the reduced space to the supermanifold.
Okay.
Okay, if there are any more questions, or is that? Is there another question? Okay, if not, I want to thank everybody again, and I'm going to close the session for today. So thank you for participating. Thank you to the speakers. Thank you, Edward, for answering the questions during the session. It was really intended for all the speakers, but I'm glad that okay, so I'm going to close the session for now. And I'm going to open another room for those of you who would still like to join the public talk. Let me see if I can find the Zoom coordinates, and I'll put it in the chat room quickly. Okay, I'm just pasting it in the chat room now if anybody would like to sign in, and you'll get a notification after that. Okay, again, thank you very much. And we will see you, for those of us who don't join us for the public talk, we'll see you bright and early or sometime late in the day tomorrow. Robert, are you working from home or have you gone into the institute?
Currently, I'm at home. You know, I think certainly, you know, it's kind of interesting that at least here in New Jersey, you know, some of the labs are open because it's seen as essential business. But I think theorists, we're supposed to be. If you can work from home, you should work from home. So. We're not essential business, which is something which I think is debatable.
Yeah. What about the systems biologists?
Well, if they have a wet lab, you know, then it's okay.
Very stringent condition.
Exactly. So theorists are a little bit discriminated.
I have a collaborator in Kyoto, and I asked him whether they were going in at some point, and he said only essential people are supposed to go in. But in Japan, everybody's considered essential.
I see. Well, in all of the 50 states of the US, I think New Jersey is one of the most rigid. But there's a very you know, sensible scientific advisory committee too, so I think they're doing the right thing. So.
Yeah, that's true.
It's just very sad that we can't give these lectures in person. I think I would love to do that. So
yeah,
at another occasion.
Indeed. Have you been to South Africa before?
I've been to South Africa, but not to Stellenbosch. No.
Oh, okay.
In fact, the Institute for Advanced Study, they get together every year, and
yes.
This year the event was planned in Stellenbosch. So
oh no,
I would have come twice in 1 month.
Yeah, it's the heart of wine country in South Africa.
I know.
On the other hand, alcohol is banned at the moment.
Is it?
Yeah, they unbanned it at some point and found that you know, it's like one of these things where if you bottle things up for too long and then you release the pressure, it goes nuts for a while.
Yes.
And then they found that there were too many avoidable casualties, let's say, that were alcohol related, and they decided to ban it again. So now alcohol is only available for export, actually. So the wine farms and people are able to ship it abroad, but they're not able to sell it to South Africans.
Wow.
Yeah.
Wow. It's something.
Yeah. Okay. I think we can start.
Mm-hmm.
You're ready. I will introduce you. Turn that down. Okay. So the room is open and people will join as they come.
Sure.
Okay, well, welcome everybody. This is the public lecture part of the String Math 2020 conference that is ostensibly being held out of Cape Town, to the extent that these things are possible anymore. And it is a great pleasure to introduce Professor Robert Dycroft, who is the director of the Institute for Advanced Study and the Leon Levy professor there. Professor Dycroft is a mathematical physicist who's made significant contributions to string theory and the advancement of science education. His research itself focuses on the interface between mathematics and particle physics, which is the central philosophy of this conference. And therein, he's found deep connections between matrix models, topological string theory, and supersymmetric quantum field theory. Professor Dycroft was awarded the Spinoza Prize, which is the highest scientific award in the Netherlands in 2003, and was named a Knight of the Order of the Netherlands Lion 2012. He was also the past president of the Royal Netherlands Academy of Arts and Science and the past co-chair of the Inter-Academy Council. He is a distinguished public policy advisor and a passionate advocate for science and arts, and really a phenomenal public speaker. In fact, one of the first lectures on string theory I think I've ever heard was by Robert Dycroft. And it's a great pleasure to introduce him and have him talk today as part of the String Math 2020 conference. Robert.
Thank you so much, Jeff. Can I share my screen? Okay, is this working? Jeff, just let me know if this is working.
Yes, we can see it.
Okay, wonderful. So thank you so much for this kind introduction and all the heroic work that you and your team have been doing over this week. It's a wonderful meeting. It's such a regret that we can't be in South Africa at this moment. We were just joking that in physics terms, we're all in a momentum eigenstate. We are in some sense everywhere and nowhere. So it's great to be together, but of course we'd love to be there in person. And I've been enjoying this virtual conference very, very much. So thanks also to all the speakers for the wonderful lectures. So I'm gonna talk quite freely about the interaction between physics and mathematics, but in particular the relation with string theory. And I chose as a title a small variation on one of the most famous titles in mathematical physics, the title of an essay Eugene Wigner wrote in 1960, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Many of you might know the title. I would really recommend also to read the article. It actually starts in a very interesting way. The first paragraph, Wigner says, well, there's a statistician that meets a classmate, and they talk about population dynamics. And then the classmate actually shows, the statistician shows a graph, and the graph and the formula of the Gaussian distribution. And clearly that formula has a pi in it. And so the classmate asks, what's that symbol? He says, well, that's the Greek letter pi. What does it mean? Well, it's the ratio between the circumference and diameter of a circle. And then the friend asks of the statistician, what do circles have to do with populations? And it's a good explanation, a good example of this wonderful property of mathematics to cover so much more than it was perhaps originally invented for or applied to. And by the way, the final paragraph of that essay I find also quite beautiful. This is it. Wigner actually ends on this, as he called it himself, cheerful note that the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. And then he writes in 1960 that we hope that it will remain valid in the future and that it will extend for better or for worse to our pleasure. even though perhaps also to our bafflement to wide branches of learning. And I think that's in some sense a wonderful summary what has happened in the 60 years after this article. Now, there are, this view of the appropriateness of math in physics has been there through the ages. This is a famous quote by Galileo. He wrote about the book of nature that you could read, and you can only read it if you know the language. And it's as he says, it's written in the language of mathematics, which at that time was Euclidean geometry, so triangles, circles, and other geometrical figures. And without, it's impossible to understand a single word, and you're wandering around in a dark labyrinth. This is Arnold Sommerfeld, a famous mentor and advisor of so many theoretical physicists at the turn of the 20th century. If you want to be a physicist, you must do three things. First, study mathematics. Second, study more mathematics. And third, do the same. Here's Richard Feynman. To those who do not know mathematics, it's difficult to get across a real feeling as to the beauty, the deepest beauty of nature. If you want to learn about nature, to appreciate nature, it's necessary to understand the language that he speaks in. Now, Feynman, by the way, also known for this famous quote: if all mathematics disappeared today, physics would be set back exactly 1 week. Physicists are arrogant enough that they can invent that mathematics themselves, and always felt this was the wonderful put down, until actually Michael Atiyah told me the following riposte: that was the week that God created the world. So there's a long history here. And certainly I think there's, for mathematics, often, mathematics considers itself a Platonic science. It's involved with physics, but it's involved with much more. And there's a famous quote by Jean-Pierre Serre, who actually didn't dare to make the remark himself, but he told Raoul Bott, when they both got the Wolf Prize, and Raoul Bott wrote the quote down: while the other scientists search for the rules that God has chosen for this universe, we mathematicians search for the rules that even God has to obey. And there's a kind of arrogance sometimes in mathematics. Now, when Hilbert in 1900 puts forward the 23 most important problems in mathematics, which was a very good list. It included the Riemann hypothesis, the Poincaré conjecture. He also included problem 6, mathematical treatment of the axioms of physics. So what are the axioms? And basically finding a fundamental theory of physics, which in his days, he basically thought of probabilities and mechanics. This was before the birth of quantum mechanics, was seen as one of the many open problems in math. Now, there's a kind of a complementary view, and I won't tell too many jokes, but this is one of my favorite because it was told to me by a famous mathematician, Alan Kohn, a Fields medalist. He tells the story of the physicist who actually has a big bag of dirty laundry. And the physicist walks into the village and he sees a little shop. And the shop has a sign, laundrette. But not only that, it also has a sign, cafe, restaurant, hotel. So basically it's a shop of everything. And of course, the shop is run by a mathematician, and the physicist comes with the dirty clothes and say, can I wash my clothes here? And then the mathematician say, no, 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 you're confused. The only thing that we sell here are advertising signs. And so sometimes I think from a physics perspective, mathematics is a lot of useful or useless, I must say, terminology that actually doesn't help to solve physical problems. Now, I just want to make the case today is that mathematics might be more an environmental science than mathematicians think. Famously, geometry was born by studying astronomy and studying the way land was distributed. So even in the ancient thousands of years ago, basically the language of geometry was born through the study of the night sky. Another famous example is, of course, Newton, Leibniz, and others inventing the language of calculus, of analysis, in order to approach mechanical problems. That language wasn't there already in mathematics. It gave a new vocabulary that was, of course, extremely successful. Another interesting example is the birth of modern algebra and symmetry. the fact that symmetry actually was discovered mathematically in the context of solving polynomial equations. It's Abel and then Galois studying the quintic equation somehow led them to study the structure of groups, in particular, the symmetric group on 5 elements. And so I think the big question that we are confronted right now, if we take the modern language of physics, quantum field theory, particles, string theory, what is the natural mathematical language that will come out of it? And I think this is somehow a great promise. I would say we only have little parts of this new language, but I think it's extremely exciting because clearly quantum field theory, quantum mechanics is a deeper level of reality. And if classical mechanics has been such a fruitful source for new mathematics, in some sense, quantum mechanics, which is in many ways the true language of physics, should be even much more richer. Now, this is, by the way, an interesting element to think about the context of mathematics. And for me, the good example is this wonderful article that was written by the famous mathematician Bill Thurston, great geometer, the pioneer of three-dimensional geometry, who lost much too early, who wrote a paper on proof and progress in mathematics. And in that paper, he asked the question, is there a best definition of a mathematical object? And he takes as an example the derivative of a function, something that we all use every time. And he starts, well, what is the right definition of a derivative? And he starts, well, we start with the formal definition. It's the epsilon delta definition that you learn in a rigid course of calculus. Quite remarkably, in the printed version of the article, he makes a mistake in this. But this only gives a limited intuition. We can think of it also as the rate. There's a natural sense of velocity. And if you think of a derivative as a velocity, then you also know it has an orientation because it could be a three-dimensional vector, in fact, an n-dimensional vector. Or you can think of it as a tangent. But then actually it's very natural generalizes to a slope, to a function of more than one variable. Or think of it as they did in the birth of calculus as an infinitesimal change. Or think about it as a discrete change, where you have a delta instead of a derivative. Or think of it symbolic. Now you can take the derivative of x to the n, where x is not a number, but it could be very much more complicated algebraic object. And the multiplication can be more complicated, but you can still have derivatives. Or think of it as the linear approximation. Or think of it as microscopic, zooming in into a function. If you zoom in, every function becomes linear. And then at some point, Thurston says, well, the definition 37 for him, that the derivative of a real function f in a domain D, well, you can read it, is a Lagrangian section of a cotangent bundle. And Thurston describes, there was a moment where definition 37 was the appropriate one for me. And I guess his point is that all these definitions, all these different contexts, all these different perspectives add value to the concept of a derivative. And so, for instance, just to give an example, in knot theory, there's the concept of a derivative because you can look at the intersection of two strands in a knot, in a projection of a knot, and make it either an overcrossing and an undercrossing, and take the difference of these two different kinds of topologies. So the use of the concept of a derivative is so high because it's moving in this very large space of possible interpretations. Now, another element to think about this math physics context is what I would say truth and beauty. That's actually the motto of the Institute for Advanced Study. And in fact, the epigraph of weakness essay starts by a quote from Bertrand Russell, where he describes the beauty of mathematics, this supreme beauty, cold and austere, the true spirit of the light, clearly written a long time ago. But it's one of the driving forces of mathematics. And again, there are many quotes about this power of truth and beauty. Famously, Herman Weil, professor at the Institute for a long time, was asked, well, what do you have a preference? And he said, well, he always tried to unite the true with the beautiful. But if you had to choose one or the other, I usually chose the beautiful. This Paul Dirac, who famously said, it's more important for our equations to be beautiful than have them fit experiment, which is, I think, a wonderful quote. You know, there's a lot of depth to that. There's, by the way, an opposite point of view that I want to contrast with this, which is, I think, nicely formulated by John Wheeler. John Wheeler said, you know, every law of physics pushed to the extreme will be found to be statistical and approximate, not mathematically perfect and precise. And if you think about that, that's again beauty of a very different kind, because the statistical nature, so to say, allows the mathematics to breathe and be flexible and allow modifications. No, the rigidness has a certain fragility. It can easily break and snap. While if there is a certain statistical flavor to it, we'll see this in a moment, it adds a lot of flexibility. And there's this famous quote I like very much by Francis Crick, co-discoverer of DNA: any theory that accounts for all the facts is wrong because some of the facts are always wrong. So we have to be very hesitant to embrace absolute truth. Now, beauty in mathematics, I would say, also comes in various shapes and sizes. And you know, one distinction I want to make, that you know, there are essentially two kinds of flavors of aesthetics. There's I would say, a universal beauty. That's the people who are excited about that. They like the abstract concept, like a vector space, an arbitrary dimension, or linear algebra, or calculus, or category theory. While there is another brand of aesthetics which likes the exceptions to the rule, like the Platonic solids, or the Lie group E8, because it's the most complicated one. The Monster group, which is in some sense the most complicated simple group, or the octonians. And there is a certain draw to this too. And in fact, you might see both of these kinds of appreciation of mathematical beauty in physics. The second one, I like to compare to these kind of 17th century cabinets of curiosity, the Wunderkammers. So they're strange exotica that we feel attracted towards. And so the question is, even if beauty is a guidance, which of the two variants is the most productive one? And there's a famous cautionary tale, let me share it here, which is Johannes Kepler. Now, Kepler was absolutely fascinated by geometry and by the Platonic solids. And in his youth, he was still very young, he had a cosmology based on this. It's a famous story. He thought, well, at that point, he wanted to explain why there are 6 planets. There are 6 known planets at that time, that in the Copernican model would rotate around the sun. And he knew there were 5 Platonic solids. And so he was able to connect the two facts by building a cosmology, that is to say, a set of interlocking Platonic solids. Can be done in a certain number of ways. And you can find a model by fitting these solids inside each other that would give a prediction for the ratio of the sizes, the radii of the orbits of the planets. And that was actually one of his earliest publications. Now we think that is like wrong. It's wrong in so many different ways. But what I like about the story is that Kepler himself proved it wrong. And he proved it wrong when based on careful observation, he noticed that the planets are not moving on circles, but on ellipses, which of course totally destroys this model. He called them ovals. And there's an interesting correspondence of Kepler with actually the assistant of Tycho Brahe, who of course was to a large extent a mentor of Kepler and produced a lot of the astronomical data. And he was accused of kind of making physics ugly by introducing these ovals. And he writes back, he says, well, it's as though I have sinned with the oval I've left. It's like being punished for leaving behind one barrow full of shit, although I've cleaned the rest of the Augean stables. So famous metaphor of the Augean stables. So he cleaned all the messy mathematics, but he left something behind, which was the ugly shape of an ellipse. And we would say it's ugly because it's not rigid. It has a moduli. It can be all possible shapes. Of course, now we know that all these celestial orbits are conics, and of course beautifully explained by Newton's 1/r² law. And they're all sections of conics, so parabola, circles, ellipses. Actually, there's a unified theory, and there's a beautiful symmetry underlying it. In fact, the symmetry SO4. So I think that's a perfect example where Kepler was attracted by the exotic brand of aesthetics, but actually found that the generic one was much more powerful. Now, if we move to modern history, so say the last 60 years after Wigner's essay, in some sense things moved in the wrong directions. In the 1960s, you can argue that actually there was a lot of separation between mathematics and physics. In the 1950s and 60s, I think mathematics felt it was needed to have move inward, look at the internal rigor, and rebuild mathematics in a very precise and rigorous fashion. It's usually associated with the French Bourbaki style of doing mathematics. The famous quote of the Bourbakistes was, "Structures are the weapons of mathematicians." So it introduced what sometimes physicists think of abstract nonsense in great quantities. And on the side of physics, in fact, there was an opposite movement. In many ways, people declared the end of reductionism. So in the 1960s, when there was this barrage of elementary particles, or nuclear particles, hadrons, we would say now, endless numbers of particles, there was a certain current, the S-matrix theory, that basically was revolutionary in the sense that it rejected reductionism and basically proposed that there are no fundamental particles. There are no fundamental laws. In the language of Geoffrey Chew, the aristocratic structure of atomic physics as governed by quantum electrodynamics, that was the gold standard of theoretical physics, very simple laws, very precise calculations, was replaced by the revolutionary character of nuclear particle democracy. As Chew said, every nuclear particle should receive equal treatment under the law. And that meant in some sense that this dream of a mathematical precise underpinning evaporated. There's a famous episode, we'll see them soon, John Wheeler and Richard Feynman. So John Wheeler was organizing a meeting of mathematicians and physicists in 1966, and he invited Feynman to come and talk to the mathematicians about what physics was doing, and this was part of his letter of invitation. Trying to get to express ourselves in the language meaningful to mathematicians. Others. So he was really trying to do the good thing. And Feynman answered, I think, in a one-sentence response: "I'm not interested in what today's mathematicians find interesting." End of discussion. And of course, this year we sadly lost Freeman Dyson, and I think one of the greatest mathematical physicists of the last 100 years. And Freeman famously wrote in 1972 that he was acutely aware of the fact that the marriage between mathematics and physics, which was so enormously fruitful in past centuries, has recently ended in divorce. Well, I would say the opposite was true. This kind of black box image of the S-matrix theory and the giving up on reductionism was as strong as it could be, because not only could the box be opened, but inside was the standard model of elementary particle physics. This is in a very concise way the Lagrangian describing all particles and fields in the standard model. And the great thing is that all the elements that appear there, gauge fields, connections, covariant derivatives, spinors, all are natural objects in the language of differential geometry, differential topology, actually objects that mathematicians could recognize if somebody explained to them what the mathematical interpretation of these physical objects were. And of course, part of this is that in a reductionist image, these particle processes are described by looking at all these individual Feynman diagrams, the individual processes where particles exchange force particles, and can do this in very, very complicated way. And each of these Feynman diagrams could be calculated with, unbelievable precision. As you know, some of the most precise measurements in physics in total, up to 12 decimals, are actually done in this very esoteric branch of the very smallest particles. Now, I would say this dialogue that was so successful in the past, this marriage, started in a subtle way. An important element was actually a seminar run in Stony Brook, New York, Long Island, in the early 70s between Xian Yang, who at that point headed the physics department, and Jim Simons, who headed the math department. And they started to compare notes, and they, in this article that actually gave a review of it, it's essentially a dictionary. They find out that what the physicists were studying in terms of gauge potentials and Dirac monopoles had interpretations in mathematics as principal fiber bundles, as connections and curvatures, as the first Chern class. In some sense, there was a very nice dictionary. Note, by the way, that in this dictionary, the sources of the gauge field on the left-hand side, particularly for the non-abelian gauge field, were absent yet in mathematics. And now we have a much better interpretation, but they are they observables, etc. So, but it's a good example of a dictionary as a metaphor for the interaction between physics and mathematics. So I would say from that point on, we got a blossoming connection. And I summarized this 20 years ago in a cartoon that in 1968 we had the physicists studying Feynman diagrams, the mathematicians doing deep things in topology and index theory, and the two were not able to discuss. And 30 years later, sadder and wiser, certainly the mathematicians start to study Feynman diagrams, and the physicists start to understand index theory because it's relevant for anomalies, etc. So I think this is what we call progress in science. And Jeff, when he invited me to give this public lecture, asked me very pointedly, what's the third cartoon? Where are we now? How would you sketch it? And I will come back to that. Now, I talked about beauty in mathematics, but I think it's important also to realize that there are two strands of beauty in physics. And what David Gross liked to say, the garbage versus beauty discussion. And there are 2 points of view. I think certainly many of us here are by training particle physicists. And then you would say, well, in particle physics, you explain the garbage of everyday life, even collisions in a detector, in terms of the reduction to elementary particles. And the true beauty you find in the standard model, this very simple Lagrangian, these very simple rules that then explain very complicated phenomena at larger scales. That's, I would say, what one half of physics looks at when they discuss the beauty in nature. The other half of physics has just the opposite point of view. Now, if you're a statistical physicist or condensed matter physicist, you would say, well, no, you look at the individual molecules, they're extremely complicated. You can look at the individual molecules in a glass of water. Nobody would like to describe this interacting system of 10 to the 24 degrees of freedom. The beauty is actually in the collective behavior, in the hydrodynamics and thermodynamics. At large scale, you find beautiful laws that actually are very precise. This is basically John Wheeler's point of view. The true beauty of the laws of thermodynamics is that they are statistical. Therefore, they are universal. Therefore, they are applied in such wide context. And that's why we all believe that the second law of thermodynamics holds not for any possible system, but it only holds in a strict limit where the number of components becomes infinitely large. Now, I would say the laws of physics, fundamental physics, have the same dichotomy. We have two languages. We have a language of general relativity describing gravity. It's a language of geometry, of curvature, of space and time. And we have a completely separate language to describe the very small, quantum mechanics. with, I'll come back to this, probability, superposition, all these crazy things. And I would say it somehow reflects another dichotomy in mathematics, which is the one between geometry and algebra. Even if students study mathematics, I notice that, some of them love to think in terms of geometrical figures, in visuals, in terms of right brain activities, and others like very much the algorithmic element in mathematics, the step-by-step, the language way to look at math as a language is basically the left brain approach. And both of them are actually present in physics. And one of the points I'm going to make is that often modern string theory, quantum field theory is relating these two halves of our brain. So as we see in much more detail, quantization is actually taking geometrical objects and assigning to them algebraic quantities. Whereas a lot of modern, say, quantum gravity approaches are in the opposite way. They start with an algebraic system, a quantum mechanical system with some number of degrees of freedom, and then show that in the limit where these degrees become very large, effective geometries appear. So geometry is an outcome. It's not a starting point. And so in some sense, the true approach that we are aiming for is a natural synthesis, which I think we call quantum geometry or quantum gravity, that has both the algebra and the geometrical point of view unified. And I think this is certainly something from a mathematical point of view, what string theory aims for and partly succeeds in doing, which is, I think, extremely exciting. Now, if you go back to quantum mechanics, it's good to realize that progress in physics comes with losses and gains. If you there are certain elements that if you learn quantum theory, you have to be accustomed that there are certain things no longer true, like determinism or a visualization of what actually is happening in the world. Classical mechanics has a setup that is very clear and crisp from a mathematical point of view. You have some phase space, some set of variables, momenta, and coordinates. You have a dynamical system that evolves through a Hamiltonian, and basically, that was Newton's big discovery, that basically all of science is a dynamical system. Every branch of science is basically science defined as the answer to the question, what happens next? If you go to quantum mechanics, we have to deal with Heisenberg's uncertainty principle. P and Q become operators that do not commute. So you either think of it in terms of momenta or in positions. I personally very much like this famous quote by Wolfgang Pauli. When Heisenberg discovered his relation, he wrote to Pauli, and Pauli wrote back. This is 2 weeks after the discovery. And Pauli writes, well, I think I understand what you were doing. If you can see the world with a PI, and one can see the world with a QI, but if one opens both eyes, then one becomes crazy. It's impossible to think of the world both from a momentum and a position point of view. And this duality, that in some sense you have to pick a set of variables, but both of them are appropriate, is a wonderful theme, I would say, that is part and parcel of quantum theory and that we're still struggling with. So the wave function particle in quantum mechanics can be either a function of Q or a function at P. Fourier transform will bring you to one to the other. And I would say it's the earliest occurrence of what we now call a duality. So what quantum mechanics does, of course, it does something quite spectacular. It takes this phase space, this very complicated geometry, could be extremely complicated, and quantization replaces it by a state space, a Hilbert space, that typically is infinite dimensional and becomes linear. Of course, and so the gain in quantum mechanics is that we can now take two states and consider their linear superposition. And this, again, from a classical mathematical point of view, something quite bizarre, that you can add the different states of the world in a linear fashion, and that it has a probability interpretation. The coefficients, absolute value squared, are the probabilities of either event 1 or event 2 occurring. So that's a major step. And of course, there's this beautiful reformulation in terms of the path integral. So in classical mechanics, I would say, a lot of classical mathematics is answering the question, suitably generalized, how do I get from A to B? And usually there is an action principle there. There's a function that you minimize. And so in plane geometry, obviously it's the straight line. In a curved geometry, it would be a geodesic. And in a more abstract sense, it would be the absolute, or it would be one of the minima of the action. So there's a variational problem that actually gives this specific solution. In quantum mechanics, we have a very different point of view. We have this view of a sum over histories. In quantum mechanics, you explore all possible paths, and each path comes with a probability amplitude. That's e to the I s over h bar. So it's basically, if the action is close to the critical point, it will be a very probable path, and the ones that are far away are much more unlikely. But mathematics, the mathematics of quantum theory forces you to consider all of the different possibilities at the same time, which I would say is a radical different point of view. In fact, it rhymes very well. It resonates with modern mathematics, because modern mathematics doesn't consider a single object. It always sees it as part of a whole set, I would say, a category of these objects. You never look at a symmetry group, one space, one Lie algebra. You consider the set of all these polyhedra. And then you build up layers. So you start with the object, then you look at the relations among these objects. And then you look at the relations among the relations. And then you build up an infinite tower of more and more complex and more subtle information built in of these objects. So one of the tremendous insight was that this abstract point of view of considering all objects at the same time perfectly fits in the quantum approach, where the path integral actually in a natural way adds all these things together. In fact, it adds them together with, in one function, a path integral with certain phases. And that's a great thing, that this, in some sense, produces formulas. Now, another open question is, what is exactly a quantum field theory, which is the bread and butter of modern theoretical physics. So typical, we think of quantum field theory as kind of a local quantum system. So I think of this often as a bucket of paint. So you have the local rules, mathematically the gauge group, the representation, so the matter and the forces. Then you have a space or space-time manifold. And you can basically paint that space-time manifold by covering it with the quantum field theory. And then the formulas of quantum field theory will produce for you numbers like the partition functions, scattering functions, etc. So this, I would say, is a very elegant and just the way you learn quantum field theory in textbooks. But I think we have come to understand that the situation is much more complex. Because, one of the most amazing things is that even in that space of field theories, there are dualities. So what typically can happen, and we have billions of examples of this, that you can take two different classical field theories, or two buckets of paint, red paint and blue paint, and that these theories, these classical theories, actually are connected, because there is a moduli space. If you look at the space of all possible quantum field theories, they both are somehow living at the edge. Now, if you get close to the edge of the space of quantum field theories, you discover the classical limit, essentially. You can connect them. So there's a path connecting one system to another system. So the paint is red at one end, when we have the one classical limit, and the paint is blue in another limit. So what happens in between? What is the color? And so this is, I would say, a vast generalization of the Fourier transform, or the wave-particle duality of quantum mechanics. And I would say we modern quantum field theories are in the same situation. What do we see if we open both eyes, if we see both red and blue? So the remarkable thing in studying quantum field theory is that though the quantum field theory themselves are quite mysterious objects, we have a much better understanding of the moduli space of it. And by the way, you know, we find both objects of generic beauty and objects of exceptional beauty there. Now, there are other ways to study quantum field theory. You know, you can do it in terms of local algebras. You can do it by trying to cut the space in different ways. And I think the honest point of view is here that we're still struggling with, I would say, Hilbert's sixth problem. What is the axiomatics, the right axiomatics of quantum field theory? Now, let me now give two examples of the power of these ideas from physics in mathematics. And these are well-known examples, and I won't spend too much time of it. And the first is from particle physics. And you know, it's the application to knot theory. So mathematicians be studying knots, topological knots. They want to classify them, and they basically have this set of all possible knots, and they want to basically distinguish them. And quantum field theory is perfectly set up to do so. So this goes back to one of my all-time favorite anecdotes. It's here is a little quote from Feynman's Nobel lecture, and he explains the anecdote. He says he's being called in the middle of the night when he was a graduate student by his thesis advisor, John Wheeler, and John Wheeler asked him, why do all electrons have the same charge and the same mass? And he answers, because there is only one electron. They're all the same electron. And this was Wheeler's point of view. Here's space and time. Here's the electron. And in under Wheeler's law, it's not only to go up in time, but also go back in time and up and back, and it can weave a big knot. So he thinks of the trajectory of a particle through space and time as making a knot. And clearly, if you look at this as a series of events, now you have one particle, but if you cut it in the middle, you see many particles and antiparticles, particles going down in time. And clearly they have the same properties because it's just the same particle that, you know, has made a few loops through space and time. So it's a beautiful point of view. Feynman describes it, immediately remarks, you know, why aren't there equal number of particles and antiparticles, electrons and positrons? And Wheeler says, well, perhaps they are hidden inside the proton or inside the nucleus. But of course, this was the birth of Feynman diagrams. And one of the simplest possible Feynman diagram is this one. It's the one where a particle and antiparticle are created out of nothing and disappear again. Or if you wish, just a particle going up and down in time through a closed loop. Now, if you think of knots as moving through three-dimensional space-time, so two space and one time direction, you can actually think of a knot as one of these virtual particles, a vacuum diagram, in particular in this Chern-Simons gate theory. And the rules of physics allow you to calculate the probability amplitude for such a process. In fact, you can do it even perturbatively. You can look at a quark going around and looking at, you know, exchange of a single gluon or two or three or more. So the rules of quantum field theory will assign complex numbers to each of these knots that actually will, when the rules are cleverly chosen, will produce a topological invariant. So this is a wonderful example where you take a geometrical object and quantum field theory actually assigns a probability amplitude to it. So these quantum knot invariants have been extremely successful. It led to a blossoming of a field of basically this kind of low dimensional topology. And I would say this, you know, happened in the 1980s, and the rest of it is quite a successful story. My second example is also quite famous. It's come from string theory. It's the example of mirror symmetry. Now, that's something that involves a mathematical field called enumerative geometry. It's calculating the solutions to polynomial equation. It starts with a space, in fact, a complex three-dimensional space called the quintic in this example. It's the solution to this, this particular equation you see here on the screen. Since you can scale the variables, actually there are only three complex dimensions to this. So it's a six-dimensional real manifold. It's a solution to Einstein's equation. And mathematicians study the curves on such a manifold, and you can, a curve is just means that each of these five variables, x1 to f5, are themselves polynomial equations of a certain degree, say degree d. And you can study the number of curves of degree d for d equals 1, 2, 3, etc. Well, in a suitable way formulated, you get integers, which are the Gromov-Witten invariants. We don't need to go into details. But for instance, if you take d equals 1, you count the number of lines on the quintic. There are 2,875 of them. If you take d equals 2, you have conics. This is something that was calculated in the first was a number from the 19th century. This is a number calculated in the 1980s. And then for d equals 3, you count the number of cubics, it becomes a very large number. These calculations were exponentially more difficult. And there's a beautiful story of this particular number because a physicist asked the mathematicians to calculate this number. And when the mathematicians came back with a number, the physicist said, "Are you sure it's the right number? Are you sure there's not a mistake in your algorithm?" And they checked the algorithm, and it turns out indeed there was a mistake. And so it took a second iteration to come to this number, 370,206,375. And of course, there was something going on. And the thing that was going on, that the physicist had all the numbers. And it's hard to imagine the shock to enumerative geometers, algebraic geometers, when they first saw this list, because it's something that's exponentially more difficult. So how could you do all of these numbers at the same time? And again, it's a beautiful illustration of the power of quantum theory. Because actually what was behind this was a string theory calculation, where in string theory, the shape of the string, basically using Feynman's path integral, has to be summed over all possible paths, and so had to be summed over all possible degrees. So one part of this, the solution to this very difficult math problem, is to realize that adding all these numbers, these degrees, these Gromov-Witten invariants, n of d, in a single function made sense. And this function actually is the quantum amplitude for a string to be in this particular background. Well, the second element was something very deep, that if you do this calculation, clearly there's a nice physical interpretation, but it doesn't lead to the solution, that there was a duality that linked the original manifold to a so-called mirror manifold, a manifold with a very different topology that actually was equivalent in the quantum sense. And that it turned out that in the mirror manifold, this very difficult calculation on the left-hand side was essentially very easy. It was a classical object, a classical period, calculated on the right-hand side. So in some sense, by this very fancy form of a Fourier transform, you were able to solve this exponentially hard problem on the left in terms of a very elegant formula on the right. Now, in the last 10 minutes, 15 minutes, let me say a few words about where we are currently. And I would say currently we are at the difficult part. We're now trying to embrace not quantum field theory, but quantum gravity. And quantum gravity is a difficult subject because from an intuitive way, it's the space-time itself becomes a quantum object. So the notions of coordinates, the notions of geometry itself disappear. So how can we do geometry without geometry? And I think this is an outstanding problem. And the suggestions out of physics, how to deal with it, are very deep, and I think will have a tremendous impact in mathematics. So the way I see this is like a three-step process. Now we start with classical geometry, as it goes back to the Babylonians. Then string theory got us to this level of stringy geometry. Instead of looking at geometry through the eyes of a point, we look at it, the loop space, at how a string is propagating through it. And we already get some magical effects. We get like mirror symmetry, for instance. So two different classical geometries can be connected through one quantum object. But the next phase is where geometry itself starts to disappear. True quantum geometry, I think we are learning, is an emergent phenomena, and it's much better studied dual to quantum systems that have no intrinsic notion of geometry at all. And I would say the breakthrough came in the 1990s, in what's usually called the second superstring revolution, when we realized that string theory not only contains these closed strings, these loops, but contains open strings and contains branes. Branes are subspaces they could be sheaves, they could be vector bundles in a space-time manifold. And a open string is literally a segment that can begin and end on these branes. Just as closed strings produce gravity, open strings produce gauge fields. And the important conclusion was that if you have multiple of these branes, so instead if you have one, you have n, you're very naturally led to consider non-abelian gauge fields. In fact, the rank of the gauge field is given by the multiplicity of the brane. And the surprising thing is you can now take a limit where the number of these branes becomes very large and something quite magically happens. A new form of duality was discovered, which we now call the gauge-gravity duality. Essentially, the statement is a system of large number of branes. So a system of a gauge field of a large rank is dual to a effective curved space-time geometry. So the closed strings on the right-hand side are, in some sense, equivalent to the open strings on the left-hand side. So in some sense, you can produce curvature, you can produce emergent curved space-time geometry out of a strongly interacting non-abelian gauge field. Now, the intuition behind this is a little bit the following. So if you think of the Feynman diagrams describing open strings, they have a very beautiful interpretation. They're not little cylinders, they're little strips. The interactions of open strings you can think of as a very natural thing. It's essentially matrix multiplication, so that you glue the strips together. And so if you consider open string diagrams, as you see in the animation on the left, and you consider a large, strongly interacting quantum effect. So when there are basically many, many loops in these open string diagrams, then this was the original intuition of Gerard 't Hooft, that in some sense the surface started to be filled in. These are kind of fishnet diagrams. In some sense you start to fill in the middle. And so if there are strong quantum effects, the open string diagrams essentially become an effective closed string on the right-hand side. So this is a very physical intuition. It's very difficult to make this rigorous in a mathematical sense, but it has been extremely productive. Of course, the most productive application in physics has been the ADS CFT correspondence formulated by Juan Maldacena, that basically tells us that the gauge theory on the boundary of an anti-de Sitter space, so that's a negatively curved space-time geometry, that a gauge theory on the boundary of that space is equivalent to a bulk theory on the interior. Now, whenever these very fuzzy physical concepts emerge, of course, mathematicians ask, how do you make this precise? How have you seen this before? And I would say, well, there's at least one place where I've seen this before. And that's one of my favorite examples, and goes back to Eugene Wigner again. Now, Wigner introduced in the 1950s, famously, matrix models. He was studying the Hamiltonian of very complicated nuclear systems. And he found it very difficult to write down the Hamiltonian. And then he pioneered a statistical approach and said, well, instead of taking a specific matrix, Hermitian matrix, let's look at a statistical ensemble of matrices. And he actually started studying these Gaussian ensembles, but you can study much more complicated statistical ensembles. So this is actually very much like the opening paragraph of his essay about the unreasonable effectiveness. There are lots of factors of pi here. And what he discovered is that if you take the limits where you look at the distribution of the eigenvalues as a statistical distribution for a matrix of large rank, that actually quite surprisingly, if you scale the eigenvalues lie in a finite band. There are no eigenvalues that are larger than square root of n. And so if you scale them and take n to infinity, you get a continuum distribution. And this continuum distribution actually turned out to have the shape of a circle, a semicircle. So it's a very sharp edge. And I would say this is the example of an effective geometry. It's a statistical mechanical model. By cranking up the degrees of freedom, the rank of the matrix, certainly in the statistical limit, the thermodynamical limit, a geometry appears. And so this is just a simple example, I think, of a generic phenomena that we have to understand mathematically. How can we have effective geometries coming out of systems of large complexity? So basically the physicist says, if you take these non-abelian algebraic systems of a certain kind, they have a dial, which is the number of degrees of freedom. If you turn the dial to infinity, you will see smooth geometry appearing. Now, I think these two operations, emergence and quantization, are both pretty problematic from a mathematical point of view. But I think they are the two tools that theoretical physicists have. They can either reduce to elementary building blocks, or elementary laws can emerge out of systems with great complexity. So essentially also what modern string theory is telling mathematics is that the two sides of the mathematical brain, the geometrical and the algebraic point of view, in some deep sense are equivalent. There is a duality relating the two. That is to say that the concepts on the left-hand side and the right-hand side, minimal surfaces, Riemannian geometries, loop spaces, the closed strings, all of that is in a deep sense equivalent to studying the bread and butter of algebra, modern algebra, such as vector bundles, gate theories, K-theory, matrix models, etc. Now, all of this goes, I think, even deeper. There's the famous line by John Wheeler that he formulated in the 1960s and 70s that he called it from bit. This is actually a famous diagram that appears in the book Gravitation. I remember reading this, as a high school senior, and I had no idea what he was talking about, and I think we still haven't idea. But he had this idea that there's a big knitting machine that feeds information and then creates space-time by how the little bits are connected to each other. I think this is an extremely fruitful idea, and I would say this is the most exciting thing that's happening currently in theoretical physics. Black holes are the place where the action happens. Black holes are the perfect example of this kind of it from bit, or the modern version, it from qubit, because it's quantum information. As you know, black holes from a gravity point of view, from a geometrical point of view, are the most simple possible objects, nothing more than literally a hole in space and time. But from a quantum perspective, they're the most complex object because they're the densest way to store information, roughly 1 qubit per Planckian surface unit of the horizon. And there are, the concept of the Bekenstein-Hawking geometric entropy allows you to calculate the amount of information inside a quantum black hole. So I think that's extremely exciting, and there are some reflections of this in modern mathematics. Another thing I think that we still are struggling to interpret in a nice mathematical way is that gravity, geometry, is built upon locality. So what does it mean for 2 points to be close together? And I have no time to go into it, but another exciting development is that the way locality can be created, which is the concept of a wormhole or an Einstein-Rosen bridge in classical relativity, seem to be very closely connected to the way in which quantum information can be entangled. So superposition of quantum states that are not direct products, the things that are famous in the EPR paradox. So what we are seeing is, in some sense, a beautiful dictionary appearing between the geometrical language and the algebraic language of physics, and I would say also mathematics. So where are we now? So I would still say that we started with Galileo with this kind of nature, the book of nature that we want to read, that's written in the language of mathematics. I think I wish that would be true, but I think we are in a little bit a mixed state. I think we have the language of physics and we have the language of mathematics, and they're not one and the same. I think what we are building are dictionaries, bringing one to the other. And although there have been astonishing applications of these deep physical ideas being brought into mathematics, I think, in some ways, I like to say that math and physics seem to be non-commuting objects. That, one thing I've noticed, that it's extremely difficult to make the physical intuition behind many of these ideas mathematical precise. And often what happens is that, the physical intuition gets translated into a conjecture, and then that conjecture is proven using rigorous mathematics. So that's beautiful, it's striking, it's very productive, but it's a bit disappointing, I think, that we haven't yet found the precise language of both fields. So they're more like metaphors, perhaps, or analogies. Now, there's nothing wrong with it. This is a famous quote by André Weil. André Weil, basically famous IS mathematician, he discovered what we now call arithmetic geometry, how number theory and geometry can be connected. And often he used himself the image of a Rosetta Stone. And he says, nothing is more fucking than the obscure analogies, the blurred reflection from one theory to nothing. Nothing gives more pleasure to the researcher. One day the illusion drifts away, the premonition changes to a certitude. The twin theories reveal their common source before disappearing. And I think we're very much in that spirit. We see these illusions of understanding, but sometimes they drift away. And also, I think there's a question of what is the final outcome? What is the knowledge that we try to achieve? And I've kind of two images. Will our knowledge be like a globe that we have, a perfect understanding from all possible perspectives? Or will our knowledge be more like an atlas where you have like separate maps, and then you have basically dictionaries, ways to tell you how you go from one map to another? I think if we're honest and we look both in terms of the state of theoretical physics, fundamental theoretical physics, but also I think about the state of math and physics, we're very much on the first. We have all these overlapping domains that each of them have their own language, their own concepts. There are dictionaries bringing us from one domain to another. But I think the thing that is really missing, and perhaps it will never come, is this kind of universal language that covers everything. So I think for me, the big open question is there something like quantum mathematics? Now, we know the classical world has perhaps been the most productive inspiration of math. Everyday experience has given us numbers, has given us geometry, has given us calculus, symmetry. We see it all around us. And we know that quantum theory, in particular, the deepest understanding of space and time and gravity and particles and fields, must be an even more fruitful source of mathematical inspiration. So to end, Jeff, you asked me, what would I put as a sign here for the situation of string math in 2020? So I think the great thing is that, compared to the 1960s and 1990s, it's not that mathematicians and physicists are, in their own world or in each other's world, but I think we now have a much more, I think we have a breakthrough. I think the two rooms are being reconstructed. I think we're building a single space, but I feel it's still very much under construction. So with that, I want to end.
Thank you very much. I'm going to unmute everybody so that we could applaud Robert Degraff's beautiful and inspirational lecture.
Oh, so obviously we missed it.
Okay, so I'm going to mute everybody now and invite questions. To ask a question, you can raise your hand and I will call on you. If you look at the participant button. You can press that, and at the bottom of the participant button, there's a raise hand feature. So I open the floor to questions. Okay, in the absence of a question, I'll start. Oh, I see. Arkady Weinstein has a question. You can unmute yourself.
Thank you. Okay, Robert, I'm trying to ask you a comment on the following. To me, the most impressive, development recently was that that in some way the notion of local field theory goes to some sense at the end. Because normally in local field theory, we believe we start from short distances and we can explain whatever is going on in the theory at large distances in particular. But when the gravity becomes in the play, it looks like this notion is ended. So the theory, this idea of constructions that you can do everything starting from local version does not work. Okay. I don't know. I just wonder of your opinion on this.
Well, I think that's a very good point. So, as we say, if gravity tells us that space-time emerge, then one question, of course, also is, do you first have an emergent space-time and then you get a quantum field theory built upon that, or do both of them emerge at the same time? And this is. You can say that we still have a little bit of an asymmetric situation. I think, from that point of view, the language of geometry, the language of general relativity is emergent, and we make quantum theory more fundamental. But it could be that, in some sense, quantum itself has a certain emergent quantity to it, right? And so perhaps it's a better way to say is that if whatever the underlying structure is, out of it should come space-time and the local rules on the space-time itself. So I think that's the only way in which it can appear. And of course, we see examples of that, where in many of these kind of holographic models, you not only get an effective theory of gravity, but you get an effective theory of gravity with a bunch of gauge fields or matter fields on top of it. So you're quite right. So in some sense, and I think this might point out to some fundamental, perhaps, misunderstanding we have about quantum field theories. I think, we thought we understand them because it's a local set of rules. We know already that that's very difficult to explain dualities in terms of that, because what's your favorite set of local ingredients? But perhaps we should think about emergent quantum field theories too. I think you're quite right.
Okay, thank you.
Okay, Madhav Tiwari.
Hi, I'm Madhav. Yeah. So my question is, do we have any relations with proper mathematical formula for entropy and time? Do you have a proper mathematical formula relating to proper time and with entropy?
Well, I think I think that the right mathematical formalism is present to understand classical entropy and classical information. I would say that what we are probably is something that really has to develop. What is the appropriate sense to think about quantum entropies in this context? And I think that would be extremely fruitful area to explore. We have some bits of information there, but I think we don't have an all-encompassing theory of.
Yeah, I've been reading this space is from bit, so I thought that time can also from bit,
Well, that's also a good question, and it's a little bit related to the previous discussion that I think in our current models we have some very crisp examples where we see an emergent space direction.
Mm-hmm.
If you almost use elementary logic, so we know that space can emerge. We know that relativity theory will connect space and time. So the question is, how can time emerge? And there are many deep ideas about this, but I would say we are mostly confused about this. As you know, in quantum mechanics, time is treated in a very different way than space. And what I've learned, at least from people who thought more about this, like Nima Khani Ahmed, I think his point of view is that, probably, if there's a model where time emerged, then time will emerge together with quantum theory. So probably you shouldn't have, it's very difficult to have an emergent time within quantum theory, because our usual formulations of quantum theory involve a choice of Hamiltonian. So probably we're looking at systems where, so to say, the full Schrödinger equation emerges at once. That seemed a good intuition, but I don't think we have any concrete example at this moment.
Thank you, Professor.
Maybe I can take the opportunity to ask a more philosophical question then. So last year I taught a course in mathematical physics, and one of the things that I used to do to get my students engaged was give them an integral of the week that they had to solve, and the rule was you couldn't use complex analysis. You had to solve it in as tricky a way as you could find. And usually these things had, 1 or 2 line answers, or maybe half a page answer, and it usually was some clever trick or the other. And the student who actually won the whole competition that I ran over the whole semester would give these many page answers, and he'd refine his answers and give them back again. And as a physicist, I found this initially quite frustrating, because there was always a trick that I wanted to see, and that was what I was going to count as correct. Until I realized that actually the reason he was doing this was because he was savoring the problem. In every solution he was producing, he would give this answer that was inspired, and it wasn't the quick answer, and it wasn't the clever answer, but it was a beautiful, inspired answer. So my question is, today we're seeing these massive developments in artificial intelligence and machine learning and deep learning, to the point where it kind of doesn't make any sense to have my kids learn chess, because they're never, ever going to be the best chess player in the world. No. The best chess player in the world hasn't been a human being in 20 years. Do you think that AI will ever get to the point where it can savor a proof?
Well, let me just share one thing. So, as you know, at the Institute for a long time, we had Vladimir Voevodsky, a famous mathematician, and whose goal in life was to teach computers abstract mathematics. So his field was category theory, abstract algebraic topology. So it was very, very difficult. And he started that program, and he wrote a very long paper, I think a 700-page paper, and found a mistake in it. And then he was surprised that he made a mistake, but he was even more surprised that nobody cared about it. And then he felt, I have to have a very smart assistant. And so you could ask, why would you need that? Because why do we need 700-page proofs? But I guess a good question is, if we want to find a certain mathematical truth, think of this, as you're standing on the shore, and how deep have you swim in the ocean to find it? What is the natural? Are all the great ideas in mathematics, drifting close to the beach, or do you have to venture deep inside it? And often, I think what we have done in history is build little islands, step by step. And so at some point there was a discussion. One of his colleagues asked Volodya, why are you so interested in these very long proofs? Isn't it much nicer to have a short proof? And his answer was, well, what do you like better, a long walk in the woods or a short walk in the woods? So there might be something in what we're trying to find out, that we need to take a very long walk with many, many steps and great complexity. And then I think we can truly ask, is our human mind, and collectively in our society, are we able to climb that high mountain, so to say, without using any artificial means? So I could imagine that there's no guarantee that, and we have seen this in the past, you know, there are simple, relatively simple stated mathematical problems that, like the Kepler conjecture on fitting, you know, spheres, the close packing of spheres in 3 dimensions, that basically needed thousands of 10,000 of pages of proofs. So I think the physicists feel that whatever it's a good idea, it should be brief and easily to understand and intuitively simple. But I think we might be mistaken. Also, we don't realize that we had many centuries to work our way towards that point where we finally say, oh, it's an intuitive thing. So I could imagine that AI, or you know, it's scientists working together with these machines could be useful. And I noticed that Voevodsky would like to show this. So he had this program, and the program is trying to make a certain proof, and you could suggest something to the computer, and so you suggested, well, think about general induction, and then it would spit out pages and pages and pages, but then it would stop again because then it needed another suggestion. So that might be a way in which we work in the future. You're muted, Jeff.
There are some questions in the chat. Let me see. How does Hawking radiation affect black holes? I don't know if you want to take that.
Oh, let's see. I don't see it here. Okay.
At the bottom of the chat page.
Well, that's a kind of a long story, but you know, I think the wonderful thing is some of these mathematical models of quantum black holes that came out of string theory give a very precise way to calculate the Hawking radiation beyond the statistical approach. So I think, you know, what was very impressive and what made many of us in the field you know, really excited is that this idea that there is a precise quantum mechanical model underlying Hawking's calculation, which, you know, remind you, was a statistical calculation, you know, somehow made everybody, you know, realize that we might be very close to understanding, at least for some specific, I would say, very mathematical, conveniently chosen models of black holes, we have a full quantum mechanical understanding. So again, in this kind of battle between geometry and quantum, where geometry is predicting a more, you know, the loss of information and this, you know, thermal radiation, I would say in these models, quantum comes out as a more precise answer that actually gives a you know, microscopic way to deal with Hawking radiation and quantum information. There's much more to be said about it, but I think, you know, that was an important element in this development.
Thank you. I think the same speaker questioner has a follow-up question. Do you consider black holes to be a reality or mathematical fantasy?
Well, it's one of these wonderful examples where a mathematical fantasy became a reality, I would say. You know, we have seen images of them. You know, it's not yet mathematical proof, but it's we are seeing we're getting closer to the horizon, and you know, it's one of the most spectacular predictions of Einstein's theory. So spectacular that he himself had serious doubts of the nature of it. And I would say, you know, black hole is perhaps, you know, one of the great gifts to us, to the scientific community, because it's, you know, it's been said it's the equivalent of the atom 100 years ago, in the sense that, you know, we know it exists on paper. We know it exists in nature. On paper, there are lots of paradoxes. There's a lot of confusion. But somehow nature seemed to have found a way to solve it. And I think this is the great advantage if you're in physics instead of mathematics, that, you know, in physics you can sometimes argue that at least nature has already solved the homework. So now it's up to us to find the solution that nature has picked.
Thank you. KJ Runia, you can unmute yourself.
Yes. First of all, thank you very much, Professor Dijkgraaf, for your wonderful lecture. Very much enjoyed it. I'm terribly sorry for not having any webcam installed on my primitive Linux computer. I have no knowledge about string theory, but about the measurement problem, we've become familiar with your standard textbook interpretation, like the Copenhagen interpretation, the collapse of the wave functions, and all that. Is there any perspective that string theory might give on the measurement problem?
So it was kind of weak, but the question was whether there is any perspective coming from string theory on the measurement problem. Of course, there are many intrinsic problems in quantum theory themselves. One thing is the interpretation of quantum theory, where, in some sense, we are in the, as I would say, in the, I think typical polls show that there's not even there's no majority interpretation. There are various ways to interpret quantum theory. I would say up to now, string theory is working in a very traditional way within quantum mechanics. And so it comes with all the benefits of quantum theory, but it also comes with all the problems. The great thing, of course, is that also allows us to address cosmological issues. So I would say there could be a promise. There could be a promise that some of the interpretations in quantum theory get a resolution or a different interpretation by understanding its link to space and time and geometry. But I think it's fair to say that at this point there hasn't been a kind of new perspective on the measurement problem that actually is coming from this kind of gravitational point of view. But perhaps some of the other speakers of this conference have a different point of view, but I think actually there's no insight that I know of. So I think these are still outstanding issues.
Okay, thank you very much.
Sam Waldring.
Yes, thank you. Robert, thank you for the talk. It was very nice and entertaining to listen to. I have a question as regards to your personal views on the future of education at universities with respect to the fusion of this or the emergence of this mathematical physics and physical mathematics that you, the new era that's come into fruition.
Well, I think in some sense that my experience is that though students always have been extremely creative and flexible, and are able to get information on both sides. But I think one thing that we have seen, and I think that's very, very much a trend, is that clearly the level of mathematical sophistication in various branches of physics has been increased. So where in the early 70s, people had no idea that what they were doing in physics actually had a counterpart in mathematics. I think these days there's much more refined mathematics that you have to know. And, I think actually personally, I feel that, I'm not sure there's an upper bound in the kind of math that you need to know. I think people joke if you have common sense, everybody feels that have exactly the right amount of common sense, not too much and too less. There might be a certain understanding among physicists that they know just the right amount of mathematics. But I think we have learned over, through history that it's very difficult, going back to Wigner, to declare that a certain piece of math is not effective. I think there's even a folk theorem among physicists that if there's one part of mathematics that you have been consistently not learning, skipping all the lectures, that you absolutely refuse to learn, say, what a sheaf is, that in the end, this will be exactly the thing you need in your physics research. And so this actually literally happened. I remember Joe Polchinski, the discoverer of brains, walking past a blackboard where we were discussing sheaves, and he came and took an eraser and erased the word sheaf. Didn't want to know about that. I actually said, oh, it's the thing you're doing. It's actually you brought it into physics. So I think actually it's my advice also to students is certainly in the beginning phase, read widely in mathematics, and there are undoubtedly certain branches of mathematics that we haven't been incorporating in a correct way. One thing that always has been on the horizon, I would say, certainly over the last decades, has been number theory. It's clearly one of the most exciting areas of mathematics. I think we are still struggling to find the right application. Some people doubt that we'll see number theory applied in quantum theory in our lifetimes, but I think some of the younger students in this audience might actually do so. So that could be an area that you might invest some time in.
There's a question in the chat from Robin Rathan.
Oh yeah, although Galileo said the book of nature is written in the language of mathematics, I think it gives only the mathematical truth. I'm not quite sure whether I understand the question. I think that there's a certain, perhaps the point is, if we use mathematics, what part of reality can we capture? And I think a typical attitude of a scientist would be everything. But if you have the right mathematical language. And so in that sense, I think Galileo was an interesting statement, because he said, math is the language to describe nature, and he was using Euclidean geometry. While actually what we, of course, found out soon after, that actually the right mathematical language is the language of calculus, of analysis, etc., that still had to be developed. So I would say there is this, that was my original point of the math being an environmental science. And if you bring math in a new context, you learn new vocabulary, which then is being added to the mathematical part of the dictionary. So in some sense, if there are parts of science that are not being able to capture mathematics, I think, are probably, if you believe that weakness, unreasonable effectiveness continues, I think we hope that we're able to develop new parts of math that are actually able to capture this. And I think that's in some sense perhaps for me, the overarching question that we are right now. There are certain branches of mathematics that we have been using, but perhaps also new branches of mathematics have to be developed. And I think actually physics, quantum physics, can be a great inspiration for finding these new parts of the language.
Hassan Khan.
Hi, so you mentioned at the end of your talk that the most interesting or exciting sort of open problem is the development of this hypothetical quantum mathematics, which will sort of clarify and make manifest the different dualities that we see in physics and math. Do you know, or do you consider some present work that you think is on the right track towards this program? Or what is the most promising thing that is in present existence that you think is getting towards this?
I think, we, in some sense, everything and nothing. I think actually the more, I think one thing that's very positive is that we're seeing basically the return of, I would say, something of the more axiomatic approach to quantum field theory. Whether it's the looking at scattering amplitudes, looking at conformal blocks, looking at the more category theory approach. That's something that you could think that was a little bit the approach perhaps in the 1960s, and it was of course overtaken by the wonderful success of the Standard Model and quantum gate theories and everything that brought back. But I think this kind of more axiomatic point of view might be interesting because it's as far removed from Feynman diagrams and Lagrangians as we can be, and I think it might shed a certain new light on quantum fields. So I find that promising. It involves also very advanced mathematics. So I think that actually might be a promising event. But I think the good thing is that I would say that in a little bit of meta remark that I think in theoretical physics we have convergent periods where basically all thinking about the same issue, which is very exciting. But I think we typically call them revolutions. We essentially all cite the same paper. And then there are periods where we have divergent views, where we are approaching many different directions, which often in retrospect are the most fruitful parts of the history of science. So I think the fact that we are exploring many different directions now, I think is a great thing, and we should encourage this.
Thanks, very interesting, thanks.
I think in the light of the time, I don't want to impose any further on Robert. So I would like to unmute everybody, and we'd like to thank the speaker again. So thank you, Robert. That was a really wonderful talk. And I wish everybody a good evening, good night, good morning, depending on where in the world you are. It's wonderful that we can say that, but as Robert pointed out, it would have been better if you were all here and I was saying good night.
Thank you, Jeff, and goodbye to everyone. See you tomorrow.
Yep.